No Human Left Behind, AI, Deep Learning by Valentin Vishnyakov, published by Infinia Publishing. Introduction: Embarking on a journey into the depths of artificial intelligence. Welcome to No Human Left Behind, AI, Deep Learning, a comprehensive exploration of one of the most transformative and exciting fields in artificial intelligence today. This book is designed to take you on a journey through the fascinating world of deep learning, from its fundamental principles to its cutting-edge architectures and diverse applications. Whether you are a student, a researcher, a practitioner, or simply a curious mind eager to understand the power and potential of deep learning, this book will provide you with a solid foundation and a broad perspective on this rapidly evolving field. Deep learning, a subfield of machine learning inspired by the structure and function of the human brain, has emerged as a dominant force in artificial intelligence over the past decade. Its ability to automatically learn hierarchical representations from vast amounts of data has led to unprecedented advances in various domains, including computer vision, natural language processing, speech recognition, robotics, and many others. Deep learning models have not only achieved state-of-the-art performance on many benchmark tasks but have also enabled new applications and capabilities that were previously considered out of reach. This book is structured into 3 parts, each designed to build upon the previous one and progressively deepen your understanding of deep learning. Part 1, Fundamentals and Core Concepts. In the first part, we will lay the groundwork by introducing the essential concepts and mathematical underpinnings of deep learning. We will begin with an overview of the history and evolution of deep learning, tracing its roots back to the early days of artificial intelligence research and exploring the factors that have led to its recent resurgence. We will then delve into the mathematical foundations, covering key concepts from linear algebra, calculus, probability, and information theory that are essential for understanding deep learning algorithms. We will explore the basic building blocks of neural networks, including artificial neurons, activation functions, and network architectures. We will learn about the backpropagation algorithm, which is the workhorse of deep learning, and the various optimization techniques used to train deep networks. We will also discuss important concepts such as loss functions, overfitting, regularization, and evaluation metrics, which are crucial for developing and assessing deep learning models. Part 2, Deep Learning Architectures and Applications. Building upon the foundations established in Part 1, the second part will take us on a deep dive into the major deep learning architectures and their applications. We will explore convolutional neural networks, CNNs, which have revolutionized computer vision, and recurrent neural networks, RNNs, which are designed for processing sequential data. We will examine advanced architectures such as ResNet, Inception, DenseNet, and transformer networks, and we will see how they have pushed the boundaries of what's possible in image recognition, natural language processing, and other domains. We will also explore generative models, such as autoencoders, variational autoencoders, VAEs, and generative adversarial networks, GANs, which have shown remarkable capabilities in generating new data samples, including realistic images and text. We will delve into the intricacies of these models, their training challenges, and their diverse applications in areas such as image synthesis, anomaly detection, and data augmentation. Furthermore, we will examine the application of deep learning to time series analysis, exploring how CNNs, RNNs, and transformers can be used for forecasting, classification, and anomaly detection in temporal data. We will discuss the use of deep learning in domains such as finance and healthcare, highlighting the transformative potential of these techniques. Part 3, Advanced Topics and Future Directions. The final part of the book will introduce you to more advanced topics and cutting-edge research in deep learning. We will explore the exciting field of deep reinforcement learning, where deep neural networks are combined with reinforcement learning algorithms to enable agents to learn complex behaviors and make optimal decisions in various environments. We'll look at applications in robotics, game playing, and natural language processing. We will then turn our attention to the critical topic of explainable AI and interpretability, discussing the need for understanding how deep learning models arrive at their decisions and exploring various techniques for interpreting and explaining these complex models. We will also delve into advanced architectures such as graph neural networks and capsule networks, which are pushing the boundaries of deep learning research. We will explore important concepts such as meta-learning, transfer learning, and the incorporation of external knowledge into deep learning models. We will discuss the ethical considerations surrounding deep learning, including issues of bias, fairness, accountability, and the societal impact of this technology. We will also look ahead to emerging trends, such as the development of more efficient and scalable models, the increasing importance of learning from limited data, and the deployment of deep learning on edge devices. Throughout the book, we will emphasize both the theoretical foundations and the practical applications of deep learning. You will find detailed explanations of the key concepts and algorithms, accompanied by illustrative examples and discussions of real-world applications. While we will not shy away from the mathematical details, we will strive to provide an intuitive understanding of the underlying principles and to make the material accessible to a wide audience. This book is intended to be a comprehensive and up-to-date resource on deep learning, covering a wide range of topics from the fundamentals to the frontiers of research. It is designed to be both a valuable learning tool for students and newcomers to the field and a useful reference for experienced researchers and practitioners. As you embark on this journey through the depths of artificial intelligence, I encourage you to approach the material with curiosity, an open mind, and a willingness to engage with both the theoretical and practical aspects of deep learning. The field is rapidly evolving, and there is always more to learn. I hope that this book will inspire you to further explore the exciting world of deep learning and to contribute to its future development. Let the adventure begin. Lesson 1, Introduction to Deep Learning. What is deep learning? Deep learning represents a significant advancement in the pursuit of artificial intelligence. It involves the use of artificial neural networks, which are computational models loosely inspired by the structure of the human brain. These networks are designed to automatically learn from vast amounts of data. Deep learning models are distinguished by their ability to learn hierarchical representations of data. This means that they can automatically extract increasingly complex features from raw input, eliminating the need for manual feature engineering. The deep in deep learning refers to the use of multiple layers in these neural networks. Each layer progressively transforms the data into a more abstract and useful representation. The process of learning in deep neural networks involves adjusting the strengths of the connections between artificial neurons, known as weights. These weights are updated iteratively during training, using algorithms like backpropagation and optimization techniques like stochastic gradient descent. The goal is to minimize the difference between the network's predictions and the actual target values in the training data. Deep learning has proven to be remarkably effective in a wide range of applications. It has achieved state-of-the-art results in areas such as computer vision, natural language processing, and speech recognition. The ability of deep learning models to automatically learn relevant features from data makes them highly adaptable to different tasks and domains. Deep learning success can be attributed to several factors. These factors include the availability of large datasets, advancements in computing power, particularly the use of GPUs, and the development of new algorithms and architectures. The combination of these factors has created an environment ripe for the rapid advancement of deep learning research and applications. As deep learning continues to evolve, it is poised to play an increasingly important role in shaping the future of technology and society. Its ability to solve complex problems and extract insights from data has far-reaching implications across various industries, from healthcare and finance to transportation and entertainment. The transformative potential of deep learning is only beginning to be realized. History and evolution of deep learning. The origins of deep learning can be traced back to the early days of artificial intelligence research in the mid-20th century. Early pioneers in the field explored the idea of creating artificial neurons and networks that could mimic the learning capabilities of the human brain. The perceptron, developed in the 1950s, was one of the first artificial neuron models. While limited in its capabilities, it laid the foundation for future work in neural networks. The development of the backpropagation algorithm in the 1980s was a major breakthrough. It provided an efficient method for training multi-layered neural networks. This development paved the way for the creation of deeper and more complex networks. Despite these advancements, deep learning faced significant challenges in its early years. Training deep networks was computationally expensive, and the amount of data available for training was limited. These limitations hindered the progress of deep learning, and it remained a niche area of research for several decades. The early 2000s saw a resurgence of interest in deep learning. This was driven by several key factors. The rise of the Internet and the proliferation of digital devices led to an explosion of data. This provided the fuel needed to train data-hungry deep learning models. Advancements in computing hardware, particularly the development of powerful GPUs, provided the computational power needed to train larger and deeper networks. GPUs, originally designed for gaming, proved to be exceptionally well suited for the parallel computations involved in training neural networks. Algorithmic innovations, such as the development of new activation functions like ReLU and improved optimization techniques, also contributed to the resurgence of deep learning. These advancements made it possible to train deeper and more complex networks more efficiently. A watershed moment in the history of deep learning was the 2012 ImageNet competition. A deep convolutional neural network called AlexNet, developed by Alex Krizhevsky, Ilya Sutskever, and Geoffrey Hinton, achieved a decisive victory. AlexNet significantly outperformed traditional computer vision methods, demonstrating the power of deep learning for image recognition. This breakthrough sparked a surge of interest and investment in deep learning. It led to rapid advancements in the field. Since then, deep learning has achieved remarkable success in a wide range of applications and continues to be an active area of research and development. Why deep learning now? The current prominence of deep learning is a result of the convergence of several critical factors. These factors have created a perfect storm for the rapid advancement and adoption of deep learning technologies. The availability of massive datasets, often referred to as big data, is one of the key drivers of deep learning success. Deep learning models are notoriously data-hungry. They require vast amounts of data to train effectively. The exponential growth of data generated by the Internet, social media, mobile devices, and sensors has provided the necessary fuel for these models. Advancements in computing hardware have also played a crucial role. Training deep neural networks is computationally intensive, requiring specialized hardware like GPUs. The development of powerful and affordable GPUs has made it possible to train larger and more complex networks in a reasonable amount of time. Cloud computing platforms have further democratized access to these resources. They allow researchers and developers to leverage powerful computing infrastructure on demand. Algorithmic improvements have also contributed significantly to the rise of deep learning. Innovations in network architectures, activation functions, and optimization algorithms have made it possible to train deeper and more accurate models. The development of user-friendly deep learning frameworks, such as TensorFlow and PyTorch, has lowered the barrier to entry for researchers and developers. These frameworks provide high-level abstractions and tools for building, training, and deploying deep learning models. They simplify the development process and make it easier to experiment with new ideas. The combination of big data, powerful hardware, algorithmic innovations, and user-friendly software has created a fertile environment for deep learning to flourish. These factors have enabled researchers and practitioners to develop and deploy deep learning models that are transforming various industries and aspects of our lives. Applications of deep learning has demonstrated its versatility and power across a wide array of applications. Its impact is being felt in numerous fields. In computer vision, deep learning has revolutionized image recognition, object detection, and image segmentation. Deep learning models can now classify images with accuracy that rivals or even surpasses human performance. They are used in self-driving cars to identify objects on the road, in medical imaging to detect diseases, and in security systems for facial recognition. In natural language processing, NLP, deep learning has significantly advanced the state-of-the-art in tasks such as machine translation, text summarization, and sentiment analysis. Deep learning models can understand and generate human language with increasing sophistication. They power virtual assistants like Siri and Alexa, enable real-time language translation, and are used to analyze customer feedback and social media posts. Deep learning has also made significant inroads in speech recognition. Deep neural networks can transcribe speech with high accuracy, even in noisy environments. This technology is used in voice search, dictation software, and to provide closed captions for videos. In the field of robotics, deep learning is enabling robots to learn complex tasks and interact with their environment more effectively. Deep reinforcement learning, a combination of deep learning and reinforcement learning, has shown promise in training robots to perform tasks such as grasping objects, navigating complex environments, and even playing games. Beyond these areas, deep learning is being applied in numerous other domains. These domains include drug discovery, where it is used to predict the properties of molecules and identify potential drug candidates. It is utilized in financial modeling, where it is used to forecast stock prices and assess credit risk. It is implemented in recommendation systems, where it is used to personalize recommendations for products, movies, and music. These are just a few examples of the many applications of deep learning. Deep learning versus machine learning. Deep learning is a specialized subfield within the broader domain of machine learning. While both deep learning and traditional machine learning aim to enable computers to learn from data, they differ significantly in their approaches and capabilities. Traditional machine learning algorithms typically rely on handcrafted features. This means that human experts must manually define the relevant features or characteristics of the data that will be used to train the model. This process, known as feature engineering, can be time-consuming, requires domain expertise, and can limit the performance of the model if important features are missed. Deep learning, on the other hand, automates the feature learning process. Deep neural networks can automatically learn hierarchical representations of data. They extract increasingly complex features from raw input without the need for manual feature engineering. This ability to learn features directly from data is a key advantage of deep learning. It makes it more adaptable to different tasks and domains. Another difference lies in the types of data that each approach can handle effectively. Traditional machine learning algorithms often work well with structured data, such as data organized in tables with rows and columns. Deep learning, on the other hand, excels at processing unstructured data, such as images, text, and audio. The depth of neural networks allows deep learning models to capture complex patterns and relationships in these types of data. Deep learning models typically require much larger amounts of data to train effectively compared to traditional machine learning models. This is because deep learning models have many more parameters that need to be learned. The availability of big data has been a key factor in the success of deep learning. While deep learning has demonstrated superior performance on many tasks, it is not always the best choice. Traditional machine learning algorithms can be more efficient and interpretable for simpler problems or when data is limited. Deep learning frameworks and libraries. The development and deployment of deep learning models have been greatly facilitated by the emergence of powerful and user-friendly deep learning frameworks and libraries. These software tools provide high-level abstractions and building blocks for creating, training, and deploying neural networks. They handle many of the low-level details, such as memory management and optimization, allowing researchers and developers to focus on the design and implementation of their models. TensorFlow, developed by Google, is one of the most popular deep learning frameworks. It offers a flexible and comprehensive ecosystem for building and deploying machine learning models, including deep neural networks. TensorFlow provides a wide range of tools and APIs for defining and training models, as well as support for distributed training across multiple GPUs and machines. PyTorch, developed by Facebook, is another widely used deep learning framework. It is known for its dynamic computational graph, which allows for more flexible and intuitive model development. PyTorch has gained popularity in the research community due to its ease of use and strong support for research workflows. Keras is a high-level neural networks API that can run on top of TensorFlow, Theano, or CNTK. It provides a user-friendly interface for building and training deep learning models, making it particularly well-suited for beginners and rapid prototyping. Other popular deep learning frameworks include Caffe, MXNet, and Microsoft Cognitive Toolkit, CNTK. Each framework has its own strengths and weaknesses, and the choice of framework often depends on the specific needs of the project and the preferences of the developer. These frameworks are typically open source, which has fostered a vibrant community of developers and researchers who contribute to their development and share their knowledge and expertise. The availability of these powerful and accessible tools has played a significant role in the democratization of deep learning, enabling a wider range of individuals and organizations to participate in its development and application. Setting up your deep learning environment. To embark on a journey into deep learning, you'll need to establish a suitable development environment. This involves installing the necessary software and configuring your system to handle the computational demands of training deep neural networks. The first step is typically to choose an operating system. While deep learning can be performed on various operating systems, Linux is often preferred due to its flexibility, open-source nature, and strong support for scientific computing. Many deep learning frameworks and libraries are primarily developed and optimized for Linux environments. Next, you'll need to install a suitable programming language. Python has become the dominant language for deep learning due to its extensive libraries and frameworks, such as TensorFlow, PyTorch, and Keras. Installing a scientific Python distribution like Anaconda is often recommended. It simplifies package management and environment setup. Anaconda includes many of the essential libraries for deep learning, such as NumPy, SciPy, and scikit-learn, pre-installed. Once Python is set up, you can install your chosen deep learning framework, such as TensorFlow or PyTorch. These frameworks often have specific installation instructions, which may involve using package managers like pip or conda. It's crucial to follow the instructions carefully to ensure compatibility with your system and hardware. If you plan to leverage the power of GPUs for training deep learning models, you'll need to install the appropriate drivers and libraries, such as CUDA and cuDNN from NVIDIA. These enable your deep learning framework to communicate with and utilize your GPU for accelerated computations. Setting up a dedicated development environment using virtual environments is highly recommended. Tools like virtualenv or conda environments allow you to create isolated environments with specific versions of Python and installed packages. This helps to avoid conflicts between different projects and ensures reproducibility. It's also a good practice to use an integrated development environment, IDE, or a code editor that provides features like syntax highlighting, code completion, and debugging support for Python and your chosen deep learning framework. Mathematical Foundations. Deep learning, at its core, relies on fundamental mathematical concepts from linear algebra, calculus, probability, and statistics. A solid understanding of these concepts is essential for comprehending the inner workings of deep neural networks and for developing and improving deep learning models. Linear algebra provides the foundation for representing and manipulating data in deep learning. Vectors, matrices, and tensors are used to represent inputs, outputs, weights, and biases in neural networks. Operations such as matrix multiplication, dot products, and transposes are fundamental to the computations performed within neural networks. Calculus, particularly differential calculus, is crucial for training deep learning models. The process of backpropagation, which is used to update the weights of a neural network during training, relies on the computation of gradients. Gradients represent the rate of change of the loss function with respect to the network's parameters. They guide the optimization process. Optimization algorithms, such as stochastic gradient descent and its variants, use these gradients to iteratively adjust the network's weights and minimize the loss. Probability and statistics play a vital role in understanding and interpreting the behavior of deep learning models. Probability theory provides the framework for modeling uncertainty and making predictions based on data. Concepts such as probability distributions, expectation, and variance are used to analyze and interpret the outputs of neural networks. Statistical concepts, such as maximum likelihood estimation and Bayesian inference, are used to train and evaluate deep learning models. Information theory, a branch of mathematics that deals with the quantification of information, also has connections to deep learning. Concepts from information theory, such as entropy and cross-entropy, are used in the design of loss functions and in the analysis of the information content of neural network representations. Neural networks. Basics. Neural networks are the fundamental building blocks of deep learning. They are computational models inspired by the structure and function of biological neural networks in the human brain. Artificial neural networks consist of interconnected nodes, often called neurons, organized in layers. Each neuron receives input from other neurons or from the input data, performs a computation, and produces an output that is passed on to other neurons. The connections between neurons have associated weights, which represent the strength of the connection. These weights are adjusted during the training process to enable the network to learn from data. A typical neural network consists of an input layer, one or more hidden layers, and an output layer. The input layer receives the raw data, such as an image or a text document. The hidden layers perform intermediate computations, progressively transforming the data into more abstract and useful representations. The output layer produces the final prediction or classification. Each neuron in a neural network applies an activation function to its input. The activation function introduces nonlinearity into the network, allowing it to learn complex, nonlinear relationships between inputs and outputs. Common activation functions include the sigmoid function, the hyperbolic tangent function, tan, and the rectified linear unit, ReLU. The process of training a neural network involves adjusting the weights of the connections between neurons to minimize a predefined loss function. The loss function measures the difference between the network's predictions and the actual target values in the training data. Backpropagation is the most widely used algorithm for training neural networks. It efficiently computes the gradients of the loss function with respect to the network's weights, allowing them to be updated iteratively using optimization algorithms like stochastic gradient descent. Different types of neural network architectures have been developed for different types of data and tasks. Feed-forward neural networks are the most basic type, where information flows in only one direction, from the input layer to the output layer. Optimization algorithms. Training deep neural networks is essentially an optimization problem. The goal is to find the optimal values for the millions or even billions of parameters, weights and biases, that define the network's behavior. This is achieved by minimizing a loss function, which quantifies the difference between the network's predictions and the actual target values in the training data. Optimization algorithms play a crucial role in this process. They guide the iterative adjustment of the network's parameters to minimize the loss and improve the model's performance. Stochastic gradient descent, SGD, is the most widely used optimization algorithm in deep learning. SGD works by computing the gradient of the loss function with respect to the network's parameters using a small batch of training data. The parameters are then updated in the opposite direction of the gradient, effectively moving downhill towards a minimum of the loss function. The size of the step taken in the opposite direction of the gradient is determined by the learning rate, a hyperparameter that needs to be carefully tuned. Several variants of SGD have been developed to improve its convergence speed and stability. Momentum is a technique that helps to accelerate SGD in the relevant direction and dampens oscillations. It does this by accumulating a moving average of past gradients and adding it to the current gradient. Adaptive moment estimation, ADAM, is another popular optimization algorithm that combines the benefits of momentum and RMSPROP, root mean square propagation. ADAM adapts the learning rate for each parameter individually based on estimates of the first and second moments of the gradients. It has been shown to be effective in training a wide range of deep learning models. Other optimization algorithms used in deep learning include AdaGrad, AdaDelta, and Nesterov accelerated gradient, NAG. Each algorithm has its own strengths and weaknesses, and the choice of algorithm often depends on the specific problem and the architecture of the neural network being trained. The field of optimization for deep learning is an active area of research. New algorithms and techniques are constantly being developed to improve the efficiency and effectiveness of training deep neural networks. Properly tuning the hyperparameters of the chosen optimization algorithm, such as the learning rate, momentum, and batch size, is crucial for achieving good performance. These hyperparameters can significantly impact the convergence speed, the quality of the final solution, and the generalization ability of the trained model. Lesson 2: Training and Evaluating Deep Learning Models. Data Preprocessing. Preparing the groundwork. The performance of a deep learning model is heavily reliant on the quality of the data it is trained on. Data preprocessing is a crucial step that involves transforming raw data into a format that is suitable for training a neural network. This often involves several stages. One of the first steps in data preprocessing is data cleaning. Real-world datasets often contain errors, inconsistencies, and missing values. These issues need to be addressed before the data can be used for training. Missing values can be imputed using various techniques, such as replacing them with the mean or median value of the feature, or using more sophisticated methods like regression imputation. Outliers, which are data points that deviate significantly from the rest of the data, can also pose problems for training. They can be identified and handled using statistical methods or domain expertise. Another important aspect of data preprocessing is normalization or standardization. Neural networks often perform better when the input features are scaled to a similar range. Normalization typically involves scaling the features to a range between 0 and 1. Standardization involves transforming the features to have zero mean and unit variance. The choice between normalization and standardization depends on the specific dataset and the requirements of the model. Feature scaling ensures that features with larger values do not disproportionately influence the learning process. It can also help to improve the convergence speed of optimization algorithms. Data transformation is another common preprocessing step. This can involve applying mathematical functions to the features to make them more suitable for the model. For example, logarithmic transformations can be used to reduce the skewness of a feature. Categorical features, which represent discrete categories rather than numerical values, need to be encoded in a numerical format that can be processed by a neural network. One-hot encoding is a common technique for representing categorical features. It creates a binary vector for each category, where each element corresponds to a specific category and is set to 1 if the data point belongs to that category and 0 otherwise. Data augmentation is a powerful technique used to artificially increase the size of the training dataset. It involves applying various transformations to the existing data, such as rotating, flipping, or cropping images, or adding noise to audio recordings. Data augmentation can help to improve the generalization ability of deep learning models and make them more robust to variations in the input data. It is particularly useful when the amount of available training data is limited. Train, validation, test split, stratifying data for robust evaluation. A fundamental principle in machine learning, including deep learning, is to evaluate the performance of a model on data that it has not seen during training. This helps to ensure that the model is not simply memorizing the training data but is learning generalizable patterns that can be applied to new, unseen data. To achieve this, the available dataset is typically split into 3 distinct subsets: a training set, a validation set, and a test set. The training set is used to train the model. This is the data that the model learns from, adjusting its parameters to minimize the loss function. The validation set is used to tune the hyperparameters of the model and to monitor its performance during training. Hyperparameters are parameters that are not learned by the model during training but are set beforehand. Examples include the learning rate, the number of hidden layers, and the number of neurons in each layer. The performance of the model on the validation set provides feedback that can be used to adjust these hyperparameters and improve the model's performance. The test set is used to evaluate the final performance of the trained and tuned model. It provides an unbiased estimate of how well the model is likely to perform on new, unseen data. It is crucial that the test set is kept completely separate from the training and validation sets and is only used once at the end of the model development process. The proportions in which the data is split into training, validation, and test sets can vary depending on the size of the dataset and the specific application. A common split is 70% for training, 15% for validation, and 15% for testing. However, other splits, such as October 10, 80 or 60/20/20, may also be used. When splitting the data, it is important to ensure that each subset is representative of the overall dataset. This is particularly important when dealing with datasets that have class imbalance, where some classes are significantly more frequent than others. Stratified sampling is a technique that can be used to ensure that each subset has a similar distribution of classes as the original dataset. Overfitting and underfitting, navigating the bias-variance trade-off. A common challenge in training deep learning models is finding the right balance between overfitting and underfitting. Overfitting occurs when a model learns the training data too well, including the noise and idiosyncrasies that are specific to that particular dataset. An overfit model performs very well on the training data but poorly on new, unseen data. It has essentially memorized the training data rather than learning generalizable patterns. Underfitting, on the other hand, occurs when a model is too simple to capture the underlying patterns in the data. An underfit model performs poorly on both the training data and new data. It has failed to learn the essential relationships between the inputs and outputs. The concepts of bias and variance are closely related to overfitting and underfitting. Bias refers to the error introduced by approximating a real-world problem, which may be complex, by a simplified model. Variance refers to the amount by which the model's predictions would change if it were trained on a different dataset. A model with high bias is likely to underfit the data. It makes overly simplistic assumptions about the relationship between the inputs and outputs. A model with high variance is likely to overfit the data. It is too sensitive to the specific details of the training data. The goal in training a deep learning model is to find a sweet spot that minimizes both bias and variance. This is known as the bias-variance trade-off. Several techniques can be used to address overfitting and underfitting. Increasing the size of the training dataset can often help to reduce overfitting, as it provides the model with a more representative sample of the underlying data distribution. Simplifying the model architecture, for example, by reducing the number of layers or the number of neurons in each layer, can also help to reduce overfitting. Conversely, increasing the complexity of the model can help to address underfitting. Regularization techniques, which add a penalty term to the loss function, can also help to prevent overfitting by discouraging the model from assigning excessively large weights to specific features. Techniques such as L1 and L2 regularization as well as dropout are commonly used in deep learning. Early stopping is another effective technique for combating overfitting. It involves monitoring the model's performance on a validation set during training and stopping the training process when the performance on the validation set starts to degrade, even if the performance on the training set is still improving. Regularization techniques, constraining complexity for better generalization. Regularization techniques are essential tools in the deep learning practitioner's toolkit for combating overfitting and improving the generalization ability of models. These techniques work by adding a penalty term to the loss function that the model is trying to minimize during training. This penalty term discourages the model from learning overly complex or specialized representations that may not generalize well to new, unseen data. One of the most widely used regularization techniques is L2 regularization, also known as weight decay. L2 regularization adds a penalty term to the loss function that is proportional to the square of the magnitude of the model's weights. This encourages the model to keep its weight small, effectively reducing the complexity of the learned function. Smaller weights tend to lead to smoother decision boundaries and can help prevent the model from fitting noise in the training data. L1 regularization is another popular technique that adds a penalty term proportional to the absolute value of the model's weights. Unlike L2 regularization, L1 regularization can lead to sparse solutions, where some weights are driven to exactly zero. This can be useful for feature selection, as it effectively eliminates the influence of less important features on the model's predictions. Dropout is a powerful and widely used regularization technique that was specifically developed for deep neural networks. During training, dropout randomly sets a fraction of the neurons in a layer to zero at each update. This prevents the network from relying too heavily on any single neuron and forces it to learn more robust and redundant representations. Dropout can be interpreted as training an ensemble of different neural networks that share weights, which helps to improve generalization. Batch normalization is a technique that normalizes the activations of each layer in a neural network. While not strictly a regularization technique, it has been shown to have a regularizing effect and can improve the training speed and stability of deep networks. Batch normalization helps to reduce internal covariate shift, which is the change in the distribution of network activations due to changes in network parameters during training. Early stopping, as previously mentioned, is another effective regularization technique. It involves monitoring the model's performance on a validation set during training and stopping the training process when the performance on the validation set starts to degrade. This prevents the model from overfitting to the training data and helps to select a model that generalizes well to new data. The choice of regularization technique and the strength of the regularization, e.g., the value of the regularization parameter, often depend on the specific dataset and the architecture of the model. Evaluation metrics, quantifying model performance. Evaluating the performance of a deep learning model is a crucial step in the development process. Various metrics are used to quantify different aspects of a model's performance, and the choice of metric depends on the specific task and the nature of the data. For classification tasks, where the goal is to assign data points to specific categories, accuracy is a commonly used metric. Accuracy measures the percentage of correctly classified data points out of the total number of data points. While accuracy is intuitive and easy to understand, it can be misleading when dealing with imbalanced datasets, where some classes are significantly more frequent than others. In such cases, a model that simply predicts the majority class for all data points can achieve high accuracy, even though it has not learned any meaningful patterns. Precision and recall are two metrics that are particularly useful for imbalanced datasets. Precision measures the proportion of true positive predictions out of all positive predictions made by the model. It quantifies the model's ability to avoid false positives. Recall, on the other hand, measures the proportion of true positive predictions out of all actual positive instances in the data. It quantifies the model's ability to identify all positive instances. The F1 score is a harmonic mean of precision and recall, providing a balanced measure that considers both metrics. It is often used as a single metric to evaluate the performance of a model on imbalanced datasets. The F1 score ranges from 0 to 1, with higher values indicating better performance. For regression tasks, where the goal is to predict a continuous value, metrics such as mean squared error, MSE, mean absolute error, MAE, and R-squared are commonly used. MSE measures the average squared difference between the predicted values and the actual values. MAE measures the average absolute difference between the predicted values and the actual values. R-squared, also known as the coefficient of determination, measures the proportion of the variance in the target variable that is explained by the model. The choice of evaluation metric can have a significant impact on how the performance of a model is assessed and compared to other models. It is important to choose metrics that are appropriate for the specific task and that reflect the desired properties of the model. In some cases, multiple metrics may need to be considered to get a comprehensive understanding of a model's performance. It's also essential to keep in mind that no single metric can capture all aspects of a model's performance, and careful consideration of the specific application and its requirements is always necessary. Cross-validation, robustly estimating model performance. Cross-validation is a powerful technique for assessing the performance of a machine learning model, including deep learning models, in a more robust way than simply using a single train/test split. It provides a more reliable estimate of how well a model is likely to generalize to new, unseen data. The basic idea behind cross-validation is to divide the available data into multiple subsets, or folds. The model is then trained on a subset of the folds and evaluated on the remaining fold. This process is repeated multiple times, with each fold serving as the evaluation set once. The most common form of cross-validation is k-fold cross-validation. In k-fold cross-validation, the data is divided into k equal-sized folds. The model is trained on k1 folds and evaluated on the remaining fold. This process is repeated k times, with each fold serving as the evaluation set once. The performance scores from each iteration are then averaged to produce a single, more robust estimate of the model's performance. The choice of k depends on the size of the dataset and the computational resources available. Common choices for k are 5 and 10. A higher value of k leads to a more reliable estimate of performance but also requires more computation. Leave one out cross-validation, LOOKV, is a special case of k-fold cross-validation where k is equal to the number of data points in the dataset. Each data point is used as the evaluation set once, and the model is trained on the remaining data. LOOKV can be computationally expensive for large datasets but provides a nearly unbiased estimate of the model's performance. Stratified k-fold cross-validation is a variation of k-fold cross-validation that is particularly useful when dealing with imbalanced datasets. It ensures that each fold has a similar distribution of classes as the original dataset. This helps to prevent situations where some folds may have very few or no instances of certain classes, which can lead to unreliable performance estimates. Cross-validation provides a more robust estimate of a model's generalization performance compared to a single train/test split. It helps to reduce the risk of overfitting to a specific train/test split and provides a more realistic assessment of how the model is likely to perform on new, unseen data. Cross-validation is a valuable tool for model selection and hyperparameter tuning. Model selection, choosing the right architecture, and hyperparameters. Choosing the right architecture and hyperparameters for a deep learning model is a crucial step in the development process. The performance of a model can vary significantly depending on these choices. Model selection often involves a combination of prior knowledge, experimentation, and automated techniques. One starting point for model selection is to consider the type of data and the specific task. Different architectures are better suited for different types of data. For example, convolutional neural networks, CNNs, are well suited for image data, while recurrent neural networks, RNNs, are designed for sequential data like text or time series. The complexity of the task also plays a role in model selection. More complex tasks may require deeper and more powerful models. Prior knowledge and experience can also guide model selection. Existing research and published results on similar tasks can provide valuable insights into which architectures and hyperparameters have been successful in the past. Transfer learning, where a model pre-trained on a large dataset is fine-tuned for a specific task, can also be a powerful approach. It allows leveraging knowledge learned from a related domain to improve performance on a new task, especially when the amount of available data for the new task is limited. Experimentation is a key part of model selection. It often involves training multiple models with different architectures and hyperparameter settings and comparing their performance on a validation set. This process can be time-consuming and computationally expensive, especially when dealing with a large number of possible combinations. Automated techniques, such as grid search and random search, can help to streamline the process of hyperparameter tuning. Grid search involves exhaustively evaluating all possible combinations of hyperparameter values within a specified range. Random search, on the other hand, randomly samples hyperparameter combinations from a specified distribution. Bayesian optimization is a more sophisticated technique that uses a probabilistic model to guide the search for optimal hyperparameters. It has been shown to be more efficient than grid search or random search in many cases. Neural architecture search, NAS, is an emerging field that aims to automate the process of designing neural network architectures. NAS algorithms use various search strategies, such as reinforcement learning and evolutionary algorithms, to automatically discover architectures that are optimized for a specific task and dataset. While NAS is still a relatively new area of research, it holds great promise for the future of deep learning. Hyperparameter tuning. Optimizing model configuration. Hyperparameters are parameters that are not learned during the training process but are set beforehand. They control various aspects of the model's architecture and the training process itself. Tuning these hyperparameters is crucial for achieving optimal performance. The learning rate is one of the most important hyperparameters. It determines the size of the steps taken during the optimization process. A learning rate that is too large can cause the optimization algorithm to overshoot the minimum of the loss function, while a learning rate that is too small can lead to slow convergence. The number of hidden layers and the number of neurons in each layer are also important architectural hyperparameters. Deeper networks with more neurons can potentially learn more complex representations, but they are also more computationally expensive to train and more prone to overfitting. The choice of activation function is another crucial hyperparameter. Different activation functions, such as ReLU, sigmoid, and tan, have different properties and can impact the training dynamics and performance of the model. The batch size, which determines the number of training examples used in each iteration of the optimization algorithm, also affects the training process. Larger batch sizes can lead to faster training due to better utilization of hardware like GPUs, but they may also require more memory. Regularization parameters, such as the strength of L1 or L2 regularization, control the amount of penalty applied to the model's weights. These parameters help to prevent overfitting and improve generalization. Tuning hyperparameters often involves a combination of manual experimentation and automated techniques. Manual experimentation, guided by prior knowledge and intuition, can provide valuable insights into the effects of different hyperparameter settings. Automated techniques, such as grid search, random search, and Bayesian optimization, can help to explore the hyperparameter space more systematically and efficiently. It's important to use a validation set to evaluate the performance of different hyperparameter settings and to avoid overfitting to the training data. Cross-validation can be used in conjunction with hyperparameter tuning to obtain a more robust estimate of the model's performance. The optimal hyperparameter settings often depend on the specific dataset and the architecture of the model. What works well for one problem may not work well for another. Transfer learning, leveraging pre-trained models. The basic idea behind transfer learning is to start with a model that has been pre-trained on a large dataset, typically for a general task such as image classification on the ImageNet dataset. This pre-trained model has already learned a rich set of features that are likely to be useful for other related tasks. Instead of training a new model from scratch, which can be time-consuming and require a large amount of data, we can fine-tune the pre-trained model on the new task using a smaller dataset. Fine-tuning typically involves replacing the final layer or layers of the pre-trained model with new layers that are specific to the new task. The weights of the pre-trained layers can either be frozen, meaning they are not updated during training, or they can be fine-tuned along with the new layers. Freezing the pre-trained weights can be useful when the new dataset is very small, as it helps to prevent overfitting. Fine-tuning the pre-trained weights, on the other hand, can lead to better performance when the new dataset is larger or when the new task is significantly different from the original task. Transfer learning has been shown to be highly effective in a wide range of applications, including computer vision, natural language processing, and speech recognition. It can significantly reduce the amount of time and data required to train a high-performing model. In computer vision, for example, models pre-trained on ImageNet, such as VGG, ResNet, and Inception, are often used as a starting point for new tasks. These models have learned to extract a rich hierarchy of visual features, from simple edges and textures to complex shapes and objects. These features can be surprisingly effective for tasks that are quite different from the original image classification task, such as object detection, image segmentation, and even medical image analysis. In natural language processing, pre-trained word embeddings, such as word2vec and glove, are commonly used to represent words as dense vectors. These embeddings capture semantic relationships between words and can be used as input features for various NLP tasks. More recently, large pre-trained language models, such as BERT and GPT, have achieved state-of-the-art results on a wide range of NLP tasks. These models are trained on massive text corpora and can be fine-tuned for specific tasks with relatively small amounts of labeled data. Transfer learning is not limited to situations where the source and target tasks are similar. Domain adaptation is a subfield of transfer learning that deals with situations where the source and target domains have different data distributions. Techniques such as adversarial training can be used to learn domain-invariant features that are useful for both the source and target tasks. Transfer learning is a powerful tool that can significantly accelerate the development of deep learning models and improve their performance, especially when data is limited. It allows researchers and practitioners to leverage the knowledge learned from large datasets and powerful models and apply it to new problems and domains. As deep learning continues to evolve, transfer learning is likely to play an increasingly important role in the development and deployment of intelligent systems. Lesson 3, Convolutional Neural Networks, CNNs, Introduction to Convolutional Neural Networks. Convolutional neural networks, CNNs, have emerged as a dominant force in the field of computer vision. They have revolutionized tasks such as image classification, object detection, and image segmentation. CNNs are a specialized type of neural network that is particularly well suited for processing grid-like data, such as images. Unlike traditional fully connected neural networks, CNNs exploit the spatial relationships between pixels in an image. They achieve this by using convolutional layers, which learn local patterns and features, and pooling layers, which reduce the spatial dimensions of the data. The architecture of a typical CNN consists of a series of convolutional layers, often followed by nonlinear activation functions like ReLU, and pooling layers. These layers are stacked on top of each other to form a deep network. The initial layers learn low-level features, such as edges and corners. Subsequent layers learn progressively more complex features, such as shapes and objects. The output of the final convolutional or pooling layer is typically fed into one or more fully connected layers, which perform the final classification or regression task. CNNs have achieved remarkable success in a wide range of computer vision applications. They have surpassed human performance on benchmark image classification datasets like ImageNet. They are used in self-driving cars to perceive the environment, in medical imaging to diagnose diseases, and in many other applications that involve visual data. The success of CNNs can be attributed to several factors. Their ability to automatically learn relevant features from raw image data, without the need for manual feature engineering, is a key advantage. The use of shared weights in convolutional filters reduces the number of parameters compared to fully connected networks, making CNNs more efficient to train and less prone to overfitting. The development of powerful hardware, particularly GPUs, has made it possible to train large and deep CNNs. The availability of large labeled datasets, such as ImageNet, has also played a crucial role in the advancement of CNNs. Despite their success, CNNs are not a silver bullet. They can be computationally expensive to train, especially for high-resolution images and videos. They can also be sensitive to small changes in the input, such as rotations or translations, although techniques like data augmentation can help to mitigate this issue. Research on CNNs is ongoing, with new architectures and techniques constantly being developed to improve their performance, efficiency, and robustness. Convolution operation, extracting local features. The convolution operation is the cornerstone of convolutional neural networks. It is a mathematical operation that involves sliding a small matrix, called a filter or kernel, over the input image. At each position, the filter performs an element-wise multiplication with the underlying pixel values. The results are then summed up to produce a single output value in a feature map. This process is repeated for each filter, resulting in multiple feature maps. Each feature map represents the activation of a particular filter across the entire image. Filters in convolutional layers are learnable parameters. During training, the network learns to adjust the values of the filter weights to extract meaningful features from the input data. Different filters learn to detect different patterns. For example, some filters might learn to detect horizontal edges, while others might learn to detect vertical edges or corners. The size of the filter is a hyperparameter that determines the spatial extent of the receptive field, which is the region of the input that affects a single output value. Common filter sizes are 3 by 3 and 5 by 5, although larger filters can also be used. The stride is another important hyperparameter that determines the step size with which the filter slides across the input image. A stride of 1 means that the filter moves 1 pixel at a time. A larger stride results in a smaller feature map. Padding is a technique used to control the spatial dimensions of the output feature map. Padding involves adding extra rows and columns of zeros, or other values, around the borders of the input image. This allows the filter to be applied to pixels near the edges of the image and can help to preserve the spatial dimensions of the input in the output feature map. The convolution operation can be thought of as a form of feature extraction. Each filter learns to detect a specific local pattern in the input image. By applying multiple filters, the network can learn a diverse set of features that are relevant for the task at hand. The use of shared weights in convolutional filters, where the same filter is applied across the entire image, significantly reduces the number of parameters compared to fully connected layers. This makes CNNs more efficient to train and less prone to overfitting. It also introduces a form of translation equivariance, meaning that if a feature is detected in one part of the image, it will also be detected if it appears in a different part of the image. Pooling layers, reducing dimensionality and enhancing invariance. Pooling layers are another key component of convolutional neural networks. They are typically inserted between convolutional layers to reduce the spatial dimensions of the feature maps. This helps to reduce the computational complexity of the network and the number of parameters. It also introduces a degree of translation invariance. The most common type of pooling is max pooling. Max pooling operates by sliding a small window, typically 2 by 2, over the input feature map. For each window, it selects the maximum value and outputs it to the next layer. This effectively downsamples the feature map, reducing its spatial dimensions by a factor of 2 in each direction. Average pooling is another type of pooling that computes the average value within each window instead of the maximum. Max pooling is generally preferred in practice as it has been found to perform better in many cases. Pooling layers help to make the learned representations more robust to small translations and distortions in the input image. By summarizing the information within a small region, pooling discards some of the precise spatial information while retaining the most salient features. This can improve the generalization ability of the network and make it less sensitive to minor variations in the input. Pooling layers also help to control overfitting by reducing the number of parameters in the network. By reducing the spatial dimensions of the feature maps, pooling reduces the number of inputs to subsequent layers, which in turn reduces the number of parameters that need to be learned. The choice of pooling size and stride determines the amount of downsampling that occurs. A larger pooling size or stride leads to a greater reduction in dimensionality but also a greater loss of information. It's important to strike a balance between reducing dimensionality and preserving important features. While pooling layers are commonly used in CNNs, some recent architectures have explored alternatives. For example, some networks use strided convolutions instead of pooling to reduce the spatial dimensions. This allows the network to learn how to downsample the feature maps in a more flexible way. Other approaches, such as spatial pyramid pooling, allow the network to handle input images of varying sizes by applying pooling at multiple scales and concatenating the results. Classic CNN architectures, landmark models and design principles. Several landmark CNN architectures have played a crucial role in the development and popularization of deep learning for computer vision. These architectures have introduced important design principles and innovations that have influenced the field. LeNet 5, developed by Jan LeCun and colleagues in the late 1990s, is one of the earliest successful CNN architectures. It was designed for handwritten digit recognition and introduced the basic structure of alternating convolutional and pooling layers followed by fully connected layers. LeNet 5 demonstrated the potential of CNNs for learning hierarchical features from image data. AlexNet, developed by Alex Krashevsky, Ilya Sutskever, and Jeffrey Hinton, marked a turning point in the history of deep learning. Its victory in the 2012 ImageNet competition showcased the power of deep CNNs for large-scale image classification. AlexNet popularized the use of ReLU activation functions and dropout regularization. It also demonstrated the benefits of training deep networks on GPUs. VGGNet, developed by the Visual Geometry Group at Oxford University, emphasized the importance of depth in CNN architectures. VGGNet used a very deep network with up to 19 layers, consisting of small 3x3 convolutional filters. It showed that deep networks could achieve high accuracy on challenging image classification tasks. GoogleNet, also known as Inception, introduced the concept of inception modules. These modules use multiple parallel convolutional filters of different sizes to capture features at different scales. Inception modules allow the network to learn more complex representations while keeping the computational cost manageable. GoogleNet also introduced the idea of one-by-one convolutions, which are used to reduce the dimensionality of the feature maps before applying more expensive convolutions. ResNet, developed by Microsoft Research, addressed the problem of training very deep networks. ResNet introduced the concept of residual connections, which allow the network to learn residual mappings instead of directly learning the desired transformation. These skip connections help to mitigate the vanishing gradient problem and enable the training of networks with hundreds or even thousands of layers. ResNet achieved state-of-the-art results on various computer vision tasks and has been highly influential in the design of subsequent CNN architectures. These classic CNN architectures have not only achieved impressive performance but have also introduced important design principles that have guided the development of new architectures. Transfer learning with CNNs, exploiting pre-trained models for new tasks. Transfer learning has become a widely used technique in deep learning, particularly in the context of CNNs. It involves leveraging knowledge gained from training a model on a large dataset for one task to improve performance on a different but related task. Transfer learning is particularly useful when the amount of labeled data available for the new task is limited. Instead of training a new CNN from scratch, which can be time-consuming and require a large amount of data, we can start with a model that has been pre-trained on a large dataset like ImageNet. ImageNet is a massive dataset containing millions of labeled images from thousands of different categories. Models pre-trained on ImageNet have learned to extract a rich hierarchy of visual features, from simple edges and textures to complex shapes and objects. These features are often transferable to other computer vision tasks, even if the specific objects or scenes are different. To apply transfer learning, the final layer or layers of the pre-trained model, which are specific to the original task, e.g., classifying 1000 ImageNet categories, are replaced with new layers that are specific to the new task. The weights of the pre-trained layers can then be either frozen or fine-tuned. Freezing the pre-trained weights means that they are not updated during training on the new task. This can be useful when the new dataset is very small, as it helps to prevent overfitting. Fine-tuning the pre-trained weights, on the other hand, allows the model to adapt the learned features to the new task. This can lead to better performance when the new dataset is larger or when the new task is significantly different from the original task. The choice between freezing and fine-tuning depends on the specific problem and the amount of available data. In practice, it is often beneficial to start by freezing the pre-trained weights and training only the new layers. Then, as training progresses, some of the pre-trained layers can be unfrozen and fine-tuned along with the new layers. This allows the model to gradually adapt to the new task while still leveraging the knowledge gained from the original task. Transfer learning with pre-trained CNNs has been successfully applied to a wide range of computer vision tasks, including object detection, image segmentation, and medical image analysis. It has also been used in other domains, such as natural language processing and speech recognition, by adapting the pre-trained features to the specific characteristics of the new data. Applications of CNNs, revolutionizing computer vision and beyond. CNNs have had a profound impact on the field of computer vision, achieving state-of-the-art results on a wide range of tasks. Image classification, which involves assigning a label to an entire image, is one of the most fundamental tasks in computer vision. CNNs have achieved remarkable accuracy on benchmark datasets like ImageNet, surpassing human performance in some cases. They are used in various applications, such as photo tagging, visual search, and content-based image retrieval. Object detection, which involves not only classifying objects in an image but also localizing them with bounding boxes, is another area where CNNs have excelled. Architectures like faster RCNN and YOLO have enabled real-time object detection in videos and images. Object detection is used in self-driving cars to identify pedestrians, vehicles, and other objects on the road. It is used in surveillance systems to detect suspicious activities, and in robotics to enable robots to interact with their environment. Image segmentation, which involves partitioning an image into multiple segments or regions corresponding to different objects or parts of objects, is a more fine-grained task than image classification or object detection. CNN architectures like UNet and Mask RCNN have achieved impressive results in image segmentation. They are used in medical image analysis to segment organs and tissues, in satellite imagery to classify land cover, and in image editing to automatically extract objects from images. Beyond these core computer vision tasks, CNNs have been applied to a wide range of other problems. In medical imaging, CNNs are used to detect and diagnose diseases such as cancer, diabetic retinopathy, and Alzheimer's disease. They can analyze medical images like X-rays, CT scans, and MRI scans with high accuracy, assisting doctors in making faster and more reliable diagnoses. In agriculture, CNNs are used to analyze satellite and drone imagery to monitor crop health, detect pests and diseases, and optimize irrigation and fertilization. This helps farmers to improve yields and reduce costs while minimizing environmental impact. CNNs are also being used in art and creativity. Style transfer is a technique that uses CNNs to apply the style of one image to the content of another image, creating novel artistic images. Generative adversarial networks, GANs, which involve training two networks, a generator and a discriminator, in an adversarial manner, can generate realistic-looking images and are also based on convolutional architectures in most cases. These are just a few examples of the many applications of CNNs. CNNs for object detection, localizing and classifying objects and images. Object detection is a fundamental task in computer vision that involves identifying and localizing objects within an image. It goes beyond image classification by not only determining what objects are present but also where they are located, typically by drawing bounding boxes around them. CNNs have become the dominant approach for object detection, achieving state-of-the-art results on various benchmark datasets. One of the early successful approaches for object detection using CNNs was the region-based convolutional neural network, RCNN, family of models. RCNN first uses a region proposal algorithm, such as selective search, to generate a set of candidate object bounding boxes in the input image. Each candidate region is then cropped and resized to a fixed size before being fed into a CNN for feature extraction. The extracted features are used to classify the region as containing a specific object or background and to refine the bounding box coordinates. Fast RCNN improved upon RCNN by performing feature extraction only once per image instead of for each region proposal. It uses a technique called ROI, region of interest, pooling to extract fixed-size feature maps for each region proposal from the convolutional feature map of the entire image. This significantly speeds up the object detection process. Faster RCNN further improved the efficiency and accuracy of object detection by introducing a region proposal network, RPN. The RPN is a small CNN that is trained to generate region proposals directly from the convolutional feature map. This eliminates the need for an external region proposal algorithm like selective search and allows the entire object detection pipeline to be trained end-to-end. Another popular approach for object detection is the You Only Look Once, YOLO, family of models. YOLO treats object detection as a regression problem, predicting bounding box coordinates and class probabilities directly from the input image in a single pass. It divides the input image into a grid and predicts multiple bounding boxes and class probabilities for each grid cell. YOLO is known for its speed and efficiency, making it suitable for real-time object detection applications. Single-shot multibox detector, SSD, is another approach that, like YOLO, performs object detection in a single pass. It uses multiple convolutional layers with different resolutions to detect objects at different scales. SSD also uses anchor boxes, which are predefined bounding boxes of different shapes and sizes, to handle objects with varying aspect ratios. CNNs for image segmentation. Pixel-level classification. Image segmentation is a computer vision task that involves partitioning an image into multiple segments or regions, where each segment corresponds to a different object or part of an object. Unlike object detection, which predicts bounding boxes around objects, image segmentation provides a more fine-grained understanding of the image by assigning a class label to each pixel. CNNs have become the dominant approach for image segmentation, achieving state-of-the-art results on various benchmark datasets. One of the early successful architectures for image segmentation using CNNs was the Fully Convolutional Network, FCN. FCN replaces the fully connected layers in a traditional CNN with convolutional layers, allowing it to output a segmentation map that has the same spatial dimensions as the input image. FCN uses upsampling, also known as transposed convolution, to increase the resolution of the feature maps in the later layers of the network. This allows the network to make pixel-level predictions. UNet is another popular architecture for image segmentation, particularly in the field of biomedical image analysis. UNet has a U-shaped architecture consisting of a contracting path, encoder, and an expansive path, decoder. The contracting path is similar to a traditional CNN, with convolutional and pooling layers that progressively reduce the spatial dimensions of the feature maps while increasing the number of channels. The expansive path uses upsampling and concatenation with feature maps from the contracting path to recover the spatial information and generate a high-resolution segmentation map. Mask RCNN is an extension of faster RCNN that adds a branch for predicting segmentation masks in parallel with the existing branch for bounding box recognition. It generates a binary mask for each region of interest, indicating which pixels belong to the object and which belong to the background. Mask RCNN has achieved impressive results on instance segmentation, which involves detecting and segmenting each individual object instance in an image. DeepLab is another state-of-the-art architecture for semantic segmentation, which involves assigning a class label to each pixel in the image. DeepLab uses atrus convolution, also known as dilated convolution, which allows for a larger receptive field without increasing the number of parameters or the computational cost. It also uses a fully connected conditional random field, CRF, to refine the segmentation results and improve the delineation of object boundaries. Advanced CNN architectures, innovations and trends. Research on CNN architectures is an active and rapidly evolving field. New architectures and techniques are constantly being developed to improve the performance, efficiency, and robustness of CNNs. One trend in CNN architecture design is the development of more efficient models that can achieve high accuracy with fewer parameters and lower computational cost. MobileNet is an example of such an architecture, designed for mobile and embedded vision applications. It uses depthwise separable convolutions, which factorize a standard convolution into a depthwise convolution and a 1-by-1 pointwise convolution. This significantly reduces the number of parameters and the computational cost compared to standard convolutions. ShuffleNet is another efficient architecture that utilizes pointwise group convolution and channel shuffle operations to reduce computation cost while maintaining accuracy. Group convolution divides the input channels into groups and applies separate convolutions to each group, reducing the number of parameters. Channel shuffle then mixes the information between different groups, improving the flow of information across channels. SqueezeNet is a small architecture that achieves AlexNet level accuracy on ImageNet with 50x fewer parameters. It uses FIRE modules, which consist of a squeeze layer with 1x1 filters and an expand layer with a mix of 1x1 and 3x3 filters. The squeeze layer reduces the number of input channels to the 3x3 filters, reducing the total number of parameters. EfficientNet is a family of models that uses a compound scaling method to uniformly scale all dimensions of depth/width/resolution using a simple yet highly effective compound coefficient. EfficientNet models have achieved state-of-the-art accuracy on ImageNet and other computer vision tasks while being significantly smaller and faster than previous models. Another trend in CNN architecture design is the use of attention mechanisms. Attention allows the network to focus on the most relevant parts of the input for a given task. Squeeze-and excitation networks, SENETs, introduce a squeeze-and excitation block that adaptively recalibrates channel-wise feature responses by explicitly modeling interdependencies between one channels. The SE block can be added to existing architectures, such as ResNet, to improve performance with a minimal increase in computational cost. CBAM, Convolutional Block Attention Module, is another attention mechanism that combines channel attention, similar to SENETs, with spatial attention. The spatial attention module focuses on where is an informative part in the feature map, complementing the channel attention. Transformers, originally developed for natural language processing, have also been applied to computer vision tasks with promising results. The Vision Transformer, VIT, treats an image as a sequence of patches and applies a standard transformer encoder to these patches. VIT has achieved competitive results compared to state-of-the-art CNNs on image classification tasks, demonstrating the potential of attention-based models for computer vision. Neural Architecture Search, NAS, is a rapidly growing field that aims to automate the process of designing neural network architectures. NAS algorithms use various search strategies, such as reinforcement learning, evolutionary algorithms, and gradient-based methods, to automatically discover architectures that are optimized for a specific task and dataset. NAS has the potential to discover novel architectures that outperform hand-designed models and to reduce the time and expertise required to develop high-performing models. These are just a few examples of the many innovations and trends in CNN architecture design. The field is constantly evolving, driven by the quest for better performance, efficiency, and robustness. Lesson 4, Recurrent Neural Networks, RNNs, Introduction to Recurrent Neural Networks. Recurrent neural networks, RNNs, are a powerful class of neural networks designed to process sequential data. Unlike feed-forward neural networks, which process each input independently, RNNs maintain an internal state, or memory, that captures information about previous inputs in the sequence. This ability to retain and utilize information from past inputs makes RNNs well-suited for tasks where the context of the sequence is important, such as natural language processing, speech recognition, and time series analysis. The key feature of an RNN is its recurrent connection, which allows information to flow in a loop within the network. At each time step, the RNN receives an input and updates its internal state based on the current input and the previous state. The output of the RNN at each time step can be a function of the current state, the current input, or both. This recurrent process enables the network to learn temporal dependencies and patterns in sequential data. RNNs can handle sequences of arbitrary length, making them flexible for processing data with varying sequence lengths. The internal state of an RNN acts as a memory that summarizes the past information in the sequence. However, the basic RNN architecture has limitations in learning long-range dependencies, where relevant information might be separated by many time steps. This is due to the vanishing and exploding gradient problems, which can occur during the training process when gradients are backpropagated through many time steps. Despite these challenges, RNNs have been successfully applied to a wide range of tasks involving sequential data. In natural language processing, RNNs have been used for language modeling, machine translation, text classification, and sentiment analysis. In speech recognition, RNNs can transcribe spoken language into text. They are also used in handwriting recognition, video analysis, and music generation. The development of more advanced RNN architectures, such as long short-term memory, LSTM, networks and gated recurrent units, GRUs, has significantly improved the ability of RNNs to learn long-range dependencies. These architectures use specialized gating mechanisms to control the flow of information through the network, mitigating the vanishing and exploding gradient problems. Research on RNNs is ongoing, with new architectures and techniques being developed to further improve their performance, efficiency, and interpretability. RNN architecture, unfolding the network in time. The architecture of a basic recurrent neural network, RNN, is characterized by its recurrent connections, which allow information to persist across time steps. An RNN can be visualized as a chain of repeating modules, each corresponding to a single time step. Each module receives an input at the current time step and a hidden state from the previous time step. It then produces an output and an updated hidden state that is passed on to the next time step. The hidden state serves as the memory of the network, encapsulating information about the past inputs in the sequence. Mathematically, the hidden state h sub t slash sub at time step t is updated according to the following equation: h sub t slash sub equals f w sub x h slash sub x sub t slash sub plus w sub h slash sub h sub t 1 slash sub plus b sub h slash sub, where x sub t slash sub is the input at time step t, w sub xh slash sub is the weight matrix connecting the input to the hidden layer, w sub hh slash sub is the weight matrix connecting the hidden layer to itself, the recurrent connection, b sub h slash sub is the bias vector for the hidden layer, and f is a nonlinear activation function, such as the hyperbolic tangent, tan, or the rectified linear unit, ReLU. The output y sub t slash sub at time step t can be computed as y sub t slash sub equals g w sub high slash sub h sub t slash sub plus b sub y slash sub, where w sub high slash sub is the weight matrix connecting the hidden layer to the output layer, b sub y slash sub is the bias vector for the output layer, and g is an activation function, which could be softmax for classification tasks or linear for regression tasks. It is important to note that the same weight matrices, w sub xh slash sub, w sub hh slash sub, w sub high slash sub, and bias vectors, b sub h slash sub, b sub y slash sub, are used at each time step. This parameter sharing is a key feature of RNNs, as it allows the network to generalize to sequences of different lengths. It also significantly reduces the number of parameters compared to a feed-forward network that would process each time step independently. To train an RNN, the network is unfolded in time, creating a computational graph that represents the flow of information across all time steps. Backpropagation through time, BPTT, is then used to compute the gradients of the loss function with respect to the network's parameters. BPTT involves applying the chain rule of calculus to the unfolded network, propagating gradients backward from the output layer to the input layer across all time steps. The gradients are then used to update the network's weights using an optimization algorithm, such as stochastic gradient descent, SGD, or ADAM. The recurrent nature of RNNs allows them to capture temporal dependencies in sequential data. However, it also makes them more challenging to train compared to feed-forward networks. The vanishing and exploding gradient problems can hinder the learning of long-range dependencies, where relevant information is separated by many time steps. In practice, more advanced RNN architectures, such as LSTMs and GRUs, are often used to mitigate these issues. Backpropagation through time, BPTT training RNNs. Training recurrent neural networks, RNNs, involves adjusting the network's weights to minimize a loss function, which measures the difference between the network's predictions and the actual target values. Backpropagation through time, BPTT, is the standard algorithm for training RNNs. It is an extension of the backpropagation algorithm used for feed-forward neural networks, adapted to handle the temporal dependencies in sequential data. BPTT works by unfolding the RNN in time, creating a computational graph that represents the flow of information across all time steps in the sequence. The unfolded network can be thought of as a deep feed-forward network with shared weights across different layers, time steps. The forward pass in BPTT involves computing the hidden states and outputs of the network for each time step, starting from the first time step and proceeding sequentially to the last. The loss function is then computed based on the network's outputs and the target values. The backward pass in BPTT involves applying the chain rule of calculus to compute the gradients of the loss function with respect to the network's parameters. This is done by propagating the gradients backward from the output layer to the input layer, across all time steps. The gradients are accumulated at each time step, taking into account the recurrent connections. Once the gradients are computed, they are used to update the network's weights using an optimization algorithm, such as stochastic gradient descent, SGD, ADAM, or ARMSPROP. The weights are updated in the opposite direction of the gradient, with the learning rate determining the step size. One challenge in BPTT is the vanishing and exploding gradient problems. When backpropagating through many time steps, the gradients can become exponentially small or large. This can make it difficult for the network to learn long-range dependencies. Several techniques have been proposed to address the vanishing and exploding gradient problems. Gradient clipping is a technique that limits the magnitude of the gradients during backpropagation, preventing them from exploding. More sophisticated RNN architectures, such as long short-term memory, LSTM, networks and gated recurrent units, GRUs, use specialized gating mechanisms to control the flow of information and gradients through time, mitigating the vanishing gradient problem. Truncated backpropagation through time, TBPTT, is a variation of BPTT that limits the number of time steps over which gradients are backpropagated. Instead of backpropagating through the entire sequence, TBPTT only backpropagates through a fixed number of recent time steps. This reduces the computational cost and memory requirements of training, but it may also limit the network's ability to learn very long-range dependencies. The choice of hyperparameters, such as the learning rate, the number of hidden units, and the sequence length, can significantly impact the training process and the performance of the RNN. Careful tuning of these hyperparameters is often required to achieve good results. Vanishing and exploding gradients, challenges in training RNNs. The vanishing and exploding gradient problems are significant challenges in training recurrent neural networks, RNNs, particularly when dealing with long sequences. These problems arise due to the repeated multiplication of gradients during backpropagation through time. In the backward pass of BPTT, the gradients are computed using the chain rule of calculus. For each time step, the gradient is multiplied by the weight matrix connecting the hidden states at adjacent time steps, W sub HH/sub in our earlier equations. When this weight matrix has values with a magnitude less than 1, repeated multiplication over many time steps can cause the gradient to become exponentially small. This is known as the vanishing gradient problem. Conversely, when the weight matrix has values with a magnitude greater than 1, repeated multiplication can cause the gradient to become exponentially large. This is known as the exploding gradient problem. The vanishing gradient problem makes it difficult for the network to learn long-range dependencies. When the gradients become very small, the updates to the weights become negligible, and the network effectively stops learning from earlier time steps. This means that information from earlier in the sequence may not be effectively propagated to later time steps, hindering the network's ability to capture long-range dependencies. The exploding gradient problem, on the other hand, can lead to instability during training. When the gradients become very large, the weight updates can be excessively large, causing the optimization process to diverge. This can result in large oscillations in the loss function or even numerical overflow errors. Several techniques have been proposed to address the vanishing and exploding gradient problems. Gradient clipping is a simple yet effective technique for mitigating the exploding gradient problem. It involves setting a threshold for the magnitude of the gradients. If the norm of the gradient exceeds the threshold, it is scaled down to have the threshold norm. This prevents the gradients from becoming too large and helps to stabilize the training process. Weight initialization is another important factor that can influence the vanishing and exploding gradient problems. Proper initialization of the weight matrices can help to ensure that the gradients are well behaved during the initial stages of training. Techniques such as Xavier initialization and He initialization are commonly used to initialize the weights in a way that takes into account the number of input and output connections of each neuron. The most effective approach to addressing the vanishing gradient problem has been the development of more advanced RNN architectures, such as long short-term memory, LSTM, networks and gated recurrent units, GRUs. These architectures use specialized gating mechanisms to control the flow of information and gradients through time. By selectively remembering or forgetting information, LSTMs and GRUs can learn long-range dependencies more effectively than basic RNNs. They have become the standard building blocks for many state-of-the-art applications involving sequential data. Long short-term memory, LSTM, networks, enhancing memory with gating mechanisms. Long short-term memory, LSTM, networks are a type of recurrent neural network, RNN, architecture that has been specifically designed to address the vanishing gradient problem and learn long-range dependencies in sequential data. LSTMs were introduced by Sepp Hochreiter and Jürgen Schmid-Huber in 1997 and have since become one of the most widely used and successful RNN architectures. The key innovation in LSTMs is the use of a memory cell and gating mechanisms that regulate the flow of information into and out of the cell. The memory cell, denoted as C(T)/sub, acts as an accumulator of information over time. It can maintain information over long periods, allowing the network to learn long-range dependencies. The gating mechanisms control which information is stored in the memory cell, which information is outputted, and which information is forgotten. An LSTM cell has three main gates: the input gate, the forget gate, and the output gate. Each gate is a neural network layer with a sigmoid activation function, which outputs values between 0 and 1. These values can be interpreted as the proportion of information that should be allowed to pass through the gate. The input gate, denoted as IT(T)/sub, controls how much of the new input information should be stored in the memory cell. It takes as input the current input X(T)/sub and the previous hidden state HT(T)(1)/sub and outputs a value between 0 and 1 for each element of the cell state. The forget gate, denoted as FE(T)/sub, controls how much of the previous cell state C(T)(1)/sub should be forgotten. It also takes as input the current input X(T)/sub and the previous hidden state HT(T)(1)/sub and outputs a value between 0 and 1 for each element of the cell state. The output gate, denoted as OE(T)/sub, controls how much of the cell state should be outputted to the hidden state HT(T)/sub. It takes as input the current input X(T)/sub and the previous hidden state HT(T)(1)/sub and outputs a value between 0 and 1 for each element of the cell state. The cell state C(T)/sub is updated based on the input gate, the forget gate, and a candidate cell state C(T)/sub. The candidate cell state is computed similarly to the hidden state in a basic RNN, using the current input X(T)/sub and the previous hidden state HT(T)(1)/sub. The hidden state HT(T)/sub is then computed based on the output gate and the updated cell state C(T)/sub. The gating mechanisms in LSTMs allow the network to selectively remember or forget information over time. This enables LSTMs to learn long-range dependencies more effectively than basic RNNs. The gates also help to mitigate the vanishing gradient problem by providing a more direct path for gradients to flow during backpropagation. Gated recurrent units, GRUs. Simplified gating for efficient learning. Gated recurrent units, GRUs, are another type of recurrent neural network, RNN, architecture that, like LSTMs, uses gating mechanisms to control the flow of information and learn long-range dependencies. GRUs were introduced by Kyung-Hyun Cho and colleagues in 2014 as a simpler alternative to LSTMs. They have fewer parameters and are computationally more efficient while often achieving comparable performance. A GRU cell has two main gates, the update gate and the reset gate. The update gate, denoted as Z sub T slash sub, controls how much of the previous hidden state H sub T1 slash sub should be retained and how much of the new candidate hidden state H sub T slash sub should be incorporated. It takes as input the current input X sub T slash sub and the previous hidden state H sub T1 slash sub and outputs a value between 0 and 1 for each element of the hidden state. The reset gate, denoted as R sub T slash sub, controls how much of the previous hidden state should be ignored when computing the candidate hidden state H sub T slash sub. It also takes as input the current input X sub T slash sub and the previous hidden state H sub T1 slash sub and outputs a value between 0 and 1 for each element of the hidden state. The candidate hidden state H sub T slash sub is computed similarly to the hidden state in a basic RNN, using the current input X sub T slash sub and the previous hidden state H sub T1 slash sub, but with the reset gate modulating the contribution of the previous hidden state. The hidden state H sub T slash sub is then updated as a linear interpolation between the previous hidden state H sub T1 slash sub and the candidate hidden state H sub T slash sub, controlled by the update gate Z sub T slash sub. GRUs have a simpler architecture compared to LSTMs, with only 2 gates instead of 3 and no separate memory cell. This makes them computationally more efficient and easier to implement. Despite their simplicity, GRUs have been shown to perform similarly to LSTMs on many tasks involving sequential data. They have been successfully applied to various applications, including machine translation, speech recognition, and music generation. One of the key differences between GRUs and LSTMs is that GRUs do not have a separate memory cell. Instead, they use the hidden state to store and propagate information over time. This can make GRUs more prone to forgetting information compared to LSTMs, which have an explicit mechanism for preserving information in the memory cell. However, in practice, GRUs often perform just as well as LSTMs, and their simpler architecture can make them a more attractive choice in some cases. The choice between GRUs and LSTMs often depends on the specific task and dataset. Some studies have suggested that LSTMs may perform better on tasks that require learning very long-range dependencies, while GRUs may be sufficient for tasks with shorter dependencies. In practice, it is often a good idea to try both architectures and compare their performance using cross-validation. Both LSTMs and GRUs have significantly advanced the field of deep learning for sequential data. They have enabled the development of state-of-the-art models for a wide range of applications and have become essential tools for researchers and practitioners working with sequential data. Bidirectional RNNs, capturing context from both direction standard recurrent neural networks, RNNs, including LSTMs and GRUs, process sequential data in a single direction, typically from left to right. At each time step, they update their hidden state based on the current input and the previous hidden state. This means that the hidden state at a given time step only contains information about the past inputs in the sequence. However, in many applications, it can be beneficial to consider both past and future context when making predictions. Bidirectional RNNs, BRNNs, are a type of RNN architecture that addresses this limitation by processing the input sequence in both directions. A BRNN consists of 2 separate RNNs, one that processes the sequence from left to right, the forward RNN, and another that processes the sequence from right to left, the backward RNN. At each time step, the forward RNN computes a hidden state based on the current input and the previous hidden state, just like a standard RNN. The backward RNN, on the other hand, computes a hidden state based on the current input and the future hidden state, effectively processing the sequence in reverse. The outputs of the forward and backward RNNs at each time step are then concatenated or combined in some other way to produce the final output for that time step. BRNNs have been successfully applied to various tasks where considering both past and future context is beneficial. In natural language processing, BRNNs have been used for part-of-speech tagging, named entity recognition, and machine translation. For example, when predicting the part of speech of a word in a sentence, it can be helpful to consider both the words that come before it and the words that come after it. In speech recognition, BRNNs can improve the accuracy of phoneme classification by taking into account both past and future acoustic frames. This can help to disambiguate phonemes that sound similar but have different meanings depending on their context. BRNNs can be combined with other advanced RNN architectures, such as LSTMs and GRUs, to further improve their performance. Bidirectional LSTMs and GRUs use LSTM and GRU cells, respectively, in both the forward and backward passes. This allows them to learn long-range dependencies in both directions. One limitation of BRNNs is that they require the entire input sequence to be available before processing can begin. This makes them unsuitable for real-time applications where the input sequence is received incrementally. However, in many offline applications, such as text processing and video analysis, this is not a major constraint. Another consideration when using BRNNs is the increased computational cost compared to unidirectional RNNs. Since BRNNs process the input sequence in both directions, they require roughly twice the amount of computation. However, the improved performance often justifies the additional cost. Despite these considerations, BRNNs have proven to be a powerful tool for modeling sequential data. Sequence-to-sequence models, mapping input sequences to output sequences sequence-to-sequence, seq-to-seq, models are a type of neural network architecture that is designed to map an input sequence to an output sequence, where the input and output sequences can have different lengths. Seq-to-seq models have been particularly successful in tasks such as machine translation, text summarization, and speech recognition. The basic seq-to-seq model consists of two main components, an encoder and a decoder. Both the encoder and the decoder are typically implemented using recurrent neural networks, RNNs, such as LSTMs or GRUs. The encoder processes the input sequence one element at a time and updates its hidden state at each time step. The final hidden state of the encoder, often referred to as the context vector or thought vector, is a fixed-length representation that summarizes the entire input sequence. The decoder then takes this context vector as its initial hidden state and generates the output sequence one element at a time. At each time step, the decoder produces an output element and updates its hidden state based on the previous output and the context vector. In machine translation, for example, the input sequence is a sentence in the source language, and the output sequence is the corresponding translation in the target language. The encoder processes the source sentence and produces a context vector that captures its meaning. The decoder then generates the target sentence based on this context vector. One of the key challenges in seq-to-seq models is how to effectively transfer information from the encoder to the decoder. The context vector needs to capture all the relevant information from the input sequence that is necessary to generate the output sequence. This can be particularly difficult when the input sequence is long. Attention mechanisms have been introduced to address this challenge. Attention allows the decoder to focus on different parts of the input sequence at each time step when generating the output sequence. Instead of relying solely on the final hidden state of the encoder, the decoder has access to all the hidden states of the encoder. At each time step, the decoder computes attention weights that determine how much attention to pay to each of the encoder hidden states. These attention weights are typically computed using a small neural network that takes as input the current hidden state of the decoder and each of the encoder hidden states. The attention weights are then used to compute a weighted sum of the encoder hidden states, which is used as an additional input to the decoder at that time step. Attention mechanisms have significantly improved the performance of seek-to-seek models, particularly for long sequences. They allow the decoder to selectively focus on the most relevant parts of the input sequence when generating each element of the output sequence. This has led to state-of-the-art results in various applications, including machine translation and text summarization. Applications of RNNs, leveraging sequential data across domains. Recurrent neural networks, RNNs, have demonstrated remarkable versatility and effectiveness across a wide range of applications involving sequential data. Their ability to capture temporal dependencies and learn from sequences of varying lengths has made them a powerful tool in various domains. In natural language processing, NLP, RNNs have been instrumental in advancing the state-of-the-art in numerous tasks. Language modeling, which involves predicting the next word in a sequence given the preceding words, is a fundamental task in NLP that has greatly benefited from RNNs. RNN-based language models have been used to improve speech recognition, machine translation, and text generation. Machine translation, the task of automatically translating text from one language to another, has been revolutionized by seek-to-seek models based on RNNs, particularly with the introduction of attention mechanisms. These models have achieved impressive results, significantly outperforming previous statistical machine translation systems. Text summarization, which involves generating a concise summary of a longer document, is another area where RNNs have shown promise. Seek-to-seek models with attention can be used to generate abstractive summaries, which may contain words and phrases that were not present in the original document. Sentiment analysis, the task of determining the emotional tone or opinion expressed in a piece of text, has also benefited from RNNs. By processing text sequentially, RNNs can capture the contextual information necessary to accurately classify the sentiment of a sentence or document. In speech recognition, RNNs have been used to develop end-to-end models that directly transcribe spoken language into text. Bidirectional RNNs, which process the audio signal in both directions, have been particularly effective in capturing the context necessary for accurate transcription. RNNs have also been applied to time series analysis, which involves analyzing and forecasting data that is collected over time. Applications include stock price prediction, weather forecasting, and anomaly detection in industrial processes. In the field of bioinformatics, RNNs have been used to model and analyze biological sequences, such as DNA and protein sequences. They can be used to predict protein structure, identify functional regions in DNA, and classify different types of RNA. Beyond these examples, RNNs have been applied to many other domains, including video analysis, music generation, and robotics. Their ability to learn from sequential data makes them a powerful tool for a wide range of problems where temporal dependencies are important. As research on RNNs continues to advance, we can expect to see even more innovative applications of these models in the years to come. Lesson 5. Autoencoders and Generative Models. Introduction to autoencoders. Autoencoders are a type of neural network that is trained to reconstruct its input data. They are unsupervised learning models, meaning they do not require labeled data for training. The primary goal of an autoencoder is to learn a compressed, efficient representation of the input data, also known as a latent representation or code. This is achieved by passing the input data through an encoder network, which maps the input to the latent space, and then through a decoder network, which maps the latent representation back to the original input space. The autoencoder is trained to minimize the difference between the original input and the reconstructed output, typically using a loss function such as mean squared error or cross-entropy. The encoder and decoder are usually implemented using neural networks, such as fully connected networks or convolutional neural networks, depending on the type of data being processed. The latent representation learned by the autoencoder can be used for various purposes, including dimensionality reduction, feature extraction, and anomaly detection. By forcing the input data to be compressed into a lower-dimensional latent space and then reconstructed, the autoencoder learns to capture the most salient features of the data. Autoencoders can be seen as a form of nonlinear principal component analysis, PCA. While PCA can only learn linear transformations of the data, autoencoders can learn complex, nonlinear mappings. This allows them to capture more intricate patterns and relationships in the data. One of the key characteristics of autoencoders is that they are data-specific, meaning that they are only able to compress data that is similar to the data they were trained on. An autoencoder trained on images of faces, for example, would not be effective at compressing images of landscapes. Despite their simplicity, autoencoders have proven to be a powerful tool for unsupervised learning and have been applied to a wide range of tasks. They have also served as a building block for more complex generative models, such as variational autoencoders, VAEs, and generative adversarial networks, GANs. Research on autoencoders is ongoing, with new architectures and training techniques being developed to improve their performance and expand their capabilities. Autoencoders have become an essential part of the deep learning toolkit and continue to be an active area of research. Their ability to learn efficient representations of data has made them useful in various applications. Autoencoder architecture, encoder, decoder, and latent space. The architecture of an autoencoder consists of three main components: an encoder, a decoder, and a latent space. The encoder is a neural network that takes the input data and maps it to a lower-dimensional representation in the latent space. This process can be thought of as compressing the input data into a more compact form. The encoder typically consists of multiple layers, with each layer progressively reducing the dimensionality of the data. The decoder is another neural network that takes the latent representation as input and maps it back to the original input space. The goal of the decoder is to reconstruct the original input data from the compressed latent representation. Like the encoder, the decoder typically consists of multiple layers, but in this case, each layer progressively increases the dimensionality of the data until it matches the original input size. The latent space is the lower dimensional space where the compressed representation of the input data resides. The dimensionality of the latent space is a hyperparameter that is typically chosen to be smaller than the dimensionality of the input data. This forces the autoencoder to learn a compressed representation that captures the most important features of the data. The latent representation can be thought of as a code that encodes the essential information about the input data. The encoder and decoder can be implemented using various types of neural networks, depending on the nature of the input data. For image data, convolutional neural networks, CNNs, are often used for both the encoder and decoder. The encoder uses convolutional and pooling layers to progressively reduce the spatial dimensions of the input image and extract hierarchical features. The decoder uses upsampling and convolutional layers to reconstruct the image from the latent representation. For sequential data, recurrent neural networks, RNNs, such as LSTMs or GRUs, can be used. The choice of activation functions in the encoder and decoder can also impact the performance of the autoencoder. Common choices include ReLU, sigmoid, and tan. The specific architecture of the encoder and decoder, including the number of layers, the number of neurons or filters in each layer, and the activation functions, are hyperparameters that can be tuned to optimize the performance of the autoencoder for a given task and dataset. During training, the autoencoder is presented with input data, which is passed through the encoder to obtain the latent representation. This latent representation is then passed through the decoder to produce a reconstructed output. The difference between the original input and the reconstructed output is measured using a loss function, such as mean squared error for continuous data or cross-entropy for categorical data. The gradients of the loss function with respect to the network's weights are computed using backpropagation, and the weights are updated using an optimization algorithm, such as stochastic gradient descent, SGD, or ADAM. By iteratively updating the weights to minimize the reconstruction loss, the autoencoder learns to encode the input data into a compressed latent representation and decode it back to the original input space. Types of autoencoders: variations for different tasks and data. Several variations of autoencoders have been developed to address specific tasks or types of data. Undercomplete autoencoders are the most basic type, where the dimensionality of the latent space is smaller than the dimensionality of the input data. This forces the autoencoder to learn a compressed representation of the data, capturing the most important features. Undercomplete autoencoders are often used for dimensionality reduction and feature extraction. Sparse autoencoders introduce a sparsity constraint on the latent representation. In addition to minimizing the reconstruction loss, a penalty term is added to the loss function that encourages the latent representation to have only a small number of active neurons or units. This can be achieved using L1 regularization or by adding a term that measures the divergence between the average activation of each latent unit and a target sparsity level. Sparse autoencoders can learn more robust and interpretable features compared to undercomplete autoencoders. Denoising autoencoders are trained to reconstruct the original input from a corrupted version of the input. Typically, noise is added to the input data, such as by randomly setting some pixel values to 0 in an image or masking some words in a text document. The autoencoder is then trained to reconstruct the original, uncorrupted input from the noisy version. This forces the autoencoder to learn features that are robust to noise and to capture the underlying structure of the data. Denoising autoencoders have been shown to learn more useful representations than standard autoencoders and can be used for pre-training deep networks. Contractive autoencoders add a penalty term to the loss function that encourages the learned representation to be robust to small perturbations in the input. This penalty term is typically the Frobenius norm of the Jacobian matrix of the encoder activations with respect to the input. By minimizing this penalty, the autoencoder learns to contract the input space around the training data points, making the learned representation more stable and less sensitive to small changes in the input. Variational autoencoders, VAEs, are a generative type of autoencoder that introduces a probabilistic twist to the latent representation. Instead of encoding the input as a single point in the latent space, VAEs encode the input as a distribution over the latent space, typically a Gaussian distribution. This allows VAEs to generate new data samples by sampling from the learned latent distribution and passing the samples through the decoder. VAEs have become a popular tool for generative modeling and have been applied to various domains, including image generation, text generation, and music generation. These are just a few examples of the different types of autoencoders that have been developed. Applications of autoencoders, dimensionality reduction, anomaly detection, and more. Autoencoders have found applications in a wide range of domains, leveraging their ability to learn efficient representations of data. One of the primary applications of autoencoders is dimensionality reduction. By learning a compressed representation of the input data in a lower-dimensional latent space, autoencoders can effectively reduce the dimensionality of the data while preserving the most important information. This can be useful for visualizing high-dimensional data, as well as for speeding up subsequent processing steps that may be computationally expensive on the original high-dimensional data. Autoencoders can also be used for feature extraction. The latent representation learned by an autoencoder can serve as a new set of features that capture the essential characteristics of the input data. These features can then be used as input to other machine learning models, such as classifiers or regressors. In some cases, the features learned by autoencoders have been shown to outperform hand-engineered features, leading to improved performance on downstream tasks. Anomaly detection is another area where autoencoders have proven useful. Anomalies, also known as outliers, are data points that deviate significantly from the normal patterns in the data. Autoencoders can be trained on a dataset consisting only of normal data points. During inference, the reconstruction error of the autoencoder can be used as an anomaly score. Data points that are poorly reconstructed by the autoencoder, resulting in a high reconstruction error, are likely to be anomalies. This approach has been applied to various domains, such as fraud detection, fault detection in industrial processes, and intrusion detection in computer networks. Autoencoders can also be used for denoising data. As mentioned earlier, denoising autoencoders are trained to reconstruct the original input from a corrupted version. This capability can be used to remove noise from real-world data, such as images or audio recordings. By training a denoising autoencoder on a dataset of noisy inputs and their corresponding clean versions, the autoencoder learns to map from the noisy space to the clean space. During inference, the trained autoencoder can be used to denoise new, unseen noisy data. In the field of information retrieval, autoencoders have been used to learn compact representations of documents or images that can be used for efficient similarity search. By mapping documents or images to a lower dimensional latent space, the similarity between items can be computed more efficiently. This can enable faster and more scalable search systems. Autoencoders have also been used as a pre-training step for deep neural networks. In this approach, an autoencoder is first trained on unlabeled data to learn a good initialization for the weights of the network. The encoder part of the autoencoder is then used as the initial layers of a deep neural network, which is subsequently fine-tuned on labeled data for a specific task, such as classification. This pre-training step can help to improve the performance and convergence speed of the deep network, especially when the amount of labeled data is limited. These are just a few examples of the many applications of autoencoders. Generative models. Creating new data from learned distributions. Generative models are a class of machine learning models that learn to generate new data samples that are similar to the training data. Unlike discriminative models, which learn to distinguish between different classes or predict a target variable given the input data, generative models learn the underlying probability distribution of the data itself. This allows them to create new data instances that resemble the training data, capturing its statistical properties and structure. Generative models have gained significant attention in recent years due to their ability to create realistic and diverse data samples, such as images, text, and audio. One of the key advantages of generative models is that they can learn from unlabeled data. This makes them particularly useful in domains where labeled data is scarce or expensive to obtain. By learning the underlying data distribution, generative models can uncover the hidden factors and structures that govern the data generation process. Generative models can be used for various tasks, including data augmentation, image and painting, style transfer, and data synthesis. They can also be used to gain insights into the data distribution and to identify potential biases or gaps in the training data. There are several types of generative models, including variational autoencoders, VAEs, generative adversarial networks, GANs, and autoregressive models. Each type has its own strengths and weaknesses and is suited for different types of data and tasks. VAEs, as mentioned earlier, are a type of generative model that combines the autoencoder architecture with probabilistic modeling. They learn a probabilistic mapping from the input space to a latent space and back, allowing them to generate new data samples by sampling from the learned latent distribution and passing the samples through the decoder. GANs, on the other hand, take a different approach to generative modeling. They involve training two networks, a generator and a discriminator, in an adversarial manner. The generator learns to create new data samples that are similar to the training data, while the discriminator learns to distinguish between real data samples and generated samples. The two networks are trained jointly, with the generator trying to fool the discriminator and the discriminator trying to correctly classify the samples. Through this adversarial process, the generator learns to produce increasingly realistic data samples. Autoregressive models are another type of generative model that models the conditional probability distribution of each element in a sequence given the previous elements. Examples of autoregressive models include PixelRNN and PixelCNN for image generation and WaveNet for audio generation. These models generate data samples one element at a time, conditioning each element on the previously generated elements. Generative models have achieved impressive results in various domains, generating high-quality and diverse data samples. Variational autoencoders, VAEs. Probabilistic latent variable models. Variational autoencoders, VAEs, are a powerful class of generative models that combine the autoencoder architecture with probabilistic modeling. They were introduced by Kingma and Welling in 2013 and have since become one of the most popular and widely used generative models. VAEs learn a probabilistic mapping from the input data space to a latent space and back, allowing them to generate new data samples by sampling from the learned latent distribution and passing the samples through the decoder. The key idea behind VAEs is to model the latent representation as a random variable that follows a specific probability distribution, typically a multivariate Gaussian distribution. Instead of encoding the input as a single point in the latent space, as in standard autoencoders, VAEs encode the input as a distribution over the latent space. The encoder network in a VAE outputs the parameters of this distribution, such as the mean and variance of a Gaussian. During training, a sample is drawn from this latent distribution and passed through the decoder to generate a reconstructed output. The loss function used to train VAEs consists of two terms, a reconstruction loss and a regularization term. The reconstruction loss measures the difference between the input data and the reconstructed output, similar to standard autoencoders. The regularization term, typically implemented as the Kullback-Leibler (KL) divergence between the learned latent distribution and a prior distribution, usually a standard normal distribution, encourages the latent distribution to be close to the prior. This regularization term is crucial for ensuring that the learned latent space has desirable properties, such as continuity and completeness. Continuity means that points that are close to each other in the latent space should correspond to similar data samples in the input space. Completeness means that any point sampled from the prior distribution should correspond to a meaningful data sample when passed through the decoder. The KL divergence term acts as a regularizer, preventing the encoder from simply memorizing the input data and encouraging it to learn a more general and useful latent representation. It also allows for approximate inference of the posterior distribution over the latent variables given the input data, which is intractable to compute exactly in most cases. To optimize the VAE objective function, which involves both the reconstruction loss and the KL divergence term, a technique called the reparameterization trick is used. This trick allows for the computation of gradients with respect to the parameters of the encoder network, enabling end-to-end training using backpropagation. Once trained, VAEs can be used to generate new data samples by sampling from the prior distribution over the latent space and passing the samples through the decoder. The decoder then maps these latent samples to the data space, producing new data instances that are similar to the training data. VAEs have been successfully applied to various types of data, including images, text, and audio. Generative adversarial networks, GAN's adversarial training for realistic data generation. Generative adversarial networks, GANs, are a class of generative models that have gained immense popularity since their introduction by Goodfellow et al. In 2014. GANs take a fundamentally different approach to generative modeling compared to VAEs. Instead of explicitly modeling the probability distribution of the data, GANs learn to generate new data samples through an adversarial training process involving two neural networks, a generator and a discriminator. The generator network takes a random noise vector as input and generates a data sample, such as an image or a text sequence. The discriminator network takes a data sample as input, which can be either a real sample from the training data or a generated sample from the generator, and outputs a probability that the sample is real rather than generated. The two networks are trained jointly in an adversarial manner, with the generator trying to produce samples that can fool the discriminator into classifying them as real, and the discriminator trying to correctly distinguish between real and generated samples. This adversarial training process can be formulated as a two-player minimax game, where the generator and discriminator have competing objectives. The generator aims to minimize the probability that the discriminator correctly classifies its generated samples, while the discriminator aims to maximize the probability of correctly classifying both real and generated samples. During training, the generator and discriminator are updated alternately. In each iteration, the discriminator is trained for one or more steps to improve its ability to distinguish between real and generated samples, while the generator's parameters are held fixed. Then, the generator is trained for one or more steps to improve its ability to generate samples that can fool the discriminator, while the discriminator's parameters are held fixed. The loss function used to train the discriminator is typically the binary cross-entropy loss, which measures the difference between the predicted probabilities and the true labels, real or generated. The loss function used to train the generator is designed to encourage the generator to produce samples that the discriminator classifies as real. One common choice for the generator loss is the negative log likelihood of the discriminator's output for generated samples. Minimizing this loss is equivalent to maximizing the probability that the discriminator classifies generated samples as real. The training process in GANs can be challenging and unstable. It requires careful balancing of the generator and discriminator's learning rates and capacities. If the discriminator is too strong, the generator may not be able to learn effectively. If the generator is too strong, it may produce samples that exploit weaknesses in the discriminator but do not correspond to realistic data. Despite these challenges, GANs have achieved impressive results in generating high-quality and diverse data samples, particularly in the domain of image generation. GAN variants and applications, improving stability and expanding use cases. Since the introduction of the original GAN framework, numerous variants have been proposed to improve the stability of training, the quality of generated samples, and the applicability of GANs to various tasks. One of the key challenges in training GANs is a problem known as mode collapse. Mode collapse occurs when the generator learns to produce only a limited variety of samples, failing to capture the full diversity of the training data distribution. This can happen when the generator finds a small set of samples that can consistently fool the discriminator, even if these samples do not represent the full range of the data distribution. Several techniques have been proposed to address mode collapse, including modifying the loss function, using different network architectures, and introducing diversity-promoting mechanisms. Wasserstein GAN, WGN, is a notable GAN variant that uses the Wasserstein distance, also known as the Earth mover's distance, to measure the difference between the distribution of real data and the distribution of generated data. WGN has been shown to improve the stability of training and reduce mode collapse compared to the original GAN formulation. It also provides a more meaningful loss metric that correlates with the quality of generated samples. Conditional GANs, CGANs, extend the basic GAN framework by conditioning both the generator and the discriminator on some additional information, such as class labels or text descriptions. This allows for more control over the generated samples and enables the generation of samples with specific attributes. For example, a CGAN can be trained to generate images of handwritten digits, conditioned on the digit label. This allows the user to specify which digit they want the generator to produce. Deep convolutional GANs, GANs, were one of the first GAN variants to successfully apply convolutional neural networks to both the generator and the discriminator for image generation. GANs introduced architectural guidelines for stable training of GANs, such as using strided convolutions instead of pooling layers and using batch normalization in both the generator and the discriminator. These guidelines have been widely adopted in subsequent GAN research. Progressive growing of GANs, GANs, is a technique that involves training the generator and discriminator incrementally, starting with low-resolution images and progressively increasing the resolution during training. This approach has been shown to improve the quality and stability of high-resolution image generation. StyleGAN is a state-of-the-art GAN architecture that focuses on controlling the style of generated images. It introduces a mapping network that transforms the input noise vector into an intermediate latent space that controls the style of the generated image at different scales. StyleGAN has achieved impressive results in generating highly realistic and diverse images, particularly of human faces. GANs have been applied to a wide range of tasks beyond image generation. In image-to-image translation, GANs are used to learn a mapping from one image domain to another, such as translating sketches to realistic images or converting daytime images to nighttime images. CycleGAN is a popular approach for unpaired image-to-image translation, where the training data does not consist of paired examples from the two domains. In text generation, GANs have been used to generate realistic sentences and paragraphs. However, training GANs for text generation is challenging due to the discrete nature of text and the difficulty of backpropagating gradients through discrete variables. GANs have also been applied to other types of data, such as audio, video, and 3D models. Autoregressive models, sequential data generation. Autoregressive models are a class of generative models that generate data sequentially, one element at a time, conditioned on the previously generated elements. They model the conditional probability distribution of each element in a sequence given the preceding elements. Autoregressive models have been successfully applied to various types of sequential data, including text, audio, and images. In the context of text generation, autoregressive models are often implemented using recurrent neural networks, RNNs, such as LSTMs or GRUs. At each time step, the RNN takes as input the previously generated word or character and its current hidden state, and outputs a probability distribution over the vocabulary for the next word or character. The next element in the sequence is then sampled from this distribution and fed back into the RNN as input for the next time step. This process continues until an end-of-sequence token is generated or a maximum sequence length is reached. Transformer-based models, such as GPT, Generative Pre-trained Transformer, and BERT, bidirectional encoder representations from transformers, have recently become popular for autoregressive language modeling. These models use the self-attention mechanism to capture long-range dependencies in the input sequence and have achieved state-of-the-art results on various natural language processing tasks. For image generation, autoregressive models typically generate images pixel by pixel, either in a raster scan order, from top left to bottom right, or using a more sophisticated ordering. PixelRNN and PixelCNN are two examples of autoregressive models for image generation that use RNNs and CNNs, respectively, to model the conditional distribution of each pixel given the previously generated pixels. PixelCNN, for example, uses masked convolutions to ensure that each pixel is only conditioned on previously generated pixels. WaveNet is an autoregressive model for audio generation that operates directly on raw audio waveforms. It uses dilated convolutions to capture long-range dependencies in the audio signal and has achieved impressive results in generating realistic speech and music. One advantage of autoregressive models is that they provide a tractable way to compute the likelihood of the generated data. This makes them suitable for tasks where it is important to be able to evaluate the probability of a given sequence, such as in language modeling or speech recognition. However, autoregressive models can be slow to generate data, as each element in the sequence must be generated sequentially. This is in contrast to GANs and VAEs, which can generate all elements of a data sample in parallel. Recent research has explored hybrid approaches that combine the strengths of autoregressive models with other types of generative models. For example, the VQ-VAE2 model combines a VAE with an autoregressive prior over the latent codes to generate high-quality images. Autoregressive models are a powerful class of generative models that have achieved state-of-the-art results in various domains. Their ability to model complex sequential dependencies makes them particularly well-suited for tasks involving sequential data generation. Lesson 6, Reinforcement Learning Fundamentals. Introduction to Reinforcement Learning. Reinforcement learning, RL, is a branch of machine learning that deals with how an agent can learn to make optimal decisions in an environment to maximize a cumulative reward. Unlike supervised learning, where the agent learns from labeled examples, or unsupervised learning, where the agent learns patterns from unlabeled data, in RL, the agent learns through trial and error by interacting with an environment. The agent takes actions in the environment, observes the resulting state and reward, and learns to choose actions that lead to higher cumulative rewards over time. The environment is typically modeled as a Markov decision process, MDP, which consists of a set of states, a set of actions, a transition function that defines the probability of moving from one state to another given an action, and a reward function that assigns a scalar reward to each state or state-action pair. The agent's goal is to learn a policy, which is a mapping from states to actions, that maximizes the expected cumulative reward over time. This is often formalized as maximizing the expected return, which is the sum of discounted future rewards. The discount factor, typically denoted by gamma, is a value between 0 and 1 that determines the importance of future rewards relative to immediate rewards. RL algorithms can be broadly categorized into two types, model-based and model-free. Model-based algorithms learn a model of the environment, including the transition function and the reward function, and use this model to plan and make decisions. Model-free algorithms, on the other hand, learn directly from experience without explicitly learning a model of the environment. Q-learning is a popular model-free RL algorithm that learns an action value function, denoted by Q, S, A, which represents the expected return of taking action A in state S and following the optimal policy thereafter. Policy gradient methods are another class of model-free RL algorithms that directly learn a parameterized policy, typically represented by a neural network. The policy is updated by following the gradient of the expected return with respect to the policy parameters. Reinforcement learning has been successfully applied to a wide range of domains, including game playing, robotics, control systems, and recommendation systems. In game playing, RL agents have achieved superhuman performance in games such as Go, chess, and video games. In robotics, RL can be used to learn complex motor skills and control policies for robots. In control systems, RL can optimize the performance of systems such as power grids and traffic networks. Despite its successes, reinforcement learning also faces several challenges. One challenge is the exploration-exploitation dilemma, where the agent must balance between exploring new actions and states to learn more about the environment and exploiting its current knowledge to maximize immediate rewards. Another challenge is the problem of sparse rewards, where the agent receives non-zero rewards only infrequently, making it difficult to learn which actions are responsible for the rewards. Markov decision processes, MDPs. Formalizing the RL problem. Markov decision processes, MDPs, provide a mathematical framework for modeling decision-making problems in which an agent interacts with an environment over a sequence of time steps. MDPs are the standard formalism used in reinforcement learning to describe the interaction between an agent and its environment. An MDP is defined by a tuple, S, A, P, R, gamma, where S is a set of states representing the possible situations the agent can encounter in the environment. A is a set of actions that the agent can take. P is a transition function that defines the probability of transitioning from one state to another given an action. It is often denoted as P, SS, A, which represents the probability of transitioning to state S from state S after taking action A. R is a reward function that assigns a scalar reward to each state or state action pair. It can be denoted as RS or R, S, A, representing the immediate reward received in state S or after taking action A in state S, respectively. Gamma, gamma, is a discount factor between 0 and 1 that determines the present value of future rewards. It represents the idea that immediate rewards are generally more valuable than rewards received in the distant future. The key property of an MDP is the Markov property, which states that the future is independent of the past given the present. In other words, the next state and reward depend only on the current state and action, and not on the history of previous states and actions. This property simplifies the analysis and allows for the development of efficient algorithms for solving MDPs. The agent's goal in an MDP is to find an optimal policy, denoted by pi asterisk, which is a mapping from states to actions that maximizes the expected cumulative reward over time. The optimal policy specifies which action the agent should take in each state to achieve the highest long-term reward. The value function is an important concept in MDPs. It represents the expected return starting from a given state and following a particular policy. The state value function, denoted by v sup a pi slash sup s, is the expected return starting from state s and following policy pi. The action value function, also known as the q function and denoted by q sup a pi slash sup s a, is the expected return starting from state s, taking action a, and following policy pi thereafter. The optimal value function, denoted by v** s, is the maximum expected return achievable from state S, following the optimal policy pi*. Similarly, the optimal action value function, denoted by q** s, a, is the maximum expected return achievable from state S after taking action A. Solving an MDP involves finding the optimal policy, which can be derived from the optimal value function or the optimal action value function. Dynamic programming algorithms, such as value iteration and policy iteration, can be used to find the optimal value function and policy when the MDP model, transition function and reward function, is known. Value functions and policy functions, evaluating states and actions. Value functions and policy functions are central concepts in reinforcement learning. They provide a way to quantify the desirability of states and actions and to define the agent's behavior in the environment. A value function measures the expected return, or cumulative discounted reward, that an agent can expect to receive from a given state or state-action pair, following a particular policy. The state value function, denoted by v sup pi/sup s, represents the expected return starting from state S and following policy pi. It can be defined recursively using the Bellman equation, v sup pi/sup s equals e r sub t plus 1/sub plus gamma v sup pi/sup s sub t plus 1/sub s sub t/sub equals s, where a sub t plus 1/sub is the immediate reward received after transitioning from state S sub t/sub to state S sub t plus 1/sub. Gamma is the discount factor, and the expectation is taken over possible next states and rewards, given that the agent follows policy pi. The action value function, also known as the Q function and denoted by q sup pi/sup s, a, represents the expected return starting from state S, taking action A, and following policy pi thereafter. It can also be defined recursively using the Bellman equation, q sup pi/sup s, a, equals e r sub t plus 1/sub plus gamma q sup pi/sup s sub t plus 1/sub a sub t plus 1/sub s sub t/sub equals s, a sub t/sub equals a, where a sub t plus 1/sub is the action taken in state S sub t plus 1/sub according to policy pi. The optimal value function, denoted by v** s, represents the maximum expected return achievable from state S, following the optimal policy pi*. Similarly, the optimal action value function, denoted by q** s, a, represents the maximum expected return achievable from state S after taking action A. The optimal value function and optimal action value function satisfy the Bellman optimality equations, v** s equals max sub a/sub e, r sub t plus 1/sub plus gamma v** s sub t plus 1/sub s sub t/sub equals s, a sub t/sub equals a, and q** s, a, equals e, r sub t plus 1/sub, plus gamma max sub a/sub q** s sub t plus 1/sub, s sub t/sub equals s, a sub t/sub equals a. A policy function, denoted by pi, as, defines the agent's behavior by mapping states to actions. It can be deterministic, in which case it specifies a single action for each state, or stochastic, in which case it defines a probability distribution over actions for each state. The goal of reinforcement learning is to find an optimal policy that maximizes the expected cumulative reward. The optimal policy can be derived from the optimal value function or the optimal action value function. For example, a greedy policy with respect to the optimal action value function would choose the action with the highest Q value in each state, pi** s equals argmax sub a/sub q** s, a. Value functions and policy functions are closely related. Value functions provide a way to evaluate the goodness of a policy, while policy functions define how the agent should act to achieve high value. Many reinforcement learning algorithms, such as Q-learning and SURSA, are based on learning value functions, while others, such as policy gradient methods, directly learn policy functions. The choice between value-based and policy-based methods depends on the specific problem and the desired properties of the solution. Value-based methods are often more sample efficient, meaning they require fewer interactions with the environment to learn a good policy, but they can be less stable and may converge to suboptimal policies in some cases. Policy-based methods, on the other hand, can learn more complex policies and can handle continuous action spaces more naturally, but they often require more data and can be more difficult to tune. Q-learning, learning action values for optimal decision-making. Q-learning is a model-free, off-policy reinforcement learning algorithm that learns an action value function, Q, S, A, which represents the expected return of taking action A in state S and following the optimal policy thereafter. Q-learning is one of the most widely used and influential RL algorithms and has been successfully applied to various domains. The key idea behind Q-learning is to iteratively improve the estimate of the optimal action value function, Q** S, A, using the Bellman optimality equation. The Q-learning update rule is given by Q, S, A, Q, S, A, plus alpha, R plus gamma max sub A, slash sub Q, S, A, Q, S, A, where S is the current state, A is the action taken in state S, R is the immediate reward received after taking action, A in state S, S is the next state, A is the action that maximizes the Q value, and the next state S alpha is the learning rate, which determines the step size of the update. Gamma is the discount factor, which determines the importance of future rewards. The term inside the brackets, R plus gamma max sub A slash sub Q, S, Q, S, A, is known as the temporal difference, TD, error. It represents the difference between the current estimate of the Q value and the updated estimate based on the observed reward and the maximum Q value in the next state. Q-learning is an off-policy algorithm, which means that it learns the optimal policy independently of the agent's behavior policy. The agent can follow any policy to select actions during training, as long as all state action pairs are visited sufficiently often. This allows for the use of exploration strategies, such as epsilon greedy, where the agent takes a random action with probability epsilon and the action with the highest Q value with probability 1 epsilon. Q-learning is guaranteed to converge to the optimal action value function, Q** S, A, under certain conditions, such as the use of a tabular representation for the Q function, i.e., a table with one entry for each state action pair, and sufficient exploration of the state action space. However, in practice, Q-learning is often used with function approximation, such as neural networks, to represent the Q function. This allows Q-learning to be applied to problems with large or continuous state spaces, but it also introduces challenges related to convergence and stability. Deep Q networks, DQNs, are a popular extension of Q-learning that use a deep neural network to approximate the Q function. DQNs have achieved impressive results in playing Atari games and other domains with high-dimensional state spaces. To improve the stability of training, DQNs use techniques such as experience replay and target networks. Experience replay stores the agent's experiences in a replay buffer and samples many batches of experiences from the buffer to update the Q network. This breaks the correlations between consecutive updates and helps to stabilize learning. Target networks use a separate, slowly updated network to compute the target Q values in the update rule. This helps to reduce the oscillations and instability that can arise from updating the Q network using its own rapidly changing estimates. Q-learning and its variants have been widely used in various applications, including robotics, game playing, and control systems. They provide a powerful and flexible framework for learning optimal decision-making policies from experience. Deep Q networks, DQNs, combining Q-learning with deep neural networks. Deep Q networks, DQNs, are a significant advancement in reinforcement learning that combine the Q-learning algorithm with deep neural networks. DQNs were introduced by researchers at DeepMind in 2013 and achieved groundbreaking results in playing Atari games, surpassing human-level performance in many of them. This work demonstrated the power of combining deep learning with reinforcement learning and has since inspired much research in the field of deep reinforcement learning. In DQNs, a deep neural network is used to approximate the optimal action value function, Q** SA. The network takes the state S as input and outputs a vector of Q values, one for each possible action A. The use of a deep neural network allows DQNs to handle problems with high-dimensional state spaces, such as images, where traditional tabular Q-learning would be infeasible. The training of a DQN involves minimizing the temporal difference, TD, error, similar to Q-learning. However, instead of updating a table of Q values, the weights of the neural network are updated using backpropagation and an optimization algorithm such as stochastic gradient descent, SGD, or ADAM. One of the key challenges in training DQNs is the instability that can arise from using a nonlinear function approximator, such as a neural network, to estimate the Q function. Small changes in the Q values can lead to significant changes in the policy, which in turn can affect the distribution of states encountered during training. This can create a feedback loop that destabilizes learning. To address this issue, DQNs employ two main techniques: experience replay and target networks. Experience replay involves storing the agent's experiences in a replay buffer, which is a large memory that holds a collection of past transitions, SARs. During training, instead of updating the network using only the most recent transition, many batches of transitions are randomly sampled from the replay buffer. This breaks the correlations between consecutive updates, reduces the variance of the updates, and helps to stabilize learning. Target networks involve using a separate neural network to compute the target Q values in the update rule. The target network has the same architecture as the main Q network, but its weights are updated less frequently. Typically, the target network's weights are periodically copied from the main network's weights, or they are slowly updated towards the main network's weights using a soft update rule. The use of a target network helps to reduce the oscillations and instability that can arise from updating the Q network using its own rapidly changing estimates. The combination of these techniques, along with the use of deep neural networks, allows DQNs to learn effective policies in complex, high-dimensional environments. DQNs have been successfully applied not only to Atari games but also to other domains, such as robotics and control systems. Since the introduction of the original DQN, several improvements and extensions have been proposed. Double DQN addresses the problem of overestimation bias in Q-learning by decoupling the selection of the action from the evaluation of its value in the target. Prioritized experience replay biases the sampling of transitions from the replay buffer based on their TD error, giving more priority to transitions that are more surprising or informative. Dueling DQN uses a network architecture that separately estimates the state value function versus and the advantage function A, which represents the relative advantage of each action compared to the average action in a given state. These and other advancements have further improved the performance and stability of deep Q-learning. Policy gradient methods. Directly optimizing the policy gradient methods are a class of reinforcement learning algorithms that directly learn a parameterized policy, typically represented by a neural network. Unlike value-based methods like Q-learning, which learn an action value function and then derive a policy from it, policy gradient methods directly optimize the policy to maximize the expected return. The policy, denoted by pi sub theta slash sub as, is a function that maps states to actions, parameterized by a set of parameters theta. In the case of a neural network policy, theta represents the weights of the network. The policy can be either deterministic, in which case it outputs a single action for each state, or stochastic, in which case it outputs a probability distribution over actions for each state. The goal of policy gradient methods is to find the parameters theta that maximize the expected return, often denoted by J, theta. The expected return is the average return that the agent can expect to receive when following the policy pi sub theta slash sub, starting from some initial state distribution. Policy gradient methods work by directly computing the gradient of the expected return with respect to the policy parameters, nabla sub theta slash sub j, theta, and then updating the parameters in the direction of the gradient using an optimization algorithm like stochastic gradient descent. The key result that enables this approach is the policy gradient theorem, which provides an expression for the gradient of the expected return that can be estimated from experience without requiring knowledge of the environment's transition dynamics. One of the most widely used policy gradient algorithms is reinforce, also known as Monte Carlo policy gradient. Reinforce works by collecting a set of trajectories, sequences of states, actions, and rewards, by following the current policy pi sub theta slash sub. For each trajectory, it computes the return g sub t slash sub for each time step t, which is the sum of discounted future rewards from that time step onward. It then computes an estimate of the policy gradient using the formula, nabla sub theta slash sub j, theta, is almost equal to sigma sub t slash sub nabla sub theta slash sub log pi sub theta slash sub a sub t slash sub s sub t slash sub g sub t slash sub, where the sum is taken over all time steps in the trajectory, s sub t slash sub, where the sum is taken over all time steps in the trajectory, s sub t slash sub and a sub t slash sub are the state and action at time step t, and g sub t slash sub is the return from time step t. The policy parameters are then updated in the direction of the estimated gradient, theta theta plus alpha nabla sub theta slash sub j, theta, where alpha is the learning rate. Reinforce is an on-policy algorithm, meaning that it learns from trajectories generated by the current policy. This can lead to high variance in the gradient estimates, as the trajectories can vary significantly depending on the specific actions taken and the stochasticity of the environment. To reduce the variance of the gradient estimates, a baseline can be subtracted from the return g sub t slash sub. A common choice for the baseline is the state value function v s sub t slash sub, which represents the average return starting from state s sub t slash sub. This leads to the advantage function a s sub t slash sub, a sub t slash sub equals g sub t slash sub v s sub t slash sub, which represents how much better or worse the action a sub t slash sub is compared to the average action in state s sub t slash sub. Using the advantage function instead of the raw return can significantly reduce the variance of the gradient estimates and improve the stability of learning. Actor-critic methods combine policy gradient methods with value function approximation. They maintain two separate structures, an actor, which represents the policy and is updated using policy gradients, and a critic, which represents the value function and is used to evaluate the actions taken by the actor. The critic can be used to estimate the advantage function, which is then used to update the actor. Actor-critic methods can be more sample efficient than reinforce, as they can learn from each individual transition rather than requiring a complete trajectory. They can also be more stable, as the value function provides a more reliable estimate of the return than the Monte Carlo estimate used in reinforce. Proximal policy optimization, PPO, is a state-of-the-art policy gradient algorithm that has gained popularity due to its stability, sample efficiency, and ease of implementation. PPO introduces a clipped surrogate objective that prevents the policy from being updated too drastically at each iteration. This helps to avoid performance collapses that can occur when the policy changes too much, leading to a significant drop in performance. Policy gradient methods have been successfully applied to a wide range of problems, including continuous control tasks, robotics, and game playing. They offer several advantages over value-based methods, such as the ability to learn stochastic policies and to handle continuous action spaces more naturally. However, they can also be more challenging to tune and can suffer from high variance in the gradient estimates. Despite these challenges, policy gradient methods remain an active area of research, and new algorithms and techniques are constantly being developed to improve their performance and applicability. Actor-critic methods. Combining value and policy learning. Actor-critic methods are a class of reinforcement learning algorithms that combine the strengths of both value-based and policy-based methods. They maintain two separate structures, an actor, which represents the policy, and a critic, which represents the value function. The actor is responsible for selecting actions, while the critic evaluates the actions taken by the actor and provides feedback that is used to improve the policy. The basic idea behind actor-critic methods is to use the critic to estimate the value function, which can be either the state value function versus or the action value function Q, S, A, and then use this estimate to update the actor's policy. The critic is typically updated using temporal difference, TD, learning, similar to Q-learning or SIRSA. One common approach in actor-critic methods is to use the critic to estimate the advantage function, A, S, A, equals Q, S, A, versus, which represents the advantage of taking action A in state S compared to the average action in that state. The advantage function can be used in place of the return in the policy gradient update, as it reduces the variance of the gradient estimates and improves the stability of learning. The actor is updated by following the gradient of the expected return with respect to the policy parameters, using the advantage function as a weight for each action. The update rule for the actor can be written as theta theta plus alpha nabla sub theta slash sub log pi sub theta slash sub as a s a, where theta represents the policy parameters, alpha is the learning rate, and pi sub theta slash sub as is the probability of taking action A in state S under the current policy. Actor-critic methods can be either on policy or off policy. In on-policy methods, such as advantage actor-critic, A2C, and asynchronous advantage actor-critic, A3C, the actor and critic are updated using data collected from the current policy. In off-policy methods, such as deep deterministic policy gradient, DDPG, and soft actor-critic, SAC, the actor and critic can be updated using data collected from a different policy, often stored in a replay buffer. A2C and A3C are synchronous and asynchronous variants of the advantage actor-critic algorithm, respectively. A2C computes the policy gradient using a batch of trajectories collected from multiple parallel actors interacting with the environment. A3C, on the other hand, uses multiple parallel actors that interact with their own copy of the environment and asynchronously update a shared set of parameters. This asynchronous updating helps to decorrelate the updates and stabilize learning. DDPG is an off-policy actor-critic algorithm that is designed for continuous action spaces. It uses a deterministic policy, meaning that the actor outputs a single action for each state, rather than a probability distribution over actions. DDPG uses a target network for both the actor and the critic to improve stability, similar to the target network used in DQN. It also uses a replay buffer to store and sample experiences for updating the actor and critic networks. SAC is another off-policy actor-critic algorithm that incorporates entropy regularization into the objective function. The entropy of the policy is a measure of its randomness, and maximizing the entropy encourages the policy to explore more diverse actions. SAC has been shown to be more sample-efficient and robust than other actor-critic methods on a range of continuous control tasks. Actor-critic methods offer several advantages over purely value-based or policy-based methods. They can be more sample-efficient, as they can learn from each individual transition rather than requiring a complete trajectory. They can also be more stable, as the value function provides a more reliable estimate of the return than the Monte Carlo estimate used in policy gradient methods like reinforce. However, actor-critic methods can also be more complex to implement and tune, as they involve maintaining and updating two separate networks. They also require careful balancing of the learning rates and other hyperparameters of the actor and critic. Exploration-exploitation dilemma. Balancing learning and acting. The exploration-exploitation dilemma is a fundamental challenge in reinforcement learning that arises from the need to balance between exploring new actions and states to learn more about the environment and exploiting the current knowledge to maximize immediate rewards. When an agent starts learning in a new environment, it has limited knowledge about the consequences of its actions and the rewards associated with different states. To learn an effective policy, the agent needs to explore the environment, trying out different actions in different states to discover which ones lead to high rewards. However, if the agent only focuses on exploration, it may never exploit its current knowledge to actually achieve high cumulative rewards. On the other hand, if the agent only exploits its current knowledge, always choosing the action that it believes to be the best based on its current estimates, it may miss out on discovering better actions and states that it has not yet explored sufficiently. This can lead to the agent getting stuck in a suboptimal policy. The exploration-exploitation dilemma can be seen as a trade-off between learning and acting. Exploration is necessary for learning about the environment and discovering potentially better policies, while exploitation is necessary for achieving high rewards based on the current knowledge. Several strategies have been developed to address the exploration-exploitation dilemma in reinforcement learning. One of the simplest and most widely used strategies is epsilon-greedy exploration. In epsilon-greedy exploration, the agent chooses a random action with probability epsilon and the action with the highest estimated value, e.g., the highest Q value in Q-learning, with probability 1 epsilon. The value of epsilon is typically decreased over time, starting with a high value to encourage exploration in the early stages of learning and gradually reducing it to favor exploitation as the agent gains more knowledge about the environment. Another popular exploration strategy is Boltzmann exploration, also known as softmax exploration. In Boltzmann exploration, the agent chooses actions probabilistically based on their estimated values, with higher valued actions being more likely to be chosen. The probability of choosing action A in state S is given by P, A S, equals exp, Q, S, A, slash tau, slash sigma sub A, slash sub exp, Q, S, A, slash tau, where tau is a temperature parameter that controls the level of exploration. A high temperature makes the action probabilities more uniform, encouraging exploration, while a low temperature makes the agent more likely to choose the action with the highest estimated value. Upper confidence bound, UCB, is a more sophisticated exploration strategy that selects actions based on both their estimated value and the uncertainty of the estimates. UCB adds an exploration bonus to the estimated value of each action, where the bonus is proportional to the square root of the logarithm of the number of times the state has been visited divided by the number of times the action has been taken in that state. This encourages the agent to explore actions that have not been tried as often, especially in states that have been visited frequently. Other exploration strategies include Thompson sampling, which maintains a probability distribution over the value of each action and samples actions from this distribution, and intrinsic motivation, which rewards the agent for visiting novel or surprising states. The choice of exploration strategy can have a significant impact on the performance of a reinforcement learning agent. Different strategies may be more suitable for different types of environments and tasks. In recent years, there has been growing interest in developing more principled and efficient exploration methods, such as those based on information theory, Bayesian inference, and meta-learning. These advanced exploration methods aim to learn more efficient exploration strategies from data and to adapt the exploration strategy during learning based on the agent's experience. Applications of reinforcement learning, from games to robotics and beyond reinforcement learning, RL, has been successfully applied to a wide range of domains, demonstrating its versatility and power as a general framework for learning optimal decision-making. One of the most prominent application areas of RL is game playing. RL agents have achieved superhuman performance in various games, including board games like Go and chess, and video games like Atari and StarCraft. In 2016, AlphaGo, an RL agent developed by DeepMind, defeated the world champion in Go, a game that was previously considered to be extremely challenging for AI systems due to its large state space and complex strategic nature. AlphaGo combined deep neural networks with Monte Carlo tree search and learned from both expert human games and self-play. Its successor, AlphaGo Zero, learned to play Go from scratch, without any human data, and surpassed the performance of all previous versions of AlphaGo, including the one that defeated the world champion. Atari games have been a popular benchmark for RL algorithms since the introduction of Deep Q networks, DQNs. DQNs were able to learn to play a wide range of Atari games directly from pixel inputs, achieving human-level or even superhuman performance in many of them. This work demonstrated the potential of combining deep learning with reinforcement learning to solve complex, high-dimensional problems. In robotics, RL has been used to learn complex motor skills and control policies for robots. RL allows robots to learn from their own experiences, without the need for explicit programming or handcrafted rules. RL has been used to teach robots to perform tasks such as grasping objects, walking, running, and even playing soccer. One challenge in applying RL to robotics is the high cost and potential risks associated with learning from real-world interactions. To address this, researchers often use simulation environments to train RL agents before deploying them on physical robots. Transfer learning techniques can then be used to adapt the policies learned in simulation to the real world. RL has also been applied to various control problems, such as optimizing the performance of data centers, managing traffic flow, and controlling power grids. In these applications, RL agents learn to make decisions that optimize a specific objective, such as minimizing energy consumption or reducing congestion, based on the current state of the system and the expected future rewards. In the field of natural language processing, RL has been used to train dialogue systems that can interact with users in a more natural and engaging way. RL-based dialogue agents learn to select appropriate responses based on the conversation history and the expected future rewards, such as user satisfaction or task completion. RL has also been applied to recommendation systems, where the goal is to learn a policy for recommending items to users that maximizes long-term user engagement or satisfaction. In this setting, the agent's actions correspond to recommending items, the states represent user preferences and history, and the rewards are based on user feedback, such as clicks, ratings, or purchases. These are just a few examples of the many applications of reinforcement learning. As RL algorithms continue to improve and computing power increases, we can expect to see RL being applied to even more complex and diverse problems in the future. One area of growing interest is the application of RL to real-world problems that involve multiple agents, such as multi-agent robotics, traffic control, and resource management in distributed systems. Multi-agent reinforcement learning, MARL, introduces additional challenges compared to single-agent RL, such as the need to coordinate and cooperate with other agents, the problem of non-stationarity due to the changing policies of other agents, and the increased complexity of the state and action spaces. Lesson 7, Deep Reinforcement Learning Introduction to Deep Reinforcement Learning. Deep Reinforcement Learning, Deep RL, is a subfield of machine learning that combines the power of deep neural networks with the principles of reinforcement learning to enable agents to learn complex behaviors and make optimal decisions in high-dimensional environments. Deep RL has emerged as a powerful approach for solving challenging problems that involve learning from interactions with an environment, particularly when the state and/or action spaces are large or continuous. The key idea behind Deep RL is to use deep neural networks to approximate the value function, the policy function, or both. By leveraging the representational power of deep neural networks, Deep RL agents can learn directly from raw, high-dimensional inputs, such as images or sensor data, without the need for manual feature engineering. This has enabled Deep RL to achieve impressive results in domains that were previously considered intractable for traditional RL methods. One of the earliest and most influential successes of Deep RL was the development of deep Q networks, DQNs, which combined Q-learning with deep convolutional neural networks to learn to play Atari games directly from pixel inputs. DQNs achieved human-level or even superhuman performance on a wide range of Atari games, demonstrating the potential of Deep RL to learn effective policies in complex, high-dimensional environments. Since the introduction of DQNs, Deep RL has been applied to a variety of other domains, including robotics, control systems, natural language processing, and recommendation systems. Deep RL algorithms have been used to train robots to perform complex manipulation tasks, to optimize the performance of data centers, and to develop dialogue systems that can interact with users in a natural and engaging way. Deep RL algorithms can be broadly categorized into two main types: value-based methods and policy-based methods. Value-based methods, such as DQN and its variants, learn an action value function, Q, S, A, which represents the expected return of taking action A in state S and following the optimal policy thereafter. The policy is then implicitly derived from the Q function, for example, by choosing the action with the highest Q value in each state. Policy-based methods, such as policy gradient algorithms and actor-critic methods, directly learn a parameterized policy, pi, AS, which maps states to actions or probability distributions over actions. The policy is typically represented by a deep neural network and is updated by following the gradient of the expected return with respect to the policy parameters. Deep RL offers several advantages over traditional RL methods. Deep neural networks can learn complex, nonlinear mappings from states to actions or values, allowing deep RL agents to operate in high-dimensional and continuous state and action spaces. Deep RL agents can also learn hierarchical representations of the state space, enabling them to discover useful features and abstractions that can improve the efficiency and effectiveness of learning. Despite its successes, Deep RL also faces several challenges. Deep RL algorithms can be sample inefficient, requiring a large number of interactions with the environment to learn effective policies. They can also be sensitive to the choice of hyperparameters and can suffer from instability during training. Research in Deep RL is rapidly advancing, with new algorithms and techniques being developed to address these challenges and to further improve the performance and applicability of Deep RL agents. Combining deep learning with reinforcement learning, the power of representation. The combination of deep learning and reinforcement learning has led to significant breakthroughs in artificial intelligence, enabling the development of agents that can learn complex behaviors and make intelligent decisions in challenging environments. The power of Deep RL lies in the synergy between the representational capacity of deep neural networks and the decision-making framework of reinforcement learning. Deep neural networks have the ability to learn hierarchical representations of data, automatically extracting relevant features from raw, high-dimensional inputs. This eliminates the need for manual feature engineering, which was a major bottleneck in traditional RL methods. By learning directly from raw inputs, such as images or sensor data, Deep RL agents can operate in complex, real-world environments without relying on handcrafted state representations. Reinforcement learning, on the other hand, provides a framework for learning optimal policies through trial-and-error interactions with an environment. By framing the problem as maximizing cumulative rewards, RL provides a natural way to learn goal-directed behavior. The combination of deep learning and RL allows agents to learn both the representation of the state space and the mapping from states to actions, or values, in an end-to-end manner. This enables Deep RL agents to learn complex policies that map directly from raw sensory inputs to actions, without the need for intermediate stages of feature extraction or state estimation. One of the key advantages of using deep neural networks in RL is their ability to generalize across states and actions. Traditional RL methods often rely on tabular representations of the value function or policy, which can only represent a finite number of states and actions. Deep neural networks, in contrast, can approximate continuous functions and generalize to unseen states and actions based on their similarity to previously encountered ones. This allows Deep RL agents to handle large or continuous state and action spaces that would be intractable for tabular methods. Another advantage of Deep RL is the ability to learn hierarchical and compositional representations. Deep neural networks can learn to represent complex concepts and relationships by composing simpler features learned in lower layers. This can lead to more efficient and effective learning, as the agent can reuse and combine learned features to represent new states and actions. The use of deep neural networks in RL also enables the application of advanced techniques from deep learning, such as convolutional neural networks, CNNs, for processing visual inputs, recurrent neural networks, RNNs, for processing sequential data, and attention mechanisms for focusing on the most relevant parts of the input. These techniques have significantly expanded the range of problems that can be addressed with RL. However, the combination of deep learning and RL also introduces new challenges. Deep neural networks can be difficult to train and can require large amounts of data. Reinforcement learning algorithms, on the other hand, often involve high-variance updates and can be sensitive to the choice of hyperparameters. The combination of these factors can lead to instability and slow convergence during training. Value-based deep RL, DQN and its variance value-based methods are one of the two main approaches in deep reinforcement learning, the other being policy-based methods. Value-based methods focus on learning an action value function, Q, S, A, which represents the expected return of taking action A in state S and following the optimal policy thereafter. Deep Q networks, DQNs, are a prominent example of value-based deep RL that have achieved significant success in various domains. DQNs use a deep neural network to approximate the optimal action value function, Q** S, A. The network takes the state S as input and outputs a vector of Q values, one for each possible action A. The use of a deep neural network allows DQNs to handle high-dimensional state spaces, such as images, where traditional tabular Q-learning would be infeasible. The training of a DQN involves minimizing the temporal difference, TD, error, which is the difference between the current estimate of the Q value and the updated estimate based on the observed reward and the maximum Q value in the next state. The TD error can be written as delta equals R plus gamma max sub A slash sub Q S A theta sup dash slash sup Q S A theta, where S is the current state, A is the action taken in state S, R is the immediate reward received, S is the next state, A is the action that maximizes the Q value in the next state, gamma is the discount factor, theta represents the parameters of the Q network, and theta sup dash slash sup represents the parameters of a separate target network. To improve the stability of training, DQNs employ two key techniques, experience replay and target networks. Experience replay stores the agent's experiences in a replay buffer, which is a large memory that holds a collection of past transitions, S, A, R, S. During training, many batches of transitions are randomly sampled from the replay buffer to update the Q network. This helps to break the correlations between consecutive updates, reduce the variance of the updates, and stabilize learning. Target networks use a separate neural network to compute the target Q values in the TD error. The target network has the same architecture as the main Q network, but its weights are updated less frequently. Typically, the target network's weights are periodically copied from the main network's weights, or they are slowly updated towards the main network's weights using a soft update rule. The use of a target network helps to reduce the oscillations and instability that can arise from updating the Q network using its own rapidly changing estimates. Since the introduction of the original DQN, several improvements and extensions have been proposed. Double DQN, DDQN, addresses the problem of overestimation bias in Q-learning, which can occur when the maximum Q value is used as an estimate of the maximum expected Q value. DDQN decouples the selection of the action from the evaluation of its value in the target. It uses the main Q network to select the best action in the next state, A equals argmax sub A slash sub Q, S, A, theta, but uses the target network to evaluate the value of that action, Q, S, A, theta sup dash slash sup. Prioritized experience replay is another extension that biases the sampling of transitions from the replay buffer based on their TD error. Transitions with higher TD errors, which are considered more surprising or informative, are sampled more frequently. This allows the agent to learn more efficiently from the most important experiences. Dueling DQN uses a network architecture that separately estimates the state value function versus and the advantage function A, S, A. The Q values are then computed as Q, S, A, equals versus plus A, S, A. This can improve the performance of the agent by allowing it to learn which states are valuable without having to learn the effect of each action in each state. These and other advancements have further improved the performance and stability of deep Q learning, making it a powerful approach for solving complex reinforcement learning problems. Policy-based deep RL, policy gradients and actor-critic methods. Policy-based methods are the other main approach in deep reinforcement learning, alongside value-based methods. Unlike value-based methods, which learn an action value function and derive a policy from it, policy-based methods directly learn a parameterized policy, pi sub theta slash sub as, which maps states to actions or probability distributions over actions. The policy is typically represented by a deep neural network, where the network parameters theta are optimized to maximize the expected return. Policy gradient methods are a popular class of policy-based algorithms that work by directly computing the gradient of the expected return with respect to the policy parameters, nabla sub theta slash sub j, theta, and then updating the parameters in the direction of the gradient using an optimization algorithm like stochastic gradient descent. The policy gradient theorem provides an expression for the gradient of the expected return that can be estimated from experience without requiring knowledge of the environment's transition dynamics. Reinforce, also known as Monte Carlo policy gradient, is a fundamental policy gradient algorithm. It collects a set of trajectories by following the current policy and then uses these trajectories to estimate the policy gradient. The policy parameters are updated in the direction of the estimated gradient, scaled by the return of each trajectory. One limitation of reinforce is that the gradient estimates can have high variance, as they are based on the full returns of the trajectories, which can vary significantly. To reduce the variance of the gradient estimates, a baseline can be subtracted from the return. A common choice for the baseline is the state value function versus, which represents the average return starting from state S. This leads to the advantage function A, S, A, equals Q, S, A, versus, which represents how much better or worse the action A is compared to the average action in state S. Using the advantage function in the policy gradient update can significantly reduce the variance and improve the stability of learning. Actor-critic methods combine policy gradient methods with value function approximation. They maintain two separate structures, an actor, which represents the policy and is updated using policy gradients, and a critic, which represents the value function and is used to evaluate the actions taken by the actor. The critic can be used to estimate the advantage function, which is then used to update the actor. Actor-critic methods can be more sample efficient than reinforce, as they can learn from each individual transition rather than requiring a complete trajectory. They can also be more stable, as the value function provides a more reliable estimate of the return than the Monte Carlo estimate used in reinforce. Proximal policy optimization, PPO, is a state-of-the-art policy gradient algorithm that has gained popularity due to its stability, sample efficiency, and ease of implementation. PPO introduces a clipped surrogate objective that prevents the policy from being updated too drastically at each iteration. This helps to avoid performance collapses that can occur when the policy changes too much, leading to a significant drop in performance. Trust Region Policy Optimization, TRPO, is another policy gradient algorithm that aims to improve the stability of learning by constraining the policy updates to a trust region, where the new policy is not too far from the old policy. TRPO uses the KL divergence between the old and new policies to define the trust region. Policy-based methods offer several advantages over value-based methods. They can learn stochastic policies, which can be beneficial in partially observable environments or when facing adversarial opponents. They can also handle continuous action spaces more naturally than value-based methods, which often require discretization of the action space. However, policy-based methods can also be more challenging to tune and can suffer from high variance in the gradient estimates. Despite these challenges, policy-based methods, particularly actor-critic methods and algorithms like PPO and TRPO, have achieved impressive results on a wide range of challenging reinforcement learning tasks, including continuous control, robotics, and game playing. Advanced deep RL algorithms, improving stability, efficiency, and performance. Since the development of basic deep RL algorithms like DQN and policy gradients, researchers have proposed numerous advanced algorithms and techniques to improve the stability, efficiency, and performance of deep RL agents. These advancements have enabled deep RL to tackle more complex and challenging problems in various domains. One important area of research has been the development of algorithms that can learn more effectively from limited data. Off-policy algorithms, such as DQN and DDPG, can learn from experiences collected under a different policy, which allows them to reuse past experiences and improve sample efficiency. However, off-policy learning can be unstable and sensitive to the choice of hyperparameters. Several algorithms have been proposed to improve the stability and performance of off-policy learning. Soft actor-critic (SAC) is an off-policy actor-critic algorithm that incorporates entropy regularization into the objective function. The entropy of the policy is a measure of its randomness, and maximizing the entropy encourages the policy to explore more diverse actions. SAC has been shown to be more sample efficient and robust than other off-policy algorithms on a range of continuous control tasks. Twin-delayed deep deterministic policy gradient, TD3, is another off-policy algorithm that addresses the problem of overestimation bias in actor-critic methods. TD3 introduces several techniques to reduce overestimation, including using the minimum value of two Q functions, clipped double Q learning, delaying policy updates relative to Q function updates, and adding noise to the target action. These techniques help to improve the stability and performance of the algorithm. Distributional RL is an approach that focuses on learning the full distribution of returns, rather than just the expected return. This can provide a more complete picture of the agent's performance and can be useful in risk-sensitive applications. Categorical DQN, C51, and quantile regression DQN, QRDQN, are examples of distributional RL algorithms that have shown improved performance on Atari games. Rainbow is an algorithm that combines several improvements to DQN, including double DQN, prioritized experience replay, dueling networks, multi-step learning, distributional RL, and noisy nets. By combining these techniques, Rainbow achieved state-of-the-art performance on the Atari benchmark, demonstrating the effectiveness of combining multiple algorithmic improvements. Another important area of research is exploration, which is crucial for learning effective policies, especially in environments with sparse rewards. Noisy networks introduce parametric noise to the weights of the neural network to encourage exploration. This can be a more effective exploration strategy than epsilon greedy or entropy regularization in some environments. Parameter space noise for exploration adds noise directly to the parameters of the policy network, rather than to the actions. This can lead to more consistent exploration behavior and has been shown to improve performance on tasks that require temporally extended exploration. Curiosity-driven exploration is an approach that rewards the agent for visiting novel or surprising states. This can help the agent to explore more effectively in environments with sparse extrinsic rewards. Intrinsic Curiosity Module, ICM, is an example of a curiosity-driven exploration method that learns a forward model of the environment and rewards the agent for taking actions that lead to state transitions that are difficult to predict. These are just a few examples of the many advanced deep RL algorithms and techniques that have been developed in recent years. Challenges in deep RL, sample inefficiency, instability, and hyperparameter sensitivity. Despite the impressive successes of deep reinforcement learning, several challenges remain that limit its applicability and performance in certain domains. Addressing these challenges is an active area of research, and progress in these areas is crucial for realizing the full potential of deep RL. One of the major challenges in deep RL is sample inefficiency. Deep RL algorithms often require a large number of interactions with the environment to learn effective policies, which can be impractical or expensive in real-world applications. For example, training a DQN agent to play an Atari game may require millions of frames of experience, which can take days or even weeks on modern hardware. Similarly, training a robot to perform a task in the real world may require a large number of trials, which can be time-consuming and potentially unsafe. Several factors contribute to the sample inefficiency of deep RL. One factor is the high variance of the updates, particularly in policy gradient methods, which can lead to slow and unstable learning. Another factor is the need for extensive exploration, especially in environments with sparse rewards, which can require a large number of interactions to discover rewarding states and actions. Another challenge in deep RL is the instability of learning. Deep RL algorithms can be sensitive to the choice of hyperparameters, such as the learning rate, the network architecture, and the exploration strategy. Poor choices of hyperparameters can lead to unstable learning or even divergence, where the performance of the agent collapses during training. The non-stationarity of the learning problem, where the data distribution changes as the policy improves, also contributes to instability. This can make it difficult to tune the hyperparameters and can require careful scheduling of learning rates and other parameters. The use of function approximation, particularly deep neural networks, can also introduce instability due to the complex interactions between the network parameters and the learning dynamics. Small changes in the network weights can lead to significant changes in the policy and the value function, which can destabilize learning. Overestimation bias is another issue that can affect the performance of deep RL algorithms, particularly value-based methods like DQN. Overestimation bias occurs when the estimated action values are consistently higher than the true action values, which can lead to the agent learning suboptimal policies. Techniques like double DQN and target networks have been developed to mitigate this issue but may not eliminate it entirely. Another challenge in deep RL is the difficulty of exploration, particularly in environments with sparse rewards. Many real-world problems have sparse rewards, meaning that the agent receives non-zero rewards only infrequently. This makes it difficult for the agent to learn which actions are responsible for the rewards and can lead to very slow learning. Handcrafting reward functions that provide more frequent feedback can help, but this can be difficult and may inadvertently lead the agent to learn unintended behaviors. Developing more effective exploration strategies is an active area of research in deep RL. Techniques like curiosity-driven exploration, which rewards the agent for visiting novel or surprising states, and intrinsic motivation, which encourages the agent to learn skills that are useful across a range of tasks, have shown promise in improving exploration in sparse reward environments. Generalization is another important challenge in deep RL. While deep RL agents can achieve impressive performance on the specific environments they are trained in, they often struggle to generalize to new, unseen environments, even if those environments are similar to the training environments. This is in contrast to humans, who can often quickly adapt to new situations based on their prior experience. Improving the generalization ability of deep RL agents is a crucial area of research. Techniques such as data augmentation, domain randomization, and meta-learning have been explored to improve generalization in deep RL. Deep RL for robotics, learning control policies for physical systems. Deep reinforcement learning has shown significant promise for enabling robots to learn complex control policies directly from raw sensory inputs, such as camera images and joint angles. By combining the representation learning capabilities of deep neural networks with the trial-and-error learning framework of reinforcement learning, deep RL can allow robots to acquire sophisticated skills and behaviors that would be difficult to program manually. One of the key challenges in applying deep RL to robotics is the high dimensionality of the state and action spaces. Robots often have many degrees of freedom, and their sensory inputs can be high-dimensional and noisy. Deep neural networks can help to address this challenge by learning compact and informative representations of the robot's state from raw sensory data. Another challenge is the cost and potential risks associated with learning from real-world interactions. Training a robot in the real world can be time-consuming, expensive, and potentially dangerous if the robot makes mistakes during the learning process. To address this challenge, researchers often use simulation environments to train deep RL agents before deploying them on physical robots. Simulators such as MuJoCo, Gazebo, and PyBullet provide realistic physics simulations and allow for faster and safer training of robot control policies. Transfer learning techniques can then be used to adapt the policies learned in simulation to the real world. Domain randomization is a popular approach for improving transfer learning in deep RL for robotics. It involves randomizing various aspects of the simulation environment during training, such as the textures, lighting, and physics parameters. By training on a diverse set of environments, the agent learns a policy that is more robust and can generalize better to the real world. Another approach to bridging the gap between simulation and reality is to learn a model of the real-world environment from data collected on the physical robot. This model can then be used to improve the accuracy of the simulator or to perform policy optimization directly in the real world. DeepRL has been used to learn a wide range of robotic skills, including locomotion, manipulation, and navigation. For example, DeepRL agents have been trained to control simulated and real-legged robots to walk, run, and perform other dynamic behaviors. In manipulation tasks, DeepRL has been used to learn policies for grasping, pushing, and other complex object interactions. These policies can be learned directly from raw visual inputs, allowing robots to interact with objects in unstructured environments. One notable example of DeepRL for robotics is the dactyl system developed by OpenAI, which learned to manipulate a Rubik's Cube with a human-like robot hand. The system was trained using a combination of reinforcement learning and supervised learning and demonstrated impressive dexterity and robustness to perturbations. Despite the successes of DeepRL in robotics, several challenges remain. One challenge is the sample inefficiency of DeepRL algorithms, which can require a large number of trials to learn effective policies. This can be particularly problematic in robotics, where each trial can be time-consuming and potentially costly. Another challenge is the safety and robustness of DeepRL policies. DeepRL agents can sometimes learn unexpected or unsafe behaviors, particularly when they are deployed in environments that are different from the training environment. Ensuring the safety and reliability of DeepRL agents is a crucial area of research, particularly for applications where robots interact with humans or operate in safety-critical domains. DeepRL in natural language processing, dialogue systems and text-based games. Deep reinforcement learning has emerged as a promising approach for developing more sophisticated and adaptive natural language processing (NLP) systems. By framing NLP tasks as sequential decision-making problems, DeepRL can enable agents to learn complex language understanding and generation skills through interactions with an environment. One prominent application of DeepRL in NLP is in the development of dialogue systems, also known as conversational agents or chatbots. Traditional dialogue systems are often based on handcrafted rules and templates, which can limit their ability to handle diverse and unpredictable user inputs. DeepRL offers a more flexible and data-driven approach to building dialogue systems that can learn from interactions with users. In a typical DeepRL framework for dialogue, the agent state represents the current dialogue context, which may include the conversation history, user information, and other relevant knowledge. The agent's actions correspond to generating responses or taking other actions, such as querying a database or invoking an external API. The reward function is typically based on user feedback, such as explicit ratings or implicit signals like task completion or conversation length. One approach to applying DeepRL to dialogue is to use a sequence-to-sequence (seek-to-seek) model as the policy network. The seek-to-seek model takes the dialogue context as input and generates a response as output. The policy is trained using policy gradient methods, such as reinforce or actor critic, to maximize the expected cumulative reward. Another approach is to use a hierarchical RL framework, where a high-level policy selects among different dialogue acts or skills, and a low-level policy generates the specific words or phrases for each act. This can allow the agent to learn more structured and coherent dialogue strategies. DeepRL has also been applied to text-based games, which are interactive simulations where the environment and the agent's interactions are described using natural language. Text-based games provide a challenging testbed for DeepRL agents, as they require both language understanding and decision-making abilities. One approach to tackling text-based games with DeepRL is to use a deep Q network, DQN, to learn an action value function over a large, discrete action space, where each action corresponds to a possible text command. Another approach is to use an actor-critic method, where the actor generates a sequence of words as the action, and the critic provides feedback on the quality of the generated action. DeepRL has also been used for other NLP tasks, such as text summarization, machine translation, and information extraction. In text summarization, for example, an RL agent can be trained to select a sequence of sentences from a document that maximizes a reward function based on the quality and coverage of the summary. One of the main challenges in applying deep RL to NLP is the difficulty of defining a good reward function. Unlike in games or robotics, where rewards are often naturally defined by the environment, in NLP tasks, it is often unclear what constitutes a good reward signal. Using human evaluations as rewards can be expensive and time-consuming. Another challenge is the large action space in many NLP tasks. Generating text often involves choosing from a large vocabulary of words at each time step, which can make exploration and learning difficult. Techniques such as action embeddings, which map discrete actions to a continuous space, and hierarchical RL, which decomposes the action space into smaller subspaces, have been proposed to address this challenge. Despite these challenges, deep RL holds significant promise for advancing the state-of-the-art in NLP. By learning from interactions and optimizing for long-term rewards, deep RL agents have the potential to develop more flexible, adaptive, and human-like language understanding and generation capabilities. The future of deep reinforcement learning, research directions and open problems. Deep reinforcement learning is a rapidly evolving field with many exciting research directions and open problems. As deep RL algorithms continue to improve and computing power increases, we can expect deep RL to play an increasingly important role in solving complex real-world problems. One important research direction is the development of more sample-efficient deep RL algorithms. Current deep RL algorithms often require a large number of interactions with the environment to learn effective policies, which can be impractical in many real-world applications. Improving the sample efficiency of deep RL is crucial for enabling its wider adoption. Several approaches are being explored to improve sample efficiency, including off-policy learning, which reuses past experiences collected under different policies, model-based RL, which learns a model of the environment to reduce the need for real-world interactions, and transfer learning, which leverages knowledge learned from related tasks or domains. Another important research direction is the development of deep RL algorithms that can learn from sparse or delayed rewards. Many real-world problems have sparse rewards, meaning that the agent receives non-zero rewards only infrequently. This makes it difficult for the agent to learn which actions are responsible for the rewards and can lead to very slow learning. Developing better exploration strategies is crucial for addressing the problem of sparse rewards. Techniques such as curiosity-driven exploration, which rewards the agent for visiting novel or surprising states, and intrinsic motivation, which encourages the agent to learn skills that are useful across a range of tasks, have shown promise in improving exploration in sparse reward environments. Hierarchical RL, which decomposes a complex task into a hierarchy of subtasks, can also help to address the problem of sparse rewards by providing intermediate rewards for achieving subgoals. Improving the stability and robustness of deep RL algorithms is another important research direction. Deep RL algorithms can be sensitive to the choice of hyperparameters and can suffer from instability during training. They can also be vulnerable to adversarial attacks, where small perturbations to the input can cause the agent to make incorrect decisions. Developing more stable and robust deep RL algorithms is crucial for deploying them in real-world applications, particularly in safety-critical domains. Techniques such as trust region methods, entropy regularization, and adversarial training are being explored to improve the stability and robustness of deep RL agents. Generalization is another key challenge in deep RL. Deep RL agents often struggle to generalize to new, unseen environments, even if those environments are similar to the training environments. Improving the generalization ability of deep RL agents is crucial for their practical applicability. Techniques such as data augmentation, domain randomization, and meta-learning are being explored to improve generalization in deep RL. Another important research direction is multi-agent deep RL, which deals with learning in environments with multiple interacting agents. Multi-agent RL introduces additional challenges compared to single-agent RL, such as the need for coordination and cooperation among agents, the problem of non-stationarity due to the changing policies of other agents, and the increased complexity of the state and action spaces. DeepRL also has the potential to advance our understanding of intelligence and learning, both in artificial and biological systems. By studying how DeepRL agents learn and solve complex tasks, we may gain insights into the principles of learning and decision-making that apply across different types of intelligent systems. Finally, the ethical and societal implications of DeepRL need to be carefully considered as the technology advances. As DeepRL agents become more capable and autonomous, it is important to ensure that they are aligned with human values and goals and that they are used responsibly and for the benefit of society. Lesson 8. Explainable AI and interpretability in deep learning. The need for interpretability in deep learning. As deep learning models become increasingly complex and are deployed in high-stakes applications, the need for interpretability and explainability has become more pressing. Interpretability refers to the ability to understand how a model arrives at its decisions, while explainability refers to the ability to provide clear and understandable reasons for a model's behavior. In many domains, such as healthcare, finance, and criminal justice, decisions made by AI systems can have significant consequences for individuals and society. In these contexts, it is not enough for a model to make accurate predictions, it is also crucial to understand why the model made those predictions and to be able to justify them to stakeholders. Lack of interpretability can lead to several problems. It can make it difficult to identify and correct biases in the model. If a model is making decisions based on spurious correlations or sensitive attributes, such as race or gender, it is important to be able to detect and mitigate these biases. Without understanding how the model works, it can be challenging to identify the sources of bias and to ensure fairness and equity. Interpretability is also important for building trust in AI systems. Users and stakeholders are more likely to trust and accept AI systems if they understand how they work and can verify that they are making decisions in a reasonable and justifiable manner. In safety-critical applications, interpretability is essential for ensuring the reliability and safety of AI systems. Understanding how a model will behave in different situations and being able to diagnose the causes of errors or unexpected behavior is crucial for preventing accidents and ensuring that the system performs as intended. Interpretability can also facilitate debugging and improvement of deep learning models. By understanding the strengths and weaknesses of a model, developers can identify areas for improvement and guide the development of more accurate and robust models. Furthermore, interpretability can provide insights into the underlying data and the problem domain. By examining which features or patterns the model relies on to make decisions, researchers can gain a deeper understanding of the factors that are most relevant to the task at hand. This can lead to new scientific discoveries and a better understanding of complex phenomena. Despite its importance, interpretability in deep learning remains a challenging problem. Deep neural networks are often referred to as black boxes because their complex, nonlinear structure makes it difficult to understand how they arrive at their decisions. The large number of parameters and the distributed nature of the representations learned by deep networks further complicate the task of interpretation. However, in recent years, there has been a growing interest in developing methods for interpreting and explaining deep learning models. These methods aim to shed light on the inner workings of deep networks and to provide insights into their decision-making processes. Model-agnostic methods, interpreting models without knowledge of their internal structure. Model-agnostic interpretation methods are techniques for explaining the behavior of machine learning models without relying on any specific knowledge of their internal structure or parameters. These methods treat the model as a black box and focus on understanding the relationship between the model's inputs and outputs. One of the key advantages of model-agnostic methods is their flexibility. They can be applied to any type of machine learning model, including deep neural networks, support vector machines, and random forests. This makes them particularly useful in practice, where different models may be used for different tasks or where the internal details of a model may not be accessible. One popular model-agnostic method is LIME, Local Interpretable Model-Agnostic Explanations. LIME aims to explain individual predictions of a complex model by approximating the model's local behavior around the data point being explained. It works by generating a set of perturbed samples around the data point of interest and querying the black box model to obtain predictions for these samples. A simple, interpretable model, such as a linear model or a decision tree, is then trained on the perturbed samples and their corresponding predictions, weighted by their proximity to the original data point. The learned interpretable model provides an explanation for the black box model's prediction at that specific point. Another widely used model-agnostic method is SHAP, Shapley additive explanations. SHAP is based on the concept of Shapley values from cooperative game theory. It aims to explain a model's prediction by assigning an importance value to each feature based on its contribution to the prediction. SHAP values satisfy several desirable properties, such as local accuracy, missingness, and consistency, which make them a principled and reliable way to explain individual predictions. SHAP computes the importance of a feature by considering its average marginal contribution to the prediction across all possible coalitions, subsets, of features. This can be computationally expensive for models with a large number of features, but several approximations and efficient algorithms have been developed to make SHAP practical for real-world applications. Other model-agnostic methods include permutation feature importance, which measures the importance of a feature by randomly permuting its values and observing the effect on the model's performance, and individual conditional expectation, ICE, plots, which visualize the relationship between a feature and the model's prediction while holding other features constant. Model-agnostic methods can provide valuable insights into the behavior of complex models and can help to build trust and understanding. However, they also have limitations. They may not always capture the true underlying decision-making process of the model, as they rely on approximations and may not have access to the model's internal representations. It is also important to note that model-agnostic methods typically provide local explanations, meaning that they explain individual predictions rather than the global behavior of the model. While local explanations can be useful for understanding specific instances, they may not always generalize to other data points or provide a complete picture of the model's overall behavior. Despite these limitations, model-agnostic methods remain an important tool for interpreting and explaining complex machine learning models, particularly in cases where the internal details of the model are not accessible or when a model-independent explanation is desired. Model-specific methods, leveraging the structure of deep neural networks. Model-specific interpretation methods are techniques that leverage the specific architecture and internal representations of deep neural networks to provide insights into their behavior and decision-making processes. Unlike model-agnostic methods, which treat the model as a black box, model-specific methods exploit the structure and parameters of deep networks to generate explanations. One class of model-specific methods focuses on visualizing the features learned by different layers of a deep neural network. By visualizing the activation patterns of neurons or filters in response to different inputs, researchers can gain insights into the types of features the network has learned to detect and how these features are combined to form higher-level representations. For convolutional neural networks, CNNs, which are widely used for image data, techniques such as activation maximization and filter visualization can be used to understand what each filter has learned to detect. Activation maximization involves finding the input image that maximally activates a particular filter or neuron. This can be done by performing gradient ascent on the input image, starting from a random or blank image, to maximize the activation of the target filter or neuron. The resulting image provides a visualization of the type of pattern that the filter is most sensitive to. Filter visualization, on the other hand, aims to visualize the weights of the filters directly. For lower-layer filters, this can often be done by simply displaying the filter weights as an image. For higher-layer filters, more sophisticated techniques may be needed to visualize the complex patterns they represent. Another class of model-specific methods focuses on understanding the importance of different input features or intermediate representations for a particular prediction. Saliency maps or attribution methods aim to highlight the regions of the input, such as pixels in an image, that are most relevant to the model's prediction. Gradient-based methods, such as guided backpropagation and integrated gradients, compute the gradient of the output with respect to the input to determine the contribution of each input feature to the prediction. These gradients can be visualized as saliency maps, highlighting the areas of the input that most strongly influence the model's output. Class activation mapping, CAM, is a technique specifically designed for CNNs that generates a heat map highlighting the regions of an image that are most important for a particular class prediction. CAM requires the network to have a specific structure, where the final convolutional layer is followed by a global average pooling layer and a fully connected layer for classification. The heat map is computed as a weighted sum of the feature maps in the final convolutional layer, where the weights are the connections from the feature maps to the output class. GradCAM is a generalization of CAM that can be applied to a wider range of CNN architectures. It uses the gradients of the output with respect to the feature maps of a convolutional layer to compute the importance weights for each feature map. These weights are then used to compute a weighted sum of the feature maps, resulting in a heat map that highlights the regions of the input that are most relevant to the prediction. Model-specific methods can provide more detailed and precise insights into the internal workings of deep neural networks compared to model-agnostic methods. However, they are limited to specific types of models and may require modifications to the network architecture or training process. They may also be more computationally expensive than model-agnostic methods. Despite these limitations, model-specific methods remain an important tool for understanding and interpreting deep learning models. Visualization techniques, making sense of learned features and activations. Visualization techniques play a crucial role in interpreting and understanding deep learning models. By visually representing the learned features, activations, and decision-making processes of deep neural networks, these techniques can provide valuable insights into how models work and why they make certain predictions. One of the most basic yet powerful visualization techniques is the visualization of filter weights in convolutional neural networks, CNNs. In the early layers of a CNN, the filters often learn to detect simple visual features such as edges, corners, and textures. By directly visualizing the weights of these filters as small images, we can gain an intuitive understanding of the types of patterns they are looking for in the input. For higher layer filters, which learn more complex and abstract features, direct visualization of weights may not be as informative. In these cases, techniques such as activation maximization can be used to generate synthetic input images that maximally activate a particular filter or neuron. These synthetic images can reveal the intricate patterns and structures that the higher layer filters have learned to represent. Another useful visualization technique is the visualization of feature maps or activations. By displaying the output of a particular layer in the network for a given input, we can observe how the input is transformed and represented at different stages of processing. For CNNs, feature maps can be visualized as heat maps overlaid on the input image, highlighting the regions that are most relevant to the network's prediction. T-distributed stochastic neighbor embedding, TSNE, is a dimensionality reduction technique that is often used to visualize high-dimensional data, such as the learned representations in deep networks. TSNE maps high-dimensional data points to a low-dimensional space, typically 2D or 3D, while preserving the local neighborhood structure of the data. This allows us to visualize the relationships between different data points and observe how the network has learned to cluster or separate different classes or concepts in its representation space. Saliency maps or attribution methods, which highlight the regions of the input that are most important for a particular prediction, can also be considered as a form of visualization. By overlaying these maps on the input image, we can quickly identify which parts of the input the network is focusing on when making its decision. Techniques such as guided backpropagation, integrated gradients, and GradCAM are examples of methods that can generate such visualizations. In the context of recurrent neural networks, RNNs, visualizing the hidden state activations over time can provide insights into how the network processes sequential data. By plotting the activations of individual neurons or groups of neurons as a function of time, we can observe how the network's internal memory evolves as it processes an input sequence. This can reveal how the network learns to capture long-range dependencies and how it represents information about the past. Visualization techniques are not only useful for understanding and interpreting deep learning models but can also aid in debugging and improving them. By visualizing the learned features and activations, developers can identify potential issues, such as dead neurons, neurons that never activate, or redundant features, and make informed decisions about network architecture and training parameters. Attention mechanisms, highlighting important parts of the input attention mechanisms, have emerged as a powerful technique in deep learning, particularly in the fields of natural language processing and computer vision. They allow models to focus on the most relevant parts of the input when making predictions, improving both performance and interpretability. The basic idea behind attention is to compute a set of attention weights that indicate the importance of each part of the input, such as words in a sentence or regions in an image. These weights are then used to compute a weighted sum of the input features, which is used for making the prediction. The attention weights are typically computed dynamically for each input, allowing the model to adaptively focus on different parts of the input depending on the context. In the context of sequence-to-sequence models, such as those used in machine translation, attention mechanisms have become a crucial component. In the original sequence-to-sequence models without attention, the encoder RNN processes the input sequence and produces a fixed-length context vector, which is then used by the decoder RNN to generate the output sequence. This forces the entire input sequence to be summarized into a single vector, which can be a bottleneck, especially for long sequences. Attention mechanisms address this limitation by allowing the decoder to attend to different parts of the input sequence at each time step during decoding. At each decoding step, the attention mechanism computes a set of attention weights over the encoder hidden states. These weights are typically computed using a small neural network that takes as input the current decoder hidden state and each of the encoder hidden states. The attention weights are then used to compute a weighted sum of the encoder hidden states, resulting in a context vector that is specific to the current decoding step. This context vector is then used along with the decoder hidden state to generate the next output element. By allowing the decoder to focus on different parts of the input sequence at each time step, attention mechanisms enable the model to capture long-range dependencies more effectively and improve the overall performance of sequence-to-sequence models. They also provide a degree of interpretability, as the attention weights can be visualized to show which parts of the input sequence the model is focusing on when generating each output element. In the context of computer vision, attention mechanisms have been used to allow convolutional neural networks, CNNs, to focus on specific regions of an image when making predictions. For example, in image captioning, attention can be used to focus on the relevant parts of an image when generating each word of the caption. One popular approach is the soft attention mechanism, which computes a weighted average of the feature maps at different spatial locations, where the weights are determined by an attention network. Another approach is the hard attention mechanism, which stochastically selects a single region of the image to attend to at each time step. Attention mechanisms have also been used in other types of models, such as graph neural networks and transformers. In graph neural networks, attention can be used to weight the contributions of neighboring nodes when aggregating information. In transformers, which have become the dominant architecture for many natural language processing tasks, self-attention mechanisms are used to compute relationships between different parts of the input sequence, allowing the model to capture long-range dependencies without the need for recurrent connections. Attention mechanisms not only improve the performance of deep learning models but also enhance their interpretability by providing a window into the model's focus and decision-making process. Adversarial examples and robustness. Understanding model vulnerabilities. Adversarial examples are inputs to machine learning models that are specifically designed to cause the model to make incorrect predictions. These examples are often created by adding small, carefully crafted perturbations to legitimate inputs, which are imperceptible to humans but can lead the model to misclassify the input. The existence of adversarial examples highlights the vulnerability of deep learning models and raises concerns about their reliability and security, particularly in safety-critical applications. Segedi et al. First discovered the existence of adversarial examples in 2013. They showed that deep neural networks are vulnerable to adversarial attacks, where small perturbations to the input can lead to misclassification with high confidence. This was a surprising finding, as it demonstrated that even state-of-the-art deep learning models can be easily fooled by inputs that appear indistinguishable from legitimate ones to humans. Adversarial examples are typically generated by optimizing an objective function that aims to find a perturbation that maximizes the model's prediction error while keeping the perturbation small and imperceptible. This can be formulated as an optimization problem, where the goal is to find an adversarial example x equals x plus delta that is close to the original input x, i.e., delta epsilon, where epsilon is a small constant, but is classified incorrectly by the model. One of the most widely used methods for generating adversarial examples is the fast gradient sign method, FGSM. FGSM computes the gradient of the loss function with respect to the input and then adds a small perturbation to the input in the direction of the sign of the gradient. This perturbation is scaled by a small constant epsilon to ensure that it remains imperceptible. Other, more sophisticated methods for generating adversarial examples have also been proposed, such as the basic iterative method, BEAM, projected gradient descent, PGD, and the Carlini and Wagner, CNW, attack. These methods often involve multiple iterations of gradient computation and perturbation to find more effective adversarial examples. The existence of adversarial examples has raised concerns about the robustness and security of deep learning models. In safety-critical applications, such as autonomous driving and medical diagnosis, adversarial attacks could have serious consequences. For example, an attacker could create adversarial road signs that are misclassified by an autonomous vehicle's perception system, potentially leading to accidents. Adversarial examples also have implications for the interpretability of deep learning models. The fact that small perturbations to the input can lead to large changes in the model's output suggests that the model may be relying on spurious correlations or features that are not meaningful to humans. This highlights the importance of understanding the vulnerabilities of deep learning models and developing methods to make them more robust to adversarial attacks. Several defense mechanisms against adversarial examples have been proposed. One approach is adversarial training, which involves augmenting the training data with adversarial examples. By training the model on both legitimate and adversarial examples, it can learn to be more robust to small perturbations in the input. Another approach is defensive distillation, which involves training a second model to mimic the output probabilities of a pre-trained model. The second model is trained on the soft probabilities produced by the pre-trained model, which can make it more resistant to adversarial examples. Other defense mechanisms include input transformations, such as adding random noise or performing JPEG compression, and using ensemble methods, where multiple models are combined to make predictions. However, many of these defenses have been shown to be vulnerable to more powerful attacks. The development of robust defenses against adversarial examples remains an open challenge and an active area of research. The study of adversarial examples has also led to a deeper understanding of the properties and limitations of deep learning models. It has been shown that adversarial examples are not just a peculiarity of specific models or datasets but rather a fundamental property of high-dimensional learning. This has implications for the theoretical understanding of deep learning and has spurred research into the geometry of high-dimensional spaces and the nature of generalization in deep networks. The existence of adversarial examples also highlights the importance of considering security and robustness when designing and deploying deep learning models, particularly in safety-critical applications. It underscores the need for rigorous testing and validation of models, as well as the development of methods for detecting and mitigating adversarial attacks. As deep learning models become more integrated into our lives, addressing the challenges posed by adversarial examples will be crucial for ensuring their safe, reliable, and trustworthy deployment. Explainable AI, XAI, techniques, methods for generating human-understandable explanations. Explainable AI, XAI, is a set of techniques and methods aimed at making the behavior and predictions of AI systems, particularly deep learning models, more understandable to humans. XAI methods strive to provide clear, concise, and human-interpretable explanations for why a model made a specific decision or how it arrived at a particular output. One class of XAI techniques focuses on generating post-hoc explanations for pre-trained models. These methods aim to explain the behavior of a model after it has been trained, without modifying the model itself. LIME, Local Interpretable Model Agnostic Explanations, and SHAP, Shapley Additive Explanations, are two popular examples of post-hoc explanation methods. LIME explains individual predictions by approximating the local behavior of the model around the data point being explained. It trains a simple, interpretable model on perturbed samples and their corresponding predictions, weighted by their proximity to the original data point. The learned interpretable model provides an explanation for the black box model's prediction at that specific point. SHAP explains predictions by assigning an importance value to each feature based on its contribution to the prediction, using the concept of Shapley values from game theory. SHAP values provide a theoretically sound and consistent way to attribute the prediction to different input features. Another class of XAI techniques focuses on developing inherently interpretable models. These models are designed from the ground up to be more transparent and understandable in their decision-making process. Examples include linear models, decision trees, and rule-based systems. However, these models often have limited expressive power compared to deep neural networks. Some research has explored hybrid approaches that combine the strengths of deep learning with inherently interpretable models. For example, attention mechanisms can be incorporated into deep neural networks to provide a degree of interpretability by highlighting the parts of the input that the model is focusing on. Another approach is to use deep learning to learn a disentangled representation, where different factors of variation in the data are captured by separate latent variables. This can make the learned representations more interpretable and allow for better control over the generated outputs. Neurosymbolic models combine deep neural networks with symbolic reasoning to create models that can learn from data and also incorporate prior knowledge and logical rules. These models aim to bridge the gap between the statistical learning capabilities of deep networks and the interpretability of symbolic systems. XAI techniques can also be categorized based on the type of explanation they provide. Some methods, like LIME and SHAP, provide feature-based explanations, which highlight the importance of different input features for a particular prediction. Other methods, like decision trees or rule-based systems, provide example-based explanations, which explain a prediction by comparing it to similar examples in the training data. Counterfactual explanations are another type of explanation that has gained attention in recent years. A counterfactual explanation for a prediction specifies the smallest change to the input that would lead to a different prediction. For example, a counterfactual explanation for a loan application that was denied might state that the loan would have been approved if the applicant's income had been higher or their credit score had been better. Generating effective counterfactual explanations is an active area of research. It involves solving an optimization problem to find the closest input to the original input that leads to a different prediction, subject to certain constraints. The choice of XAI technique depends on the specific application, the type of model being used, and the desired properties of the explanation. Different stakeholders may have different requirements for interpretability. For example, a developer might want detailed insights into the model's internal workings to debug and improve it, while an end user might prefer a simple, intuitive explanation for a specific prediction. XAI is a rapidly evolving field, and new methods and techniques are constantly being developed. Evaluating interpretability, metrics and methodologies for assessing explanation quality. Evaluating the quality and effectiveness of interpretability methods is a challenging but crucial aspect of explainable AI research. Unlike traditional machine learning tasks, where performance can be measured using well-defined metrics like accuracy or precision, there is no single, universally accepted metric for assessing the quality of an explanation. One approach to evaluating interpretability is to use human evaluation. Human subjects can be presented with explanations generated by different methods and asked to rate them based on various criteria, such as understandability, usefulness, and trustworthiness. These subjective evaluations can provide valuable insights into how well different explanation methods meet the needs of human users. However, human evaluation can be time-consuming, expensive, and difficult to scale. It can also be subjective and may not always provide a clear ranking of different methods. To address these limitations, researchers have proposed several quantitative metrics for evaluating interpretability. One such metric is fidelity, which measures how well an explanation matches the behavior of the underlying model. A high-fidelity explanation is one that accurately reflects the model's decision-making process. Fidelity can be measured by comparing the predictions of the explanation model, e.g., a linear model trained on perturbed samples in LIME, to the predictions of the original model on a set of test inputs. Another metric is stability, which measures the consistency of explanations for similar inputs. A stable explanation method should produce similar explanations for inputs that are close to each other in the input space. Stability can be measured by generating small perturbations of an input and comparing the explanations generated for the original and perturbed inputs. Sparsity is another desirable property of explanations, particularly in high-dimensional settings. A sparse explanation is one that involves only a small number of features or components, making it easier to understand and interpret. Sparsity can be measured by counting the number of non-zero coefficients in a linear explanation model or by computing the entropy of the attention weights in an attention-based model. Other metrics that have been proposed for evaluating interpretability include comprehensiveness, how much of the model's behavior is captured by the explanation. Compactness, the size or complexity of the explanation. Consistency, whether similar inputs produce similar explanations across different models or runs. Correctness, whether the explanation accurately reflects the ground truth or expert knowledge. Importance, whether the explanation highlights the most relevant features or factors. In addition to quantitative metrics, qualitative evaluation methods, such as case studies and user studies, can also provide valuable insights into the effectiveness of interpretability methods. These methods can help to identify the strengths and weaknesses of different explanation techniques in real-world scenarios and can provide a more holistic assessment of their usefulness. It is important to note that the choice of evaluation metric depends on the specific application and the goals of interpretability. Different stakeholders may have different requirements for interpretability, and different types of explanations may be more suitable for different tasks. For example, a developer debugging a model may prioritize fidelity and comprehensiveness, while an end user may value simplicity and ease of understanding more highly. Ultimately, the evaluation of interpretability is a multifaceted problem that requires a combination of quantitative metrics, qualitative analysis, and human judgment. Lesson 9, Advanced Deep Learning Architectures. Introduction to Advanced Architectures. As deep learning has matured as a field, researchers have developed increasingly sophisticated and specialized neural network architectures to tackle complex problems and improve performance across various domains. These advanced architectures often build upon the fundamental building blocks of deep learning, such as convolutional neural networks, CNNs, and recurrent neural networks, RNNs, but introduce novel concepts and designs to enhance their capabilities. One trend in advanced deep learning architectures is the development of models that can capture more complex and structured relationships in data. Graph neural networks, GNNs, for example, are designed to operate on graph-structured data, where the relationships between entities are represented by edges in a graph. GNNs have shown promise in applications such as social network analysis, recommendation systems, and drug discovery. Another trend is the development of architectures that can learn more efficiently and effectively from limited data. Meta-learning, also known as learning to learn, aims to train models that can quickly adapt to new tasks or environments with only a few examples. This is achieved by training the model on a distribution of tasks, rather than a single task, and optimizing for fast adaptation to new tasks sampled from the same distribution. Transfer learning, where a model trained on a large dataset is fine-tuned for a different but related task, has also become a powerful technique for improving performance when data is limited. Pre-trained models, such as BERT and GPT in natural language processing and VGG and ResNet in computer vision, have become widely used starting points for many applications. Another important direction in deep learning research is the development of architectures that can incorporate different types of inductive biases. Inductive biases are assumptions or constraints that are built into the model architecture to guide the learning process and improve generalization. For example, CNNs incorporate the inductive bias that spatial locality and translation invariance are important for image data, while RNNs incorporate the inductive bias that sequential order matters for temporal data. Hybrid architectures that combine the strengths of different types of models have also emerged as a powerful approach. For example, neurosymbolic models combine deep neural networks with symbolic reasoning to create models that can learn from data and also incorporate prior knowledge and logical rules. These models aim to bridge the gap between the statistical learning capabilities of deep networks and the interpretability and reasoning abilities of symbolic systems. Attention mechanisms, which allow models to focus on the most relevant parts of the input, have become a key component in many advanced architectures. Transformers, which rely entirely on self-attention mechanisms to capture relationships between different parts of the input sequence, have revolutionized natural language processing and are increasingly being applied to other domains, such as computer vision. The development of advanced deep learning architectures is an ongoing and rapidly evolving area of research. New architectures and techniques are constantly being proposed to address the limitations of existing models and to push the boundaries of what is possible with deep learning. Transformers and self-attention, revolutionizing sequence modeling. Transformers are a groundbreaking neural network architecture that has revolutionized the field of natural language processing and is increasingly being applied to other domains, such as computer vision and audio processing. Introduced by Vaswani et al. In 2017, transformers depart from the recurrent and convolutional architectures that previously dominated sequence modeling tasks. Instead, they rely entirely on a novel mechanism called self-attention to capture relationships between different parts of the input sequence. The key innovation in transformers is the self-attention mechanism, which allows the model to weigh the importance of each element in the input sequence when encoding another element. Unlike recurrent models, which process the input sequentially and maintain a hidden state that is updated at each time step, transformers can process the entire input sequence in parallel. This makes them highly efficient and scalable to long sequences. In the self-attention mechanism, each element in the input sequence is transformed into three vectors: a query vector, a key vector, and a value vector. These vectors are obtained by multiplying the input embedding with learned weight matrices. To compute the attention weights for a given element, the query vector of that element is compared to the key vectors of all elements in the sequence using a dot product. The resulting scores are then scaled down by the square root of the dimension of the key vectors and passed through a softmax function to obtain a probability distribution over the input elements. This distribution represents the attention weights, indicating the relevance of each element to the given element. The output of the self-attention layer is a weighted sum of the value vectors, where the weights are given by the attention weights. This allows the model to combine information from different parts of the input sequence, taking into account their relevance to each other. The transformer architecture consists of an encoder and a decoder, each composed of multiple layers of self-attention and feed-forward neural networks. The encoder processes the input sequence and generates a set of contextualized embeddings, which capture the meaning of each element in the context of the entire sequence. The decoder then generates the output sequence, using the encoder embeddings and its own self-attention mechanism to attend to both the input sequence and the previously generated output elements. One of the key advantages of transformers is their ability to capture long-range dependencies in the input sequence. In recurrent models, information from distant elements needs to be propagated through many time steps, which can lead to the vanishing gradient problem and make it difficult to learn long-range relationships. In contrast, transformers can directly attend to any element in the input sequence, regardless of its distance, allowing them to capture long-range dependencies more effectively. Transformers have achieved state-of-the-art results on a wide range of natural language processing tasks, including machine translation, text summarization, question answering, and sentiment analysis. Models such as BERT, bidirectional encoder representations from transformers, and GPT, generative pre-trained transformer, have become widely used in both research and industry. The success of transformers has also inspired their application to other domains beyond natural language processing. In computer vision, for example, the vision transformer, VIT, applies a transformer encoder directly to image patches, treating them as a sequence of tokens. VIT has achieved competitive results compared to state-of-the-art convolutional neural networks on image classification tasks, demonstrating the potential of transformers to generalize across different data modalities. Despite their impressive performance, transformers also have some limitations. The computational cost of self-attention grows quadratically with the sequence length, which can make it expensive to apply transformers to very long sequences. Several approaches have been proposed to address this limitation, such as sparse attention mechanisms and linear attention mechanisms, which reduce the computational complexity while maintaining most of the performance benefits. As research on transformers continues to advance, we can expect to see even more powerful and efficient variants of this architecture being developed, further expanding their applicability and impact across various domains. Graph neural networks, GNNs. Learning on graph-structured data. Graph neural networks, GNNs, are a class of deep learning models designed to operate on graph-structured data. Unlike traditional neural networks that process grid-like or sequential data, GNNs can handle data with complex relationships and interdependencies represented by nodes and edges in a graph. GNNs have gained significant attention in recent years due to their ability to model and learn from relational data in a wide range of applications. The fundamental idea behind GNNs is to learn node representations by aggregating information from neighboring nodes in the graph. Each node in the graph is associated with a feature vector, and the GNN updates these feature vectors iteratively by passing messages between neighboring nodes. This process is often referred to as message passing or graph convolution. In a typical GNN, each layer performs two main operations: message passing and aggregation. During message passing, each node sends a message to its neighbors, which is typically a function of its current feature vector. During aggregation, each node receives messages from its neighbors and aggregates them to update its own feature vector. This process is repeated for a fixed number of layers or until convergence. There are several variants of GNNs, which differ in how they perform message passing and aggregation. Graph convolutional networks, GCNs, are one of the most popular GNN architectures. In GCNs, the message passing operation is analogous to a convolution operation in CNNs, but adapted to graph data. The feature vector of each node is updated by taking a weighted average of the feature vectors of its neighbors, where the weights are typically determined by the graph structure and learned parameters. Graph attention networks, GATs, introduce an attention mechanism into the message passing process. Instead of using fixed weights for each neighbor, GATs learn to assign different weights to different neighbors based on their relevance to the central node. This allows the model to focus on the most important neighbors when updating the node representations. GraphSage is another popular GNN architecture that uses a more general framework for aggregating information from neighboring nodes. It allows for different types of aggregation functions, such as mean, max pooling, or LSTM-based aggregation. GraphSage also supports sampling of neighbors to handle large graphs more efficiently. GNNs can be used for various tasks on graph-structured data, including node classification, link prediction, and graph classification. In node classification, the goal is to predict a label or attribute for each node in the graph, based on its features and the features of its neighbors. In link prediction, the goal is to predict whether an edge exists between two nodes in the graph. In graph classification, the goal is to predict a label or attribute for the entire graph. GNNs have been successfully applied to a wide range of domains, including social network analysis, recommendation systems, drug discovery, and computer vision. In social network analysis, GNNs can be used to predict user attributes, classify communities, and recommend connections between users. In recommendation systems, GNNs can model the interactions between users and items as a bipartite graph and learn representations that capture the preferences of users and the properties of items. In drug discovery, GNNs can be used to model molecules as graphs, where atoms are represented as nodes and bonds as edges. GNNs can learn to predict molecular properties, such as activity, toxicity, and solubility, which can guide the search for new drugs. In computer vision, GNNs have been used for tasks such as point cloud classification, scene graph generation, and human-object interaction detection. GNNs can also be combined with other types of neural networks, such as CNNs and RNNs, to create hybrid models that can handle data with both graph structure and other types of structure, such as images or sequences. Despite their success, GNNs also face several challenges. One challenge is scalability to very large graphs, as the message passing process can be computationally expensive. Another challenge is handling dynamic graphs, where the graph structure changes over time. Developing GNN architectures that can generalize to unseen graph structures and tasks is also an active area of research. As research on GNNs continues to advance, we can expect to see even more powerful and versatile models being developed, further expanding the applicability of deep learning to graph structured data. Metalearning, learning to learn metalearning, also known as learning to learn, is a subfield of machine learning that aims to design models that can learn new skills or adapt to new environments rapidly with only a few training examples. Unlike traditional machine learning, where a model is trained from scratch for each new task, metalearning aims to leverage knowledge learned from previous tasks to improve the learning process for new, related tasks. The key idea behind metalearning is to train a model on a distribution of tasks, rather than a single task. Each task is typically associated with a small dataset, often referred to as a support set or training set, and a corresponding test set or query set. The model is trained to quickly adapt to new tasks by learning from the support set and making accurate predictions on the query set. Metalearning algorithms can be broadly categorized into three main types: recurrent models, metric-based methods, and optimization-based methods. Recurrent models, such as MetaLearner LSTM, use a recurrent neural network, RNN, to process the sequence of tasks. The RNN maintains an internal state that represents the learned knowledge about the task distribution. At each time step, the RNN receives the support set and the current task's input as input and outputs a prediction for the query set. The RNN is trained end-to-end using backpropagation through time, allowing it to learn how to update its internal state and make predictions for new tasks. Metric-based methods, such as prototypical networks and matching networks, aim to learn a metric space where classification can be performed by computing distances to prototype representations of each class. In these methods, the model learns an embedding function that maps the support set and query set into a common embedding space. The prototype for each class is computed as the mean of the embedded support set examples for that class. The query set examples are then classified based on their distance to the prototypes in the embedding space. Optimization-based methods, such as model-agnostic metalearning (MAML), frame metalearning as a bi-level optimization problem. The inner optimization loop adapts the model parameters to a new task using one or more gradient descent steps on the support set. The outer optimization loop updates the model parameters to improve the model's performance on the query set after the inner loop adaptation. MAML aims to find model parameters that are sensitive to changes in the task and can be quickly fine-tuned to new tasks with only a few gradient steps. Metalearning has been successfully applied to various domains, including few-shot image classification, reinforcement learning, and neural architecture search. In few-shot image classification, the goal is to learn a model that can classify images from new classes with only a few examples per class. Meta-learning algorithms have achieved impressive results on benchmark datasets such as Omniglot and MiniImageNet, demonstrating their ability to generalize from limited data. In reinforcement learning, meta-learning can be used to train agents that can quickly adapt to new environments or tasks. Meta-reinforcement learning algorithms learn a policy that can be efficiently fine-tuned to new tasks with only a small amount of experience. This can significantly reduce the sample complexity of reinforcement learning and enable the development of more versatile and adaptable agents. Meta-learning can also be used to automate the design of neural network architectures. In this context, the meta-learner learns to generate or modify neural network architectures that perform well on a given task or distribution of tasks. This can potentially reduce the need for manual architecture engineering and lead to the discovery of novel, high-performing architectures. Despite the successes of meta-learning, several challenges remain. One challenge is the computational cost of meta-learning algorithms, which often involve nested optimization loops or complex recurrent architectures. Another challenge is the problem of meta-overfitting, where the meta-learner overfits to the distribution of training tasks and fails to generalize to new, unseen tasks. Developing more efficient and scalable meta-learning algorithms, as well as techniques for preventing meta-overfitting, are active areas of research. Meta-learning represents a significant shift in how we approach machine learning, moving from training models from scratch for each new task to training models that can learn and adapt quickly to new tasks and environments. Transfer learning, leveraging pre-trained models. Transfer learning is a powerful technique in deep learning that involves leveraging knowledge learned from one task or domain to improve performance on a different but related task or domain. Instead of training a model from scratch for each new task, transfer learning allows us to reuse a pre-trained model as a starting point and fine-tune it for the specific task at hand. This can significantly reduce the amount of data and computational resources required to train a high-performing model, especially when the new task has limited labeled data available. The basic idea behind transfer learning is that features learned for one task can often be useful for other related tasks. For example, a model trained to classify images of objects in a large dataset like ImageNet will learn a hierarchy of visual features, from simple edges and textures in the lower layers to complex object parts and shapes in the higher layers. These learned features can be transferred to other computer vision tasks, such as object detection, image segmentation, or even tasks in different domains, such as medical image analysis. Transfer learning typically involves two main steps: pre-training and fine-tuning. In the pre-training step, a model is trained on a large source task or dataset, often referred to as the pre-training task or dataset. This step allows the model to learn a rich set of features that are generally useful for the domain. In the fine-tuning step, the pre-trained model is adapted to the target task by continuing the training process on the target dataset. The weights of the pre-trained model are used as the initialization for the fine-tuning process, and some or all of the layers may be updated during training. There are several strategies for fine-tuning a pre-trained model. One common approach is to freeze the weights of the lower layers of the network, which have learned more general features, and only update the weights of the higher layers, which are more specific to the target task. This can help to prevent overfitting when the target dataset is small. Another approach is to use a smaller learning rate for the pre-trained layers compared to the newly added layers. This allows the pre-trained weights to be gently adapted to the target task while preserving the knowledge learned from the source task. Transfer learning has been successfully applied in various domains, including computer vision, natural language processing, and speech recognition. In computer vision, models pre-trained on ImageNet, such as VGG, ResNet, and Inception, have become widely used starting points for many tasks. By fine-tuning these models on smaller, task-specific datasets, researchers and practitioners have achieved state-of-the-art results on tasks such as object detection, image segmentation, and facial recognition. In natural language processing, pre-trained language models, such as BERT and GPT, have revolutionized the field. These models are trained on massive text corpora using self-supervised learning objectives, such as masked language modeling or next sentence prediction. The pre-trained models capture rich syntactic and semantic information about language and can be fine-tuned for various downstream tasks, such as text classification, question answering, and named entity recognition, often with significantly less labeled data than would be required to train a model from scratch. Transfer learning is not limited to transferring knowledge between similar tasks within the same domain. Cross-domain transfer learning aims to leverage knowledge from a source domain to improve performance in a different target domain. For example, a model trained on natural images might be fine-tuned for a medical imaging task, or a model trained on text in one language might be adapted to a different language. Despite the success of transfer learning, several challenges remain. One challenge is negative transfer, which can occur when the source and target tasks are too dissimilar, and the knowledge learned from the source task does not help or even hurts performance on the target task. Another challenge is determining which layers to freeze or fine-tune and how to set the learning rates for different layers. Developing more principled and automated methods for transfer learning is an active area of research. Techniques such as meta-learning and domain adaptation are being explored to improve the effectiveness and efficiency of transfer learning. Transfer learning has become a cornerstone of modern deep learning practice. By enabling the reuse of pre-trained models and the transfer of knowledge across tasks and domains, it has significantly reduced the data and computational requirements for building high-performing models and has expanded the applicability of deep learning to a wider range of problems. Hybrid architectures, combining the strengths of different models. Hybrid deep learning architectures combine different types of neural network models to leverage their complementary strengths and create more powerful and versatile systems. These architectures often integrate components such as convolutional neural networks, CNNs, recurrent neural networks, RNNs, and attention mechanisms to handle complex data and tasks that require multiple types of processing. One common type of hybrid architecture combines CNNs and RNNs for tasks that involve both spatial and temporal dependencies. For example, in video action recognition, a CNN can be used to extract spatial features from individual frames, while an RNN can be used to model the temporal dynamics of the action across frames. The CNN and RNN can be trained jointly, allowing the model to learn how to extract and combine spatial and temporal information for accurate action recognition. Another example of a hybrid architecture is the combination of CNNs and attention mechanisms for image captioning. In this task, the model generates a natural language description of an image. A CNN is used to extract visual features from the image, and an RNN with an attention mechanism is used to generate the caption. The attention mechanism allows the RNN to focus on different regions of the image when generating each word in the caption, improving the accuracy and coherence of the generated descriptions. Neurosymbolic models are another type of hybrid architecture that combines deep neural networks with symbolic reasoning. These models aim to bridge the gap between the statistical learning capabilities of deep networks and the interpretability and reasoning abilities of symbolic systems. Neurosymbolic models typically use neural networks to process raw input data and generate a symbolic representation, which is then manipulated using logical rules or symbolic algorithms. The output of the symbolic reasoning component can then be used to guide the learning process of the neural network or to make final predictions. For example, a neurosymbolic model for visual question answering might use a CNN to extract visual features from an image and an RNN to process a natural language question. The outputs of the CNN and RNN could then be combined to generate a symbolic representation of the scene and the question, which is then processed using a symbolic reasoning engine to answer the question. Hybrid architectures can also involve combining deep learning models with other types of machine learning models, such as probabilistic graphical models or decision trees. For example, a deep learning model can be used to extract features from raw data, and these features can then be used as input to a probabilistic graphical model that captures the dependencies between different variables. This can combine the representation learning power of deep networks with the ability of graphical models to represent structured knowledge and perform probabilistic inference. Another trend in hybrid architectures is the combination of generative and discriminative models. For example, a variational autoencoder, VAE, or a generative adversarial network, GAN, can be used to learn a generative model of the data, and the learned latent representations or generated samples can then be used to train a discriminative model, such as a classifier or a regressor. This can improve the performance of the discriminative model, particularly when labeled data is scarce. Hybrid architectures offer several advantages over using a single type of model. They can leverage the strengths of different models to handle complex data and tasks that require multiple types of processing. They can also incorporate different types of inductive biases and constraints, which can improve generalization and learning efficiency. However, designing and training hybrid architectures can be challenging. It often requires careful consideration of how to integrate the different components, how to train them jointly or separately, and how to balance their respective contributions to the overall model. Despite these challenges, hybrid architectures represent an important direction in deep learning research and have the potential to lead to more powerful, versatile, and interpretable models. Inductive biases. Guiding learning with architectural constraints. Inductive biases refer to the set of assumptions or constraints that are built into a machine learning model to guide the learning process and influence the types of solutions it can learn. In deep learning, inductive biases are often incorporated through the choice of network architecture, activation functions, and other design choices. These biases can help to improve generalization, learning efficiency, and interpretability by encoding prior knowledge or assumptions about the structure of the data or the task. Convolutional neural networks, CNNs, are a prime example of how inductive biases can be incorporated into a network architecture. CNNs are designed with the assumption that spatial locality and translation invariance are important for processing image data. The use of convolutional filters that operate on local receptive fields and are shared across the entire image encodes the inductive bias that local patterns are important and that the same features can occur at different locations in the image. Pooling layers further reinforce this bias by providing a degree of translation invariance. Recurrent neural networks, RNNs, incorporate the inductive bias that sequential order matters in temporal data. The recurrent connections in RNNs allow the network to maintain an internal state that summarizes the past information in the sequence, and the hidden state is updated at each time step based on the current input and the previous hidden state. This sequential processing bias enables RNNs to capture temporal dependencies in the data. Attention mechanisms, such as those used in transformers, provide a way to incorporate the inductive bias that certain parts of the input are more relevant than others for making a prediction. By learning to attend to specific elements in the input sequence or specific regions in an image, attention mechanisms can improve the model's ability to focus on the most important information and ignore irrelevant details. Graph neural networks, GNNs, encode the inductive bias that relationships between entities are important. By operating on graph-structured data and using message passing between neighboring nodes, GNNs can learn representations that capture the relational structure of the data. This is particularly useful for tasks that involve reasoning about relationships, such as social network analysis, recommendation systems, and knowledge graph reasoning. The choice of activation function can also introduce inductive biases. The ReLU activation function, for example, introduces a bias toward sparsity by setting negative values to 0. This can help to improve the efficiency and interpretability of the learned representations. Inductive biases can also be incorporated through the use of specific training procedures or regularization techniques. For example, data augmentation, which involves applying transformations such as rotations, flips, or crops to the input data, can be seen as a way of encoding the inductive bias that these transformations do not change the underlying class or meaning of the data. Regularization techniques, such as L1 or L2 regularization, introduce biases toward simpler models by penalizing large weights or encouraging sparsity. The choice of inductive biases is crucial for the success of a deep learning model. Strong inductive biases that are aligned with the structure of the data and the task can significantly improve generalization and learning efficiency. However, if the inductive biases are incorrect or too strong, they can limit the model's ability to learn the true underlying patterns in the data. Finding the right balance between incorporating useful inductive biases and maintaining the flexibility to learn from data is a key challenge in deep learning research. Capsule networks, learning hierarchical representations with capsules. Capsule networks, CapsNets, are a relatively recent development in deep learning that aim to address some of the limitations of convolutional neural networks, CNNs, in learning hierarchical representations of data. CapsNets were introduced by Geoffrey Hinton and colleagues in 2017 and have since generated significant interest in the research community. The key idea behind CapsNets is to replace the scalar output neurons in traditional neural networks with vector output capsules. A capsule is a group of neurons whose activity vector represents the instantiation parameters of a specific type of entity, such as an object or a part of an object. The length of the activity vector represents the probability that the entity exists, and the orientation of the vector represents the properties of the entity, such as its pose, texture, and deformation. In a CapsNet, lower-level capsules make predictions, called votes, for the instantiation parameters of higher-level capsules. These votes are computed by multiplying the output of the lower-level capsule by a learned weight matrix that represents the spatial relationship between the lower-level and higher-level entities. The votes are then routed to the higher-level capsules using a dynamic routing algorithm, which iteratively updates the coupling coefficients between capsules based on the agreement between their votes. The dynamic routing algorithm is a key component of CapsNets. It ensures that the output of a capsule is sent to the appropriate parent capsule in the higher layer. The coupling coefficients between a capsule and its potential parent capsules are determined by a routing softmax, which ensures that the coefficients sum to 1. The routing process involves multiple iterations, where the coupling coefficients are updated based on the dot product between the current output of the capsule and the votes from the lower-level capsules. This allows the network to learn hierarchical part-whole relationships between entities. CapsNets have several potential advantages over traditional CNNs. By using vector outputs instead of scalar outputs, capsules can represent more information about the properties of an entity and its relationships to other entities. This can improve the network's ability to handle variations in viewpoint, lighting, and deformation. CapsNets have also been shown to be more robust to adversarial examples than CNNs. The dynamic routing mechanism in CapsNets can be seen as a form of attention, where the network learns to attend to the relevant lower-level capsules when activating higher-level capsules. This can improve the interpretability of the network and provide insights into the hierarchical structure of the data. CapsNets have been applied to various tasks, including image classification, object detection, and image segmentation. On the NIST dataset of handwritten digits, CapsNets have achieved state-of-the-art results, demonstrating their ability to learn robust and generalizable representations. They have also been shown to perform well on more complex datasets, such as small NORB, which contains images of 3D objects with variations in viewpoint and lighting. Despite their potential advantages, CapsNets also have some limitations. The dynamic routing algorithm can be computationally expensive, especially for networks with many layers and capsules. Training CapsNets can also be more challenging than training CNNs, requiring careful tuning of hyperparameters and optimization algorithms. Research on CapsNets is still in its early stages, and many aspects of their behavior and performance are not yet fully understood. However, they represent an interesting and promising direction in deep learning research, particularly for tasks that require learning hierarchical representations and reasoning about part-whole relationships. Neural Architecture Search, NAS. Automating the design of neural networks. Neural Architecture Search, NAS, is an emerging field in deep learning that aims to automate the process of designing neural network architectures. Traditionally, designing neural network architectures has been a manual process that relies on human expertise and intuition. This can be time-consuming, labor-intensive, and may not always lead to optimal architectures. NAS seeks to automate this process by using algorithms to search for high-performing architectures within a defined search space. The basic idea behind NAS is to define a search space of possible architectures, a search algorithm to explore the space, and a performance estimation strategy to evaluate the performance of different architectures. The search space defines the set of all possible architectures that can be generated by the NAS algorithm. It is typically defined by a set of building blocks, such as different types of layers, e.g., convolutional, pooling, fully connected, activation functions, and connectivity patterns, and a set of rules for combining these blocks to form valid architectures. The search algorithm explores the search space to find architectures that perform well on a given task. Several search algorithms have been used in NAS, including reinforcement learning, evolutionary algorithms, Bayesian optimization, and gradient-based methods. Reinforcement learning-based NAS methods train an agent, typically an RNN, to generate architectures by sequentially selecting building blocks and connections. The agent is trained using policy gradient methods to maximize the expected performance of the generated architectures on a validation set. Evolutionary algorithms maintain a population of architectures and evolve them over time using operations such as mutation and crossover. The performance of each architecture is evaluated, and the best performing architectures are selected to produce the next generation. Bayesian optimization methods model the performance of architectures as a function of their design choices and use this model to guide the search process. They typically use a probabilistic surrogate model, such as a Gaussian process, to represent the performance function and an acquisition function to select the next architecture to evaluate. Gradient-based methods use gradient information to optimize the architecture parameters. One popular gradient-based method is differentiable architecture search, DARTS, which relaxes the discrete search space into a continuous space by introducing continuous architecture parameters that represent the probability of selecting each building block or connection. DARTS then jointly optimizes the architecture parameters and the network weights using gradient descent. The performance estimation strategy is a crucial component of NAS. Evaluating the true performance of an architecture typically requires training it from scratch on the target dataset, which can be computationally expensive. To reduce the computational cost, various performance estimation strategies have been proposed, such as using lower fidelity estimates, e.g., training for fewer epochs or on a smaller dataset, weight sharing, e.g., training a single large network that contains all possible architectures as subnetworks, and learning curve prediction. NAS has been successfully applied to various domains, including image classification, object detection, and semantic segmentation. NAS algorithms have discovered architectures that outperform manually designed architectures on benchmark datasets such as CIFAR, 10 and ImageNet. Despite the success of NAS, several challenges remain. One major challenge is the computational cost of searching for architectures, which can require thousands of GPU days for some methods. Another challenge is the transferability of architectures found on one task or dataset to other tasks or datasets. Developing more efficient and scalable NAS algorithms, as well as methods for transferring architectures across tasks and domains, are active areas of research. NAS represents a significant step towards automating the design of deep learning models and has the potential to accelerate progress in the field by reducing the reliance on manual architecture engineering. Lesson 10: Ethical Considerations and Future Directions in Deep Learning. Ethical considerations in deep learning, bias, fairness, and accountability. As deep learning becomes increasingly integrated into various aspects of society, it is crucial to consider the ethical implications of this technology. Deep learning models can perpetuate and amplify existing biases in data, leading to unfair or discriminatory outcomes. They can also raise concerns about privacy, transparency, and accountability. One of the primary ethical concerns in deep learning is bias. Deep learning models are trained on large datasets, which may reflect existing societal biases. If the training data contains biased representations of certain groups, the model may learn and perpetuate these biases in its predictions. For example, facial recognition systems have been shown to be less accurate for individuals with darker skin tones, likely due to underrepresentation of these groups in the training data. Similarly, natural language processing models trained on large text corpora have been found to exhibit gender and racial biases, reflecting the biases present in the text data. These biases can have real-world consequences when these models are deployed in applications such as hiring, loan applications, and criminal justice. Fairness is a related but distinct concept that refers to the equitable treatment of different groups by an AI system. A fair model should not systematically disadvantage certain groups based on sensitive attributes such as race, gender, or religion. Several definitions of fairness have been proposed in the literature, such as demographic parity, equal opportunity, and equalized odds. However, it has been shown that it is often impossible to satisfy all fairness criteria simultaneously, and trade-offs must be made. Addressing bias and fairness in deep learning requires careful consideration of the entire pipeline, from data collection and preprocessing to model training and evaluation. Techniques such as data augmentation, resampling, and reweighting can be used to mitigate biases in the training data. Fairness-aware algorithms have also been developed that incorporate fairness constraints or objectives into the learning process. Another important ethical consideration is transparency and accountability. Deep learning models, particularly complex ones with millions of parameters, are often considered black boxes due to their lack of interpretability. This can make it difficult to understand how a model arrived at a particular decision, which can be problematic in applications where accountability and trust are important. Explainable AI, XAI, techniques, as discussed in Lesson 8, aim to address this issue by providing insights into the decision-making process of deep learning models. However, developing methods for ensuring transparency and accountability in deep learning remains an active area of research. Privacy is another major concern, particularly when deep learning models are trained on sensitive personal data, such as medical records or financial data. Techniques such as federated learning, where models are trained in a decentralized manner across multiple devices or institutions without sharing the raw data, can help to address privacy concerns. Differential privacy, which adds noise to the data or the model's parameters to provide formal privacy guarantees, is another approach for training deep learning models while preserving privacy. The ethical considerations in deep learning are complex and multifaceted, and there are often trade-offs between different values, such as accuracy, fairness, and privacy. Addressing these challenges requires interdisciplinary collaboration between computer scientists, ethicists, policymakers, and domain experts. It is also crucial to involve stakeholders and affected communities in the development and deployment of AI systems to ensure that their values and concerns are taken into account. Societal impact of deep learning, benefits, risks, and responsible development. Deep learning has the potential to bring about significant benefits to society, but it also poses risks if not developed and deployed responsibly. Understanding the societal impact of deep learning is crucial for maximizing its positive contributions while mitigating potential harms. One of the major benefits of deep learning is its ability to automate complex tasks and improve efficiency across various domains. In healthcare, for example, deep learning can assist in medical diagnosis, drug discovery, and personalized medicine. Deep learning models can analyze medical images, such as X-rays and MRIs, to detect anomalies and assist in the early diagnosis of diseases. They can also analyze patient data to predict the risk of developing certain conditions and recommend personalized treatment plans. In transportation, deep learning is enabling the development of self-driving cars, which have the potential to improve road safety, reduce traffic congestion, and increase accessibility for people with disabilities. Deep learning models can process data from various sensors, such as cameras, LiDAR, and radar, to perceive the environment, make driving decisions, and navigate complex scenarios. In finance, deep learning can be used for fraud detection, risk assessment, and algorithmic trading. Deep learning models can analyze large volumes of financial data to identify patterns and anomalies that may indicate fraudulent activity. They can also be used to assess credit risk and make more accurate predictions about market movements. Deep learning can also contribute to scientific discovery by accelerating the analysis of large datasets in fields such as astronomy, genomics, and materials science. For example, deep learning models have been used to analyze telescope images to identify and classify galaxies, to analyze genomic data to predict the function of genes, and to design new materials with specific properties. Despite these potential benefits, deep learning also poses several risks. One concern is the potential for job displacement due to automation. As deep learning models become more capable of performing tasks that were previously carried out by humans, there is a risk that jobs in certain sectors may be automated, leading to unemployment and social disruption. Another risk is the potential for deep learning to exacerbate existing inequalities. If the benefits of deep learning are not distributed equitably, there is a risk that the technology could widen the gap between the rich and the poor, or between different demographic groups. For example, if access to deep learning-powered healthcare is limited to those who can afford it, it could worsen health disparities. The use of deep learning in surveillance and security applications also raises concerns about privacy and civil liberties. Facial recognition systems, for example, can be used for mass surveillance and may disproportionately impact certain communities. It is important to carefully consider the ethical implications of these technologies and to put in place appropriate safeguards and regulations to prevent misuse. The development of autonomous weapons systems that use deep learning to select and engage targets without human intervention is another area of concern. These systems raise ethical and legal questions about accountability, the potential for unintended harm, and the risk of an AI arms race. To ensure that deep learning is developed and deployed responsibly, it is crucial to adopt a multi-stakeholder approach that involves researchers, developers, policymakers, ethicists, and the wider public. This includes promoting research on the societal impact of AI, developing ethical guidelines and best practices, and fostering public dialogue and engagement on these issues. It is also important to invest in education and training to prepare the workforce for the changes that deep learning may bring and to ensure that the benefits of the technology are shared broadly. Promoting diversity and inclusion in the field of deep learning is also crucial for ensuring that the technology reflects the values and needs of all members of society. A more diverse and inclusive workforce can help to identify and mitigate biases, develop more equitable and fair AI systems, and ensure that the benefits of deep learning are accessible to everyone. Emerging trends in deep learning, frontiers of research and development. Deep learning is a rapidly evolving field, with new research directions and trends constantly emerging. Staying abreast of these developments is crucial for researchers, practitioners, and anyone interested in the future of artificial intelligence. One major trend in deep learning is the development of more efficient and scalable models. As deep learning models become larger and more complex, there is a growing need for techniques that can reduce their computational and memory requirements. Model compression techniques, such as pruning and quantization, aim to reduce the size of deep learning models without significantly sacrificing performance. Pruning involves removing redundant or less important connections in the network, while quantization involves reducing the precision of the weights and activations. Another approach to improving efficiency is the development of specialized hardware for deep learning, such as tensor processing units, TPUs, and other AI accelerators. These custom-designed chips can perform deep learning computations much faster and with lower power consumption than general-purpose CPUs and GPUs. Another important trend is the development of deep learning models that can learn from less labeled data. Supervised deep learning typically requires large amounts of labeled data, which can be expensive and time-consuming to obtain. Techniques such as semi-supervised learning, self-supervised learning, and transfer learning aim to reduce the reliance on labeled data by leveraging unlabeled data or knowledge from related tasks. Self-supervised learning, in particular, has gained significant attention in recent years. In self-supervised learning, a model is trained on an auxiliary task that can be created from unlabeled data itself, such as predicting missing parts of an image or the next word in a sentence. By learning to solve this auxiliary task, the model learns useful representations of the data that can then be fine-tuned for a downstream task with limited labeled data. Another emerging trend is the development of deep learning models that are more robust and reliable. Deep learning models have been shown to be vulnerable to adversarial examples, which are inputs that are specifically designed to fool the model. They can also be sensitive to small changes in the input or to shifts in the data distribution. Developing methods for improving the robustness of deep learning models and for detecting and mitigating adversarial attacks is an active area of research. Techniques such as adversarial training, input transformations, and model ensembling have been explored to improve robustness. Another important research direction is the development of deep learning models that are more interpretable and explainable. As deep learning models are increasingly used in high-stakes applications, it is crucial to understand how they arrive at their decisions and to be able to justify their predictions. Explainable AI, XAI, techniques, such as attention mechanisms, saliency maps, and model-agnostic methods like LIME and SHAP, are being developed to provide insights into the decision-making process of deep learning models. The integration of deep learning with other areas of artificial intelligence, such as symbolic reasoning and probabilistic programming, is another emerging trend. Neurosymbolic models, for example, aim to combine the strengths of deep learning and symbolic AI by incorporating logical reasoning and prior knowledge into deep learning systems. This can potentially lead to models that are more interpretable, robust, and data efficient. Finally, the development of deep learning models that can learn continuously and adapt to new tasks and environments over time is a major research direction. Lifelong learning or continual learning aims to create models that can accumulate knowledge over time, without forgetting previously learned information, and can adapt to changing conditions and requirements. These are just a few of the many exciting research directions in deep learning. Deep learning on the edge, deploying models on resource-constrained devices. Deploying deep learning models on edge devices, such as smartphones, embedded systems, and IoT devices, presents unique challenges and opportunities. Edge devices often have limited computational resources, memory, and power compared to cloud servers or high-performance computing clusters. This requires the development of efficient and lightweight deep learning models and specialized techniques for on-device inference. One approach to enabling deep learning on the edge is model compression. Techniques such as pruning, quantization, and knowledge distillation can significantly reduce the size and computational requirements of deep learning models without sacrificing too much accuracy. Pruning involves removing redundant or less important connections in the network, reducing the number of parameters and computations. Quantization involves reducing the precision of the weights and activations, for example, from 32-bit floating point to 8-bit integer representations. This can reduce the memory footprint and speed up computations, particularly on hardware that supports low-precision arithmetic. Knowledge distillation is a technique where a smaller, more efficient student model is trained to mimic the behavior of a larger, more accurate teacher model. The student model learns from the soft targets, i.e., the output probabilities, produced by the teacher model, which can provide more information than training on the hard labels alone. Another approach is to design neural network architectures that are specifically tailored for resource-constrained devices. Mobile nets, for example, are a family of efficient convolutional neural networks that use depthwise separable convolutions to reduce the number of parameters and computations compared to standard convolutions. Shuffle nets and efficient nets are other examples of architectures that are designed for efficiency and have shown strong performance on mobile and embedded devices. Hardware acceleration is also crucial for enabling deep learning on the edge. Specialized hardware, such as mobile GPUs, neural processing units, NPUs, and field programmable gate arrays, FPGAs, can significantly speed up deep learning inference on resource-constrained devices. These accelerators often support low-precision arithmetic and have specialized circuits for performing common deep learning operations, such as convolutions and matrix multiplications. Another important consideration for deploying deep learning on the edge is the trade-off between on-device processing and cloud offloading. In some applications, it may be more efficient to perform some or all of the computations in the cloud, particularly if the model is too large or computationally intensive to run on the device. However, this requires sending data to the cloud and receiving results back, which can introduce latency and raise privacy concerns. Federated learning is an emerging approach that allows deep learning models to be trained on decentralized data residing on edge devices without the need to share the raw data with a central server. In federated learning, each device trains a local model on its own data, and only the model updates, e.g., gradients or weights, are sent to a central server. The central server aggregates the updates from multiple devices to improve a global model, which is then sent back to the devices for further training. This approach can help to preserve privacy and reduce communication overhead. Deploying deep learning models on edge devices also requires careful consideration of factors such as power consumption, thermal management, and real-time performance. Optimizing deep learning models for specific hardware platforms and using techniques such as model caching and pipelining can help to improve efficiency and reduce latency. The deployment of deep learning on the edge is a rapidly growing area, driven by the increasing availability of powerful edge devices and the demand for intelligent applications that can operate in real time and with limited connectivity. Quantum machine learning. Exploring the intersection of quantum computing and deep learning. Quantum machine learning is an emerging field that explores the intersection of quantum computing and machine learning, including deep learning. It aims to leverage the unique capabilities of quantum computers to enhance machine learning algorithms and potentially solve problems that are intractable for classical computers. Quantum computers use the principles of quantum mechanics to perform computations in a fundamentally different way than classical computers. They operate on quantum bits, or qubits, which can exist in a superposition of 0 and 1 states, and can be entangled with each other. This allows quantum computers to perform certain computations exponentially faster than classical computers, at least in theory. One of the key challenges in quantum machine learning is to develop quantum algorithms that can provide a speed-up or other advantage over classical machine learning algorithms. Several quantum machine learning algorithms have been proposed, including quantum versions of support vector machines, principal component analysis, and k-means clustering. These algorithms often rely on quantum subroutines, such as the quantum Fourier transform and quantum matrix inversion, which can be performed more efficiently on a quantum computer than on a classical computer. In the context of deep learning, researchers are exploring how quantum computing can be used to enhance various aspects of neural networks. One approach is to use quantum circuits to implement specific layers or operations within a neural network. For example, a quantum convolutional neural network might use quantum circuits to perform the convolution operation, potentially offering a speed-up over classical implementations. Another approach is to use quantum computers to train classical neural networks more efficiently. For example, quantum annealing, a technique for finding the global minimum of a function using quantum fluctuations, could potentially be used to optimize the weights of a neural network. Quantum generative models are another active area of research. These models aim to learn a quantum circuit that can generate samples from a probability distribution that approximates the distribution of the training data. Quantum versions of generative adversarial networks, GANs, and variational autoencoders, VAEs, have been proposed. Despite the potential of quantum machine learning, there are significant challenges that need to be addressed. Current quantum computers are still in their early stages of development, with limited numbers of qubits and high error rates. Building fault-tolerant, large-scale quantum computers is a major technological challenge. Another challenge is the development of quantum machine learning algorithms that can provide a clear advantage over classical algorithms for real-world problems. While some quantum algorithms offer theoretical speedups, it is often unclear whether these speedups will translate into practical advantages, given the current state of quantum hardware and the overhead associated with encoding classical data into quantum states. The field of quantum machine learning is still in its infancy, and many open questions remain. However, it is a rapidly growing area of research that holds significant promise for the future of both quantum computing and artificial intelligence. As quantum computers continue to improve and new quantum machine learning algorithms are developed, we may see quantum machine learning enabling new capabilities and applications that are beyond the reach of classical machine learning alone. Lesson 11, Advanced Convolutional Neural Networks. Introduction to Advanced CNN Architectures. Convolutional neural networks, CNNs, have been a driving force behind many of the recent advances in computer vision. Since the success of AlexNet in 2012, researchers have developed increasingly sophisticated and powerful CNN architectures that have pushed the boundaries of what's possible in image classification, object detection, segmentation, and other related tasks. These advanced CNN architectures often build upon the fundamental principles of earlier models but introduce novel concepts and designs to improve performance, efficiency, and robustness. One major trend in advanced CNN architectures is the exploration of network depth. While early CNNs like LeNet-5 had only a few layers, models like VGGNet and ResNet demonstrated the benefits of using much deeper networks, with tens or even hundreds of layers. However, simply increasing the depth of a network does not always lead to improved performance. Training very deep networks can be challenging due to issues like vanishing gradients and optimization difficulties. Advanced architectures like ResNet and DenseNet introduce techniques such as skip connections and dense connections to address these challenges and enable the training of very deep networks. Another trend is the development of architectures that can capture multiscale information more effectively. Inception networks, for example, use modules with multiple parallel convolutional filters of different sizes to capture features at different scales. This allows the network to learn a richer and more diverse set of features, improving performance on tasks that involve objects of varying sizes and scales. The design of more efficient CNN architectures has also become an important area of research, particularly for applications where computational resources are limited, such as mobile devices and embedded systems. Models like MobileNets and ShuffleNets use techniques such as depthwise separable convolutions and group convolutions to reduce the number of parameters and computations while maintaining high accuracy. SqueezeNet introduced the FIRE module to reduce the number of parameters by using 1x1 convolutions to squeeze the number of channels before applying more expensive 3x3 convolutions. Attention mechanisms have also been incorporated into CNN architectures to improve their ability to focus on the most relevant parts of the input. Squeeze-and excitation networks, SENETs, for example, introduce a channel attention mechanism that allows the network to recalibrate the feature maps by modeling the interdependencies between channels. CBAM, Convolutional Block Attention Module, extends this idea by combining both channel and spatial attention mechanisms. Another important direction in advanced CNN architectures is the development of models that are more robust to variations and perturbations in the input. Adversarial training, which involves training the network on adversarial examples, can improve the robustness of CNNs to small, carefully crafted perturbations. Other techniques, such as defensive distillation and input transformations, have also been explored to improve robustness. The field of CNN architecture design is rapidly evolving, with new models and techniques being proposed regularly. Neural Architecture Search, NAS, has emerged as a promising approach for automating the design of CNN architectures, potentially leading to the discovery of novel architectures that outperform hand-designed ones. As research on advanced CNN architectures continues, we can expect to see even more powerful, efficient, and robust models being developed, further expanding the capabilities of deep learning in computer vision and other domains. ResNet and Residual Learning, Enabling Very Deep Networks. ResNet, short for Residual Network, is a groundbreaking CNN architecture that was introduced by He et al. In 2015. ResNet addressed the challenge of training very deep neural networks by introducing the concept of residual learning. It quickly became one of the most influential and widely used architectures in computer vision, achieving state-of-the-art results on various benchmarks and winning the ImageNet Large-Scale Visual Recognition Challenge, ILSVRC, in 2015. The key innovation in ResNet is the use of residual blocks, which incorporate skip connections, also known as shortcut connections, that bypass one or more layers. In a standard feed-forward network, each layer feeds its output directly to the next layer. In a residual block, the output of a layer is added to the input of the block, creating a shortcut path. This can be expressed as h, x, equals f, x, plus x, where x is the input to the block, f, x, is the output of the layers in the block, and h, x, is the output of the block. The intuition behind residual learning is that it is easier to optimize the residual mapping f, x, equals h, x, x than to optimize the original, unreferenced mapping h, x. In the extreme case, if an identity mapping were optimal, it would be easier to push the residual f, x, to 0 than to fit an identity mapping by a stack of nonlinear layers. The skip connections in ResNet help to mitigate the vanishing gradient problem that can occur when training very deep networks. By providing a direct path for the gradient to flow during backpropagation, skip connections allow for more effective training of deep networks. They also enable the network to learn identity mappings more easily, which can be useful in cases where adding more layers does not improve performance. ResNet architectures are typically composed of multiple residual blocks, each consisting of 2 or 3 convolutional layers with batch normalization and ReLU activations. The most common ResNet variants have depths ranging from 18 to 152 layers, with deeper models generally achieving better performance. One important design choice in ResNet is the use of downsampling to reduce the spatial dimensions of the feature maps and increase the number of channels as the network gets deeper. This is typically done using strided convolutions or pooling layers. Another key aspect of ResNet is the use of global average pooling at the end of the network, followed by a fully connected layer for classification. This reduces the number of parameters compared to using multiple fully connected layers and helps to prevent overfitting. ResNet has been successfully applied to a wide range of computer vision tasks, including image classification, object detection, and semantic segmentation. Its ability to enable the training of very deep networks has significantly advanced the state-of-the-art in these areas. The concept of residual learning has also been adopted in other types of neural networks, such as recurrent neural networks and graph neural networks, demonstrating its generality and effectiveness. Since the introduction of ResNet, several variants and improvements have been proposed. ResNeXT introduces the concept of cardinality, which refers to the number of independent paths within a residual block. By increasing the cardinality instead of just increasing the depth or width, ResNeXT achieves better performance with a similar number of parameters. Wide residual networks, WRNs, explore the trade-off between depth and width in residual networks. WRNs show that increasing the width of residual blocks can be more effective than increasing their depth, leading to improved performance and faster training. Other variants, such as ResNet with squeeze-an excitation blocks, SEResNet, and stochastic depth ResNets, have also been proposed to further improve the performance and efficiency of ResNet architectures. ResNet and the concept of residual learning have had a profound impact on the field of deep learning, enabling the training of much deeper networks than previously possible and significantly advancing the state-of-the-art in computer vision. Inception and multi-scale processing, capturing features at different resolutions. Inception networks, also known as GoogleNet, are a class of CNN architectures that were introduced by Segedie et al. In 2014. Inception networks were among the first to demonstrate the effectiveness of using multiple filter sizes within a single layer to capture features at different scales. This multi-scale processing approach has become a key design principle in many subsequent CNN architectures. The core building block of inception networks is the inception module. An inception module consists of multiple parallel convolutional filters of different sizes, e.g., 1 by 1, 3 by 3, 5 by 5, applied to the same input, along with a pooling operation. The outputs of these parallel branches are then concatenated along the channel dimension to form the output of the module. The intuition behind the inception module is that different filter sizes can capture different types of features at different scales. For example, a 1 by 1 convolution can capture pointwise features, a 3 by 3 convolution can capture local patterns within a small neighborhood, and a 5 by 5 convolution can capture larger patterns. By using multiple filter sizes in parallel, the inception module can learn a richer and more diverse set of features compared to using a single filter size. The use of 1 by 1 convolutions in the inception module, also known as pointwise convolutions, is another important design choice. 1 by 1 convolutions are applied before the more computationally expensive 3 by 3 and 5 by 5 convolutions to reduce the number of input channels, thus reducing the computational cost. They can also be seen as learning a linear combination of the input channels, allowing the network to learn more complex features with fewer parameters. Inception networks are typically composed of multiple inception modules stacked on top of each other, with occasional pooling layers to reduce the spatial dimensions of the feature maps. The original GoogleNet architecture, which won the ILSVRC 2014 competition, had 22 layers and used 9 inception modules. One of the challenges in designing inception networks is the increased number of hyperparameters, such as the number of filters of each size in each inception module. The original GoogleNet architecture used handcrafted inception modules based on empirical results and intuition. Subsequent work has explored more systematic ways of designing inception modules, including using reinforcement learning and other optimization techniques to automatically search for optimal configurations. Inception networks have achieved strong performance on various computer vision tasks, including image classification, object detection, and semantic segmentation. Their ability to capture multi-scale information has made them particularly effective for tasks that involve objects of varying sizes and scales. Since the introduction of the original Inception network, several variants have been proposed, such as Inception v3, Inception v4, and Inception ResNet. These variants introduce various improvements and refinements to the Inception module and the overall network architecture. For example, Inception v3 introduces factorization of the larger convolutions into smaller ones, e.g., replacing a 5 by 5 convolution with two 3 by 3 convolutions, to reduce the computational cost. Inception ResNet combines the Inception module with residual connections, similar to ResNet, to enable the training of even deeper networks. Inception, Extreme Inception, is another variant that takes the idea of multi-scale processing to the extreme. It replaces the Inception module with depthwise separable convolutions, which apply a single convolutional filter to each input channel separately, followed by a pointwise convolution to combine the outputs. This can be seen as a special case of the Inception module where the number of parallel branches is equal to the number of input channels. Inception networks and the concept of multi-scale processing have had a significant impact on the field of computer vision, influencing the design of many subsequent CNN architectures and advancing the state-of-the-art on various tasks. DenseNet and connectivity patterns, promoting feature reuse. DenseNet, short for Densely Connected Convolutional Network, is a CNN architecture that was introduced by Huang et al. In 2017. DenseNet takes the idea of skip connections, as used in ResNet, to the extreme by connecting each layer to every other layer in a feed-forward fashion within a dense block. This dense connectivity pattern encourages feature reuse, improves gradient flow, and reduces the number of parameters, leading to more efficient and accurate models. In a dense net, each layer receives the feature maps from all preceding layers as input. Specifically, the input to the LTH layer consists of the feature maps produced by layers 0, 1, L1. These feature maps are concatenated along the channel dimension to form the input to the LTH layer. This can be expressed as x sub L slash sub equals h sub L slash sub x sub 0 a slash sub x sub 1 slash sub comma x sub L 1 slash sub, where x sub L slash sub is the output of the LTH layer, h sub L slash sub is a composite function consisting of operations such as convolution, batch normalization, and ReLU, and x sub 0 slash sub x sub 1 slash sub comma x sub L 1 slash sub denotes the concatenation of the feature maps from layers 0, 1, L1. The key idea behind DenseNet is that by directly connecting each layer to all preceding layers, the network can reuse features learned in earlier layers and build upon them to learn more complex features. This promotes feature reuse and reduces the need to relearn redundant features, making the network more parameter efficient. The dense connectivity pattern also improves the flow of gradients during backpropagation. Each layer has direct access to the gradients from the loss function, as well as from all subsequent layers. This helps to alleviate the vanishing gradient problem and enables the training of very deep networks. Dense nets are typically composed of multiple dense blocks, where each block consists of several layers with dense connections. Between the dense blocks, transition layers are used to reduce the spatial dimensions of the feature maps and control the number of channels. A transition layer typically consists of a 1x1 convolution followed by a 2x2 average pooling operation. One of the remarkable properties of DenseNet is that it achieves high accuracy with significantly fewer parameters compared to other state-of-the-art architectures, such as ResNet. This is due to the feature reuse encouraged by the dense connectivity pattern, which reduces the need to learn redundant features and allows the network to be more compact. Dense nets have been shown to be particularly effective in the presence of limited training data, as the dense connections act as a form of implicit regularization. Dense nets have achieved strong performance on various computer vision tasks, including image classification, object detection, and semantic segmentation. They have also been applied to other domains, such as medical image analysis and natural language processing. Since the introduction of DenseNet, several variants and extensions have been proposed. CondenseNet, for example, learns to prune connections during training, leading to even more efficient models. Dual Path Networks, DPNs, combine the benefits of ResNet's residual learning and DenseNet's feature reuse by maintaining two separate paths, a residual path and a densely connected path. Dense nets have also been combined with other advanced techniques, such as attention mechanisms and squeeze-in excitation blocks, to further improve their performance. The dense connectivity pattern introduced by DenseNet has had a significant impact on the field of deep learning, influencing the design of subsequent architectures and promoting the idea of feature reuse. Efficient architectures, mobile nets, shuffle nets, and Moria's deep learning models are increasingly deployed on resource-constrained devices such as mobile phones and embedded systems. The need for efficient neural network architectures has become more pressing. Efficient architectures aim to reduce the computational cost and memory footprint of deep learning models without significantly sacrificing accuracy. This has led to the development of models like mobile nets, shuffle nets, and other architectures specifically designed for efficiency. Mobile nets, introduced by Howard et al. In 2017, are a family of streamlined CNN architectures designed for mobile and embedded vision applications. The key innovation in mobile nets is the use of depthwise separable convolutions, which factorize a standard